Thank you. Hello? Hello? Is this working? There we go. Hello everybody. Nice to be back. Okay, cool. Very nice. Nice to be back, first of all. It has been like so long time. I've been busy with school and yeah, job work. I'm trying to learn how to make this compiler, so it has been like 4 months trying to understand how I'm gonna build it, and it actually proves to be much simpler than I thought. You just have to know exactly how to do it. Yeah. Hello, Mr. Castleman. Welcome to the stream again. That Tin Kid, welcome. Welcome to the stream. All right. Yeah, as the title is saying, I'm gonna make a compiler. I'm gonna start today. We're gonna start completely from scratch. Let's see if I have the project here. Yeah. So nothing is written. I'm gonna start completely from scratch. And we're gonna start with simple makefile. Nothing special. And I'm gonna do it a little bit different this time. So let's first check the volume. Is the volume a little bit low? I don't think I've changed the volume here. I just installed OBS, so I don't know if the volume is right. Starring soon is still on the screen. Yeah, thank you. There we go. Is the microphone a little bit low? Can try to increase the volume a little bit. Is that better? Okay, cool. Anyway, yeah, so I'm gonna take a little bit different approach this time. So last time, I don't know if I remember what we did last time. I think we tried to make the entire Lexer, and then I don't know if we started with the parser, but I'm not gonna do that this time. We're gonna try to make like an incremental approach. So you're gonna actually build assembly code as we go. Yeah, so we have nothing here. Where should we start? I'm just gonna make a simple assembly program, like 4 lines, just to illustrate how we're gonna build this. And then I'm gonna give a little bit of an overview, like how this works, and then we're gonna start with the Lexer, like a really simple one. We're not gonna implement everything. We're gonna just start, and then we're gonna do the what is it called? Like recursive descent parser, descent parser. It's some recursive shit in C. So we're gonna take a look at that. Okay, nice. The volume is perfect. Yeah, it's so nice to be back, by the way. I really missed it, because I'm always talking when I'm working, talking to myself, and that's kind of lame. So I like doing this. Yep. Okay. So let's start by just making a build folder. And we're gonna make an assembly file. I'm gonna call it output.s. So this is what we're gonna generate. So I'm writing this manually now, but this is gonna be generated from our program. And I've never written x86 assembly before, and I don't like it. So yeah, it's gonna generate shitty assembly, and then I'm gonna migrate to ARM, which is what this is gonna be built for. And probably I'm gonna do some like more work on the generator, but I first want to have the language sorted out. Personally, I insult myself often. Do you? Okay, and I'm gonna switch the keyboards because I'm using this new keyboard and I'm learning Dvorak, and it actually goes very well, but I feel like the people watching want to have a little bit higher speed on what I do. So let's just choose the right keyboard. So global, this tells it is like something like extern in C. And we're gonna declare main as global. That's gonna be a function. And we're gonna define it here. And we're just gonna say, we're gonna move the value 5. Why is its keyboard not working? There we go. What the hell is that US keyboard? Huh. Anyway, we're gonna move the value 5 to RAX and return. So basically this is supposed to return the value 5. And this is one of the registers in x86. I'm not an expert on this, so yeah, we're gonna move this in here and that's gonna be the return value. So we should be able to run this. Let's just see if the build is working. Yep, it is. You misspelled global. Yeah, I think it's supposed to be like that. It's supposed to be global because yeah, like Linux people doesn't like to type out the words completely. They like to use short words for like abbreviations. So this is much shorter than this. It's so huge difference. But I think it's supposed to be like that. Yeah, we're gonna call GCC. We're gonna generate an output. There is something weird with my keyboard. And output.s. And we probably should specify the output file first. Okay, like the typing is gonna go up, I promise you, because I have to do the switch mentally. Okay, so we're gonna generate the output file from this assembly file. Let's see if that works. All right, that works. All right, so it compiles, or it links, or it assembles, and we're generating an executable here. So now I'm just gonna execute that application and see what we're getting. Something is very wrong with my keyboard. Anyway, okay. So we're gonna do build and output. And if I make it, I'm gonna have error 5. So that's very interesting. That's, unless it was intentional. Yeah, it was intentional. And that's very interesting. Like the value 5 is what we're returning from the assembly code. So something is working. This is the basic thing we're gonna do. Yeah, so that's RAX. And yeah, we're gonna start here and try to make, today I'm gonna try to make a program which can compile basic expressions and parentheses and order of operations, plus minus, divide, division, multiplication. It is very simple because it's a beautiful algorithm which we're going to use for this, and it just handles everything. It is really cool. You may compile on assembler. Yeah, so we're going to compile to x86 assembly, and then we're going to link that, or we're going to call the GCC assembler on that. And that's very convenient because I can actually call C functions from here. So if I, for example, want to print something, let's see if I can, let's make a new file under test here. So I'm gonna do oh my god, I'm so slow. probably should switch again. Standard.c, and here I'm going to include stdio for printing and stdlib. I don't know if I need stdlib. We have to see. We can probably just use stdio. And then I want to make a function called printf. Oh, probably we don't need to do that. Let's go in here. And how do we make, like, we have to do a label. So string, and that's going to be a ASCII C. Okay, so this string here is supposed to end with 0. I think it's this syntax here. Yeah, so we're gonna use GCC first. We're gonna link in these functions that we want, and like when the compiler is working a little bit more, we can start doing the syscalls ourselves. But I'm a little bit unsure there. Because the syscalls, because this is eventually gonna run on my own operating system, and how it works is that I have to call this, like, that's not gonna be a compiler thing, that's gonna be a standard library. So I want to be able to like write inline assembly functions in the language. So possibly I have to implement that first, and then we can try to make this work. Just 2 seconds, I'm gonna get some water. All right. Yeah, so we're gonna load the address, so load effective address of this string, probably here, into, what is the first register? Remember to align stack for print call. Yes, we're not gonna use a stack pointer, so it should be aligned from the start of the application. x86. What is it called? Procedure calling standard. There we go. So we're gonna push the registers in here. So RDI first, which is the first. So we're gonna load this into RDI, and then we're gonna call printf, and then return. Let's see if that works. Cannot be used with making a Pi object. I probably should make this static. So no relocation. Segmentation fault, that's perfect. ASCII 0, hello, I'm gonna search on that. Maybe the stack needs to be aligned. EAX. Yeah, I'm going for x64, so 64-bit. Okay, so format, that's ASCII something. Oh, wait a second, isn't the RAX supposed to be 0 before this call? I think so. I don't think that's the issue though. No, it isn't. Alright, so let's just see how he does it. We have to mark it as data first. I don't know if that's necessary, but we're gonna do it. data. Okay. Text global main. Yeah, we probably need to add the text section here as well. And I guess this is for not for using for supporting like relocation, I think. I don't know about that. And call print, that's exactly what I'm doing. And move on to source index. Okay, so we're gonna try this. We're gonna add the RIP, and we're gonna move 1 to RSI and 0 to racks. If this doesn't work, I'm gonna ignore it and define a reference to fuck, that is supposed to work. Okay, let's try something different. Let's make a function printer which takes in a string and just calls just prints the string with a new line. And I'm gonna change this to print instead. Hey, come on, a phone. Undefined reference. Wait a second, we're not linking this in. Wait a second here. Okay, that makes sense. Alright, I think I know what I'm doing now. I'm not, but let's try to call GCC. We're gonna make the C option, which is telling the compiler to only compile. It is not gonna link. And it's gonna compile, let's see, test standard .c, and output is gonna be called test, or it's gonna be called build standard. Okay, let's do this instead. So you're getting the standard here. That's fine. And now we're gonna link in that as well. So you're gonna give it the test standard. I'm gonna switch keyboard, I'm not kidding. Test standard. Test standard, that's supposed to be build standard. Why isn't this working? Look, are we supposed to do it like this? Yeah, we consider the stack frame for main, but that's gonna require something more. Let's just try his code here. Let's see if that works. Assembler, makefile error 2. Okay, that works. Wait a second here. What the hell? That works. Okay, so it's printing. So let's call it print instead, because this shouldn't have any formatting. So I'm gonna try this, and it still works because we're calling our print function here. So what the hell did it do? Extends to RSI, source index. EX. Should we need to do this? RBX. I should think this goes slower. I'm gonna switch keyboards again. Okay, so it still works. As I expected. I'm gonna switch keyboards. It might be a little slow, but it's gonna be fine. I'm very fast at typing some compiler stuff here. So for example, okay. That goes really fast. Okay, so we're gonna just start with this. So that's how we're gonna do printing and like debugging. So I can also write simple like test functions here in C, and I can call them from my compiler, which is really cool. So when we're gonna do like automated build and automated testing, we can make the assert function here and just call it from the C thing. All right, that's a good start. We don't need this one. I'm just gonna include this and hope it still works. So we can do F here instead, and it works. So it's having error 6. Oh, now I know why it doesn't work. I have an American keyboard. I have Norwegian setting. So I'm gonna move 0 to rax, and that's supposed to compile successfully. Okay, that's a good start. It was a little slow start, but that's fine. So now I can write thing in the assembly code here, and I can print it, and it works. Perfect. The moving to 0 didn't solve the... It solved the error I was getting here, but this is not an error. This is just that... I don't know if that's global or is it just for Linux, but in Linux it's supposed to, like, every thread or process is going to return a value, and if that is non-zero, Linux assumes it's an error. So when you want, that's like that's why I have like return 0 at the end of main, because that's a success status code. Hello, Big Bon, welcome to the stream. Yes. Okay, perfect. Yeah, let's make a little diagram. I'm gonna just okay. So we're actually gonna develop this all together. Like, wait a second. The color here takes my entire brain capacity. There we go. We're gonna develop like all the parts together, like incremental. So the first part is a tokenizer or a lexer or whatever. So this is the first part, and this is not lexing the entire file. This is gonna be incremental. So when the parser, which is the next step, asks for or needs a new token, it's gonna ask this lexer for it. And then we have the parser, and then we have the typer, and then we have the generator. And we also have like, we're also gonna have a different module here, which is called like printer. This is not really a part of the compiler. It's just for printing the abstract syntax tree in a nice way. All right. So let's say I have some program here. I'm gonna write it in C because that's simple. Yeah, let's just stick with this. So the lexer will, let's say this is the entire file. The lexer will get the entire file. It's not gonna do anything with it. It's gonna contain, this is gonna be like basically a structure which is gonna contain the current location in the file. So the only thing this knows about the file is where it's currently at. So if I read the first token, which is supposed to be void, then the lexer will hold a pointer to the start of the M word. So then the parser can just ask like, get a new token, and the lexer will read the next thing, word, punctuation, whatever, and it's going to generate a new token of this. And that token is going to have the source location, like where it's in the file, and the line number, the column number. It's going to contain everything. And it's only a pointer, so we're not going to copy any data around, because we're going to have this file in memory as long as the compiler is running. That's going to make it much simpler, and it's going to make the error printing much easier. Wait a second here. I've forgotten to do this. Just give me 2 seconds. I'm gonna start Streamlabs. 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 I think that's what it's called. Not download. What happened to your previous language? Unknown. That was shit. Completely useless. So yeah, I did a new name of this. It's called looks. What the hell is it called? Something with looks. Luxury. Luxury. Yeah, Luxury is it called. I don't know. I just like the extension. Login. Wait a second here. Widgets. Alert box. Copy. Okay, there we go. Browser. Is that working? Let's see. Yeah, it is. Perfect. I'm gonna place this up here in a corner. To unknown, yeah. Fuck unknown. Yes. Okay, so this is gonna just get a new token. It's gonna this is gonna generate references into this file, this source file, which is supposed to be really much bigger. Also, because we don't need all the tokens. That's the point. So we're gonna have like a token cache or a token buffer, ring buffer, whatever. Oops. So this is gonna be the current one. And we're gonna sort of make a ring buffer, and we're gonna store the next tokens and the previous ones. So if I'm currently at this token here, which is, let's see, 1, 2, 3, the opening parenthesis. So this is the open parenthesis. I still want to contain the void and the main token in the cache, so that if I want to undo a token, I can do that. And that's going to be really convenient in some cases, because either you can, if you have a function in the language where you check like 20 things, instead of doing the next token on all these 20 cases, you can just assume that the token is valid, and if none of these 20 cases hit, you can just undo a token. It's going to be more clean code. And also we want to contain next tokens. So if I want to peek a token, I can just generate these two here, and I'm still at this location here, but I have parsed these functions, these tokens here. Yeah. So if for example I'm doing, like, let's make 2 more. If I want to peek, let's say I'm at void here, and I want to peek 1, 2, 3, 4 tokens ahead, then I'm basically looking for this token here. So what I'm gonna do, I'm gonna parse or lex all these tokens, and I'm gonna return this one. And I'm still at this token here, so when I'm now like asked to get the next token, I'm gonna just get it from the cache here. so that's the tokenizer. Yeah, and again, we're gonna make it really simple. The parser is gonna take these tokens here and generate a syntax tree, and we're gonna generate it really cool. So this is the algorithm for making the entire expressions. What the hell doesn't that work? The entire expressions work. So we're gonna do a recursive algorithm, and we're gonna track the priority. That's how we're gonna build this the right way. So let's write something here. Times, we can do times 4, no, times 3 plus, and some in the parentheses. Let's do times something like this. Okay, so we want to parse this. It's actually really simple. I've done it before, and it's literally, how many lines? Like 20 lines. It is so simple, but it's a really cool algorithm. So the question is, we're gonna build this like, we're gonna have three different constructs. So we're gonna have special expressions for different cases. So we're gonna have one binary expression. So this is a binary expression, and this is going to be a structure, and that structure is going to point to two other expressions. So it's going to point down here, and it's going to point over here. So that's the word binary. It's pointing to two other things. And then we have unary, which is only pointing to one thing. Unary. So this might also be the multiplication symbol, because this is supposed to be a deref or an address, depending on how you want to write it. And then you can have like an expression here, like a number, whatever. All right. So the question is, like, how do I say this? First of all, this part here is really going to be a unary expression. So it's going to be parsed as a unary expression. I'm going to get back to it later, but let's make it simple here. 1 plus 2 plus 3 times 3. So this tree will be very stupid that doesn't work. All right. So that's going to be 1 times, it's going to be a plus here. So 1 plus, no, it's going to be, it is going to be times, that's going to be a 2, that's a 3. And then you have the 1 here, and it's going to be a, and it's going to be a plus symbol up here. So basically you want to take 2 times 3 first, and then you want to take the result of this operation and you want to plus it by 1. Yeah, so this is going to be how that's supposed to look like. And if we're iterating like this, so I want to do this one, and I'm plussing, and I'm doing plus a new expression here. How is this gonna work? Like, the question here is, you're gonna make a new, this is how we're gonna do it. Like, you're gonna have 1 and plus something, and that is supposed to be something. I don't know how to explain it. It basically uses the operator to determine if we're going to recurse or not. So if the operator precedence is rising, you're going to build a tree. Like, fuck this. How am I going to explain this? So this is 1 plus 2. All right, okay, so we have 1 first, we have a plus, so we're gonna make a binary operator, and we're gonna call this call expression recursively. And we're gonna track the priority. So let's say the plus is priority number 1. So plus, that's equal to 1. And time is equal to 2. Times is equal to 2. So we're getting the priority 1. So when you call the parse expression on 2 times 3, you have the priority 2. And then you're going to check if the priority rises, which in this case it does. And that's going to... Yeah, so the priority rises. So if the priority rises, you're going to make a new expression. You're going to continue to recurse down. So since the priority is rising, you're going to continue to recurse down, which is 2 and 3. So this is what you started with, and you're going to continue to recurse down. If the priority here is still, if it's still rising, so let's say you have like a division or something, and that has higher priority, this is going to be the sub-expression, and you're going to continue to recurse down this way. So this will be like 23. And you have the division symbol up here. And then on the way back, you're gonna link it into this symbol. So this is gonna point to here, and this is gonna point here. If the priority falls here, that's an interesting case. So if the priority falls, you are not gonna recurse down. So you're gonna get the 3, and you're gonna return from the 3. So that's gonna effectively return this 3 number here, and then we're going to do the pointer swap. Fuck this, I'm going to explain this later, but we're basically going back here, and we're gonna, this is basically, fuck this, okay, I'm gonna just start doing the code, dang it. Yeah, it is gonna be like, it's much easier to explain once I write the code for it. But anyway, the parser is gonna make this tree thing works, and it's really simpler than it looks. And since this is not gonna, like in C you have to declare stuff before you're using it. In this language you don't need to do that, and that forces us to have like a separate pass on the type stage, so we have to figure out what a type is. So for example, in my language, let's write it here. You should be able to do, so let's say data is equal to 3, 4, 5. So you're not declaring data, you're just saying that that's supposed to be 3, 4, 5. And then you have like an if statement, whatever, and then you say like data is supposed to be U32. So this is gonna work in my language. So even though this is up here, the declaration is down here. So when I'm parsing this data equals 3, 4, 5, and the parser doesn't know what type this is. So it has to do like the second pass and figure out all the typing here. It's gonna be some typing on the structures, figuring out the offsets. That's basically the stage here. And if I'm doing more advanced type inference, it is also happening in here. And also the types and references, if I have like, if I want to make a token here, so I say token equals token. The compiler doesn't know what token is, because this is defined in a different file. So it just has to assume this is an identifier, which is a type, so it assumes this is a structure, and it's gonna just save the name, and in the typing stage it's gonna figure out what exactly that type is. Has this been defined before? Where is it defined? Like auto in C. C doesn't have auto. I think auto in C is a different kind of thing. I think it has something to do with static. It is not like type inference in C, I think. Auto in C++ has the, like, that's correct. Builds X3 doesn't need postfix notation. Your algo that builds X3 doesn't need postfix notation. it is going to parse postfix expression as well. I don't know what you mean by that. But it parses everything in one single function. It's going to check, it's basically using the operators to determine if it's going to recurse or not. It's a really fast algorithm, I think. Oh, autotype. Yeah, so we're going to definitely have type inference, some simple type inference. So I'm going to do this the same way as there is one other guy at Twitch who makes a compiler, and that's really cool. I know Go does kind of this here. So I want to do this also because I like it. So this is, you're declaring data, but you're not giving it a type. And that's supposed to be this. And then it's a question, because I know also in the language J, he uses double colon for something. I haven't like figured out what it's used for. But I thought about it for a few days ago, and with structures, you're not defining a variable, you're defining a type. So if I, for example, say token, let's do a big T. Token is a structure. This doesn't make sense because token doesn't have the type structure, it is the type structure. And what if you want to write some like anonymous structures? So for example, I want to have like new token is equal to structure something, and this is going to be a variable. So I should be able to use this new token in the code, so it doesn't have a name structure. That would be the correct way of writing an anonymous token, anonymous variable, I think. Which means that we have to do a different notation on this. I don't know why that's the way he does it, but doing this kind of makes sense for typedef. So I'm not sure if we're going to do that. So then I would, for example, be able to say like IPv4. That's supposed to be a U32, and let's do this. So you're defining this type here to be a U32. So then you can just write like, I want IPv4 0. So new token is an IPv4. So I think that syntax is really cool. I know that's not the way he does it because functions are, in this case, the functions should be something like this. And that doesn't make sense to have two colons there because a function of the type, I think. No, I think I'm gonna have it like this. Actually, it should be like this, but I don't like it. We just have to see. Double colons are constants. Oh, postfix. I don't know what do you mean by postfix? It's gonna be expressions, and we're gonna parse the postfix expression like plus plus, or what is postfix? An array function. That's gonna be like also parsed. We're gonna get to it. In J it is, double colons are constants. Okay. I understand. So, but you'll be limited by stack size during parsing with that, right? Yeah, so we're gonna recurse down. There are other algorithms which uses way more functions, and that's gonna require more stack space. So as far as I know, this is the best way of doing it. Like otherwise it's gonna be really complicated. Like everything you can do with recursion, you can do with loops, but I don't see the point. It is a really nice algorithm, we're gonna use it. So it's a constant lambda. I didn't know what lambda was for 2 weeks ago, and it was a function. Why not call it a function? I don't know. It's a constant lambda, okay, constant function. That makes sense. I think we're gonna have a constant keyword because I like to see the const thing. I like this for typedef. And that actually makes sense for me because it is very easy to see you're defining a type here. If I'm gonna make some more advanced structures, let's have a token. You should be able to do both tagged structures and untagged. So this is an untagged structure, which means if you have, let's write it the right way. If you have token, which is the type of token, you should be able to do token and let's call this member. You should be able to token member because this doesn't have a name. If this had a name, you could, for example, say data is this union. And then you would be required to do data member. And that makes sense because you're using almost the same syntax, but here not defining a type. So I think that's really cool. But yeah, you can also use your own heap allocated stack instead, but that can get messy. Yeah, probably. I don't know how to do that. Anyway, this wasn't exactly what I planned for today. Let's just jump into it. Let's close this one. Let's do this. Include. I think it's an include. Okay, so we definitely want to have some list list functions there. I'm going to be using a circular double linked list. We're going to also be using these types here. And we're going to make a string type. I think that's a good start. So let me just copy in these things really quick. Hello, long time to see you. How's everything? Yeah, it's very good. Like, it's a little bit easier at school now, so that's cool. And I just was bored and alone, so I thought of streaming. This is supposed to be include. And that's types string.h. That's for, I'm gonna make the data type string because I think C should have that, and we're gonna definitely implement that. Types string, what was the last thing? Yeah, lists. And this is gonna have, like, list is only gonna be a header file, so we don't need to make a C file for the list. And the string, I want to implement string compare. So the question is, should I make it inline or not? I probably will not make it inline. String.c. We're gonna make a main file. We're gonna fix the make file. You know what? I'm gonna try the alt keyword again. This is going way too slow. There we go. All right. So we're gonna define the top place where this is executing. So this variable here is gonna be where, like, what path I am in. So I'm gonna say, I'm gonna execute in shell, and I'm gonna say pwd. Is that right? Let's have info. I think this is the right syntax for it. Yeah, so we can see this is giving us the path, and we're gonna specify the target, which is gonna be luxury. This is the executable we're gonna make. So when I'm done, I should be able to do, like, just execute this application here. We're gonna make it build directory. Luxury. Let's make the build directory first. So I'm gonna just say build. Actually, I'm gonna say top build. Okay, now it's coming back to me. So top build. and this is going to be build luxury. So if I print this target here, it is going to give me luxury build luxury, which is exactly what we want. I like everything is an object conception. Like in Swift, for example, you have an extension for int. Like, what did you mean by object conception? You can do an extension for int. Yeah, like make type defs and stuff like that. I think it's sometimes it's useful, and it can also get very annoying if you're using it too much. All right, so what I like to do on the makefiles, I'm just gonna make it really quick. I like to just add the source files and the include files. That's the only thing I'm just listing it in here. And it's gonna be a relative path from where the makefile is. So basically the source has to have source before. And I'm gonna add in string.c, and we're gonna have in main.c. And for the include, we're gonna do list.h and string.h and types.h. So this is just listing these things. So I can also print this just to see what it yields. So you can see that this variable here has all these symbols. I moved on from C. I only use it for legacy stuff now. Rest. Yeah, I don't like when I started making, like, thinking about this compiler, it is so many things with C that I don't like. And you only like realize it once you try to make or try something else. And it's really bad, I think. Yes. So I'm just gonna make a quick variable here, which is gonna be called like src. We can also call it like source g, stands for source global, and include g for include global, and we're gonna add the prefix. So we're gonna do add prefix. And this is the makefile I'm using for every single project. It is really nice. So we're gonna add the build. Let's see, should I link this? Yeah, so we're gonna link and build together. So I don't need to have like separate object files. That's gonna make it simpler. So I'm gonna just have top here, and then I'm gonna use the source files. And we're gonna use the same here. I'm gonna add the top directory to the include files. So if I now print include, it is gonna list all the global directories, which is what I want. And all is gonna build all my files. And if any of the include files changes, I'm gonna need to rebuild this target here. So this is making sure that if I change a header file, I need to rebuild every single thing. And some IDEs doesn't have that, and that's really annoying. I think I debugged this problem like a few hours because I was changing the header file and it didn't work. Yeah, we're gonna have a rule for like, how did I do this? How did I do this? This is gonna make a... Do I need to do this? I don't think I need to do. This is gonna... Luxury. This is just gonna build the thing. Actually, I'm gonna have it in here. So this is depending on all of these. We're just gonna call into GCC, or the standard CC compiler. and we're gonna link it with std equal c11, which is really nice because then we can have like bools and other cool stuff. Yeah, we're gonna take in all these source globals, and we're gonna generate the targets dot elf or exe, and we're just gonna generate the targets. So just this executable here. And let's write something in main. All right, testing. Okay, so include this, gonna get rid. Let's try to do make luxury. Error, luxury source string. No such file. Why? Let's close this one. Why wouldn't that work? Document luxury source string. No such file. Should I need to write anything in here? I don't think I need to do that. Source. That is right spelled. Oh, I have a space before it. Shit. There we go. Cannot open file. Linker. Build luxury. Okay, perfect. So what we need to do here, because this is telling GCC to place it in this build folder. So we need to, if this is not made already, we need to make that directory. So we're gonna call make dir p with this build folder. So if I now do this, it's gonna make this build folder, and it's gonna make the executable. So if I now type build built-in, it's gonna say testing here. So that's supposedly working. We're also gonna make a clean target. We don't really need to do that, but it is nice to have. So clean is gonna do rm rf the entire build folder. So when you see I'm writing this @ symbol, this is basically suppressing the output. So the make is not gonna, because make files like to print the command before they do it, and that's gonna prevent them for printing that. Okay. Also, we want to stop this. Yeah, we can just delete this. So this is the first target, and that's going to be the default one. So when I'm just using make, it's going to run this one, and you can see it works. And also after doing this luxury, I want to call it. So I'm going to make the old target here, and that's depending on luxury. And I'm going to print, or I'm going to echo done. And then we're gonna run this executable. So build luxury. So if I now type make here, it is gonna print done, and it's gonna start to run this executable. So what we want to do here, we want to add in the files, so the source file into this executable here. So I'm gonna specify the test file. So this is which file I want to compile basically. So I'm gonna call it test0. I'm just gonna call it main. Yeah, main.lux. So this is this file here, and this I want to compile. So let's print hello here, just to see if this is working. I want to give this as an input to the executable. So I basically want to specify I'm gonna say test file, and we're gonna do add prefix, and the prefix is gonna be test, and what we're gonna add after test is gonna be the test here. So basically we're taking this here and we're adding test / before it, and we're gonna give it here. Add prefix, let's add top here. So top, test, and then the test. And we're gonna give this to the executable. Okay, it's beginning to go a little bit faster. And you see it still works, that's good. And now we should be able to print this, what we're giving to this to this application. So if I'm not mistaken, the first is the argument, like how is this? Argument count first. And then a char double pointer to the arguments. Okay, so I want to have 2 arguments. I'm gonna do an assertion on the arguments first. I need to include assert for that. So we're gonna assert that the argument count is equal to 2. So the first argument will be the function itself, so luxury, the compiler itself, and the second argument will be what we're actually giving it. That makes 2 arguments. And we're saying arguments 1, which is the second argument, and that's the string pointer or char pointer, and we're just printing that. So we can say that the argument from this function here is the file, which we're going to compile. So that's nice. So what we can do here, we can do compiling this file and outputting this file. And I'm gonna say argument 2 here. And we're gonna define the output file as well. So this is the test file. I think I will just hardcode in the output file. So the output file is gonna be build, because I want to place the output file is the assembly file we're gonna generate. So build, let's call it output.asm. So if I now run this, yep, it fails because the argument is now 3 and not 2. Okay, so it's gonna compile this main file here, and it's gonna output this output assembly file. So that's a good start. I think, yes, so the next thing we're gonna do, we're gonna just read the entire file into some kind of pointer, some buffer, and we're gonna give it to the Lexer, and then we're gonna start tokenizing this thing. So let me just copy in these header files that I want. Let's get in the list. And I've also changed a little bit the style I'm typing in, because I went back to what I originally did, and then I saw the Linux stuff and changed my style, and I didn't really like it. So I'm gonna go back to what I was actually doing. Yes. So I'm gonna do some changes here. Let me just copy in the types first. So that's done. So this is my favorite types. We need stdint and stddef for this. Why do we need stddef for this? We don't. Yeah, you know that. All right, so that's the types. String, this is the string header file. We're gonna say if not def string.header. And if I'm gonna include types here. And also when I'm including types, I'm specifically looking for this types.h here. And that will not work. If I had written it like this, it would work. Yeah, this would work, because when it's like quoted, it is gonna look in the same folder first, and then it's gonna go and ask GCC where it's gonna look. If I write it like this, which I think looks cleaner, it is gonna just go and ask GCC where I'm gonna look for the include files. So now this is gonna ask GCC where do I find this type here. So we have to tell GCC that it's gonna find the include files in the include folder. So this is the I flag and include. So now GCC knows where to find those. And this is including types and stddef. We need stddef for this null pointer, which I don't know why I'm using. Let me just rename all these nulls to 0. There we go. And this is fine. And we're gonna make a string. We're gonna make a string structure. Also, I like I like writing it like oh my god. Okay. You know, I don't think it's better to just... I'm very sorry about the keyboard thing. I thought this was gonna go smoother. Struct string. So this doesn't work in C because we need to have a typedef on this. So what I like to do, I like to have a typedef header. And if. And here I like to add all the typedefs. So I'm gonna say typedef struct string string. So when I'm referring to this in the code, I could just write string here. Also, I want to have some typedefs for the list. So I want to say struct list is equal to list, and I want to typedef. I also want to typedef list. So this is the structure. I want to give it a different name as well. List node. Because this is a circular list, I'm using the same structure for the list and a list member. So that's why I'm just calling it two different things, so it makes it easy for the reader to know what I'm doing here. Inference structure. In a fairness struct, yeah. So that was what I was thinking to do. Okay, so that's a type def. This is included in here. Okay, now it's beginning to get up with speed here. So including type def there and here, we don't need it there. Okay. I also want to rename this to list. Let's see if I can do a full rename here. Yes, I want to change this. So structure list, and I'm type defing this. So this should work, I think. Yes, let's try that. So we're gonna have a char pointer, which is what is in the string. So I'm gonna call it text, and we're gonna have a size. So this is the string, and we're gonna have one simple function. It's gonna return a bool, string compare, and it's gonna take in two string pointers, A and B, and we're going to compare and see if they are equal. All right. U32 size, yeah, that's a 32-bit integer. C strings are just yikes. Yeah, I'm actually thinking, because we need to, the lecturer needs to know where the file ends. So I think I will do a null termination on the file, just to make the checking a little bit faster or simpler. I don't know. We have to check that. What kind of language? This is like, it is going to be inspired by something that already exists. It's going to be simpler, and it's going to make it possible for me to add things that I like into the language. So I'm basically targeting the new language I'm going to use for embedded development, OS development. So basically what I've been doing on stream previously, I'm going to do it again, but in my own language. Because I think, yeah, C needs some changes. But also, at the same time, I don't want to have, because there have been several attempts on rewriting C to something that's better, and I feel that many of these attempts has been like unsuccessful. Like, they're better languages, but they're so far from C. And C is like, it's a really good language. It's just some issues with it, and I just is gonna try to fix those and nothing more. How have you learned how to make a compiler? Uni class, to be honest, no. I have a university class on compilers. And I like the first day, this is actually quite funny. The first day I was having this class, I learned about regular expressions and stuff like that. And I was doing a stream on this, and I wrote like 1,000 lines. Like, I think it was 1,000 lines with this stupid regex generator crap. And then this guy comes into my stream and just, you can't do this. You have to just do a recursive descent parser and like just write normal C code. And that's so much better. Like, I was testing the lecture we did last time. I didn't know if I said it, but I just copied the file. I just copied the FAT32 driver I just made like 100 times, because that's around 1,000 lines. So I was lexing 100,000 lines in, what was it, like 5 milliseconds? 5 milliseconds on 100,000 lines. And that was like 500 lines of code for doing that. So that's not the bottleneck. So I just don't understand why we should learn this. It is really simple to make a compiler once you know all the steps into it. Yeah. I'm gonna stop ranting here. Yeah, I really miss how to program good and clean in university, and it's so horrible because we previously we had this elevator project, and they just say like, you're gonna have multiple elevators on a network, make them work. And people come up with these crazy ideas with, oh, we need a ring queue, we need a master, what if the master goes down? Then we need a backup master, and all this crap. It just makes it so difficult. And they should TCP and stuff like that. Like, I wrote it with UDP broadcast only in 300 lines. I'm sure that's the simplest solution ever. And all the people in my class goes around and like, oh, you can't write in C because that's too difficult. But yeah. So I think they should, instead of just saying do whatever you want, try to give like a little bit like how to do this the right way. Because sometimes programming is just the right way and you just have to know exactly how to do it. Still in job hunting. Just out of uni in February, I'm still in job hunting. I'm sure you're gonna get a job. You're on the programming section in Twitch, so that's a good thing. Yeah, that's exactly. I totally agree. I'm not a pro, but I really enjoy what I'm doing, and probably all the time I should be spending on school, I've spent on doing programming stuff on my spare time. And I mean, it's very hard because I haven't learned anything how to do it the correct way. So all the time I'm getting these, what do you call it? Like experiences when you have been doing things wrong a long time. But that's good because then you know you have been doing things wrong. So yeah. No way how to start. I mean, OS Dev is very hard to start with, do I think. I think it's much simpler once you have a platform which is a bit smaller, because then it's easier to know the entire thing. So I'm using ARM, simple ARM chips, and like they have no bias, they're really simple to set up. Some of the higher end has virtual memory, so that's cool. But yeah, but it's hard to start. Like everything else is very hard to start with. Don't even touch 32-bit shit for. Yeah, but I'm gonna try to make an operating system in this language here. So that's the plan. All right. So we're gonna check if why can't I do this? Type def struct string. That is correct, isn't it? Should I probably open in, what is it called? VSL. Reopen folder in VSL. Am I already in VSL? I'm missing the autocomplete here because I'm including typedef. Struct string, and this is defined here. That's fine. And it seems the autocomplete works. Anyway. Okay, so if the sizes doesn't matter, if the sizes doesn't match, we don't need to check anything else, because we know that is very quick, like a quick check. Otherwise, we're gonna do a for loop. So it doesn't matter if we're doing the A size or the B size, that doesn't matter. So we're gonna iterate the entire size of A, and we know these are the right size. So we can just say if A text of I is not equal to B text of I, return false. And if this doesn't happen, we're gonna return true. So that's a simple string compare. We don't need anything else, I think. See if this works. Unknown type name bool. Am I using the wrong compiler? CCSTD11. I think I had a separate project on this. Wait a second. That's weird. Okay, so I was using it like this. Maybe this is the wrong order. I used the G option. I think that's for debug. And no common. Unknown type name bool. Oh, probably I need to include it. Is that in standard def? Yeah, bools are in C++, but the C11 extension has something for bool. No mem compare. I don't think we need mem compare. We'll probably need it, but we're gonna make it if we need it. Are you on Rust community Discord? I'm not. I should probably drop down a little bit. Oh, T-Soding is raiding! So nice! Thank you so much, Soding. Did you have a nice stream? I haven't been that much on Twitch, so I don't know what you do, but I think I saw you did something with some language thing. Are you making some kind of cool language? Yeah. That's really cool, thank you very much. Alright, triangle. Thank you, welcome everybody, it's standard bool, thank you. I'm just gonna add it in here so we don't need to include it all the time. And it works, perfect. But thank you very much. I don't know what you were streaming, but yeah, go check out Soding. He's really he's doing really cool stuff and games and like really funny stuff. Thank you for following. Welcome to the stream. Thank you, thank you. Yeah, so for the new people, we're making a compiler. This is the first day, and we're gonna try to. We've been setting up stuff a little bit now. We're gonna start with the tokenizer, like right now. I'm hopefully be able to like parse and generate code for expressions by the end of this day, I think. And it's gonna be like a statically typed language like C. It's gonna have a few different features, a little bit of an improvement, but that's the main idea. Thank you for following, guys. Thank you very much. Welcome to the stream. Showing Vulkan with, yeah, I saw Vulkan. I don't know what Vulkan is. Isn't that like some GPU stuff? IRRC. It's really cool. Yes, so we have made our string library. That's supposed to work, and yeah, this is the main file. So I think we just can start with the tokenizer. Yes, let's do this. Okay. First day, the most exciting day. Yeah, that's right. I haven't been streaming in like months. Like probably not since Christmas. As a Vulkan, that's a GPU API. Ah, that's cool. I've never done that before, but that seems really cool. Okay, so we're gonna make I'm gonna call it lexer.c. This is the lexical analyzer. I don't know why it's called lexer, but it's a really short and sweet name. So lexer.h, and we need typedef as well. So this is typedef, lexer, and we're gonna have lexer here as well. So if I now compile, it's gonna compile these files. What all you have done? String function and little main. Yeah, that's about what we have done. So we're gonna start from scratch here now. It's gonna be really cool. So strawberry overclock script once it was done. What is that? Awesome. Yeah, it's gonna be cool. I'm sorry, I'm really bad at writing if not defined. That's the worst word to type ever. All right. We're gonna make a structure called so where do we need this? We need to have it in a header file. So we're gonna make two structures, which is for the lexer. That's gonna be a lexer object and a token object. So the lexer is gonna sort of contain our position inside the file, and the token is gonna be given to the parser, and if the parser wants the token, it's gonna copy. It's gonna do a mem copy of the token. So that allows us to not copy all the tokens because we don't need all the tokens. It's going to be a little bit more, use a little bit less memory. And that's actually not a problem on these computers here, but if I'm going to run this on my A5 ARM board, that's going to be a problem because I have like 64 megabytes of RAM there. Bike shading. I know Pragma once. Pragma. I've never used Pragma before. I know it's the same thing, but yeah, like I'm typing faster than this. It's just that if not def is a horrible word to type. So we're gonna make a struct lexer object, and we're gonna make a struct token object. These two. We're gonna also include. Let's you know what? Let's go in here and include a typedef from there. Include typedef there. Okay, so now I'm gonna go into typedef and just type out these. There we go. So I had to think what we're gonna do here. String, should that probably be a type as well? No, I don't think so. Okay, so the token, how should we do this? Okay, the lexer needs to know the source file. So I think I'm gonna have a string object with the text. I'm gonna say source. Source file. And then we're gonna have a char pointer, which is the cursor, which is telling where in the file we are. We're gonna have a line number, line. Let's use just line, and column. This is the position in the file, so we can print line numbers, and I don't know if we need the column number. I don't think we need a column number. It is nice to have, but I don't like printing the column number because I think it's really messy. The token should also have these types of information. It's going to have a string, which is the name of the token. It might have a number. So we're going to make this U64 because it might be quite big. Name, line, column, number. We're also going to do one more thing, which I think is necessary, because you want to know the file name. So I want to be able to print. If I have an error, I want to be able to print what file it came from. And additionally, I want to be able to print the last 3 lines, for example, or 4 lines or 5 lines. And in order to do that, I need to know where the file starts. So either I can have a pointer in this token to where the file starts, so I don't have a segfault or something, or, and that's gonna be a pointer as well. I'm just gonna get the pointer to the Lexer object. And from this we can get the start location, we can get the cursor, we can get the file name, which we're gonna add in here. File name. Let's say file here. So file and file name. 2 strings. Getting confused by C++. Yeah, there is some difference between C and C++. I don't know. Okay. Using this cursor, we have to know where this file ends. So either we can save the end location of this file and just compare with that, or we can inject this 0 termination on the end of the file. And I think I'm going to go with the last thing. So we want to write must be with a 0. Must be terminated with a 0. And name, Lexer, line, column. We also want to type, and this is something I did wrong the last time, because I was using token type, which is a really bad word, because since we're writing a compiler, we maybe want to use the name type. So I'm going to write token kind instead. So we're basically reserving the word type. And this is an enum, and we're going to define it here as well. So this is token kind, that's going to go in the type def as well. That's missing an E here. So this is telling what type this is. So we might have groups. We're going to have a whole list of these token kinds, and each single punctuation character, dots, comma, what is it? Multiplication, minus, is going to have its own token kind. And all identifiers is going to have a token kind, and so on. So I want to have token none. This is if we don't have a token at all. We also want an end of file token. And we also want a count token. So this is really cool because this is going to be Yeah, count only works if we yeah, so this is gonna have the value of 1 0 1 2, which is the number of token kinds there is. So that's really cool. I just knew about this for a few weeks ago. U32 cursor. I could also do that. I'm gonna think about it. I could do that, definitely. And then we're gonna add in the tokens here. Identifier token number token string. Wait a second here. Let's add in just the one we need, because last time I did quite a few things, so I'm just gonna add in the things we need. We're gonna need the number. So I'm gonna say like now. So that's the numbers, and here is gonna go like chars, strings, identifiers, compiler keywords, and so on, intrinsics and stuff like that. And we're gonna have the punctuation beneath. So plus token token plus, token minus, token multiplication, token division, so let's see what we're gonna add in here. We should probably start with only those, and let's add in a few more. So I'm gonna say equal. This is for equal equal. This is comparison operators. Less. Greater equal, less equal. I think that's about it. Unary minus, yeah, that's also an operator. What are the enum value size? That's a really good question. In my language, I want to have enums a specific type. So you should be able to say, I want to have an enum. I don't know what the syntax for this is going to be yet, but some kind of kind is equal to a token kind. And then you can specify the type below, or you can specify the type of the enum. And if the compiler sees that this is going to go out of range or something is going to have a negative number, it's going to give you a warning. But you can specify the type you want. But I think this is a normal int, which on this computer is a U64. Token not, yeah, that's right. So there are a lot of tokens there, and I'm not going to add all of them because it's going to make it harder to implement. It's going to take more time. So I'm just going to make the most important ones. So less equal. There we go. And then we have division, which is the same as the commenting characters. Multiplication is times, minus, and plus. A number is fine. So this is going to allow us to, yeah, this is going to be what we're going to start with today. We're gonna implement all these things here, so we can write everything in the main file here, which is either a number or either one of these, and we're gonna be able to compile this together and generate the code for evaluating any expression with these tokens there, as long as it's valid. So if you're writing equal 2 times, it's not valid. And then you're going to print an error message. Modulus arithmetic operator is cool though. It's very cool. And it's as easy. Yeah, like a lot of these operators are really easy to implement, but if you're going to try to implement them all, it's going to take time. That's the only thing I'm worried about. So I'm just trying to shrink the scope of this a little bit. Weren't you making a compiler? Yeah, I was making a compiler before, but that was crap. So we're trying to do it again. Compiler stream, yes. We're gonna have and I'm gonna use dynamic allocators for this. So I think okay, this is not really important. I'm gonna have a Lexer object here. New Lexer. This is gonna take in 2 string pointers, which is the file and the file name. And this is gonna set up a new Lexer object and return that object. It's gonna be dynamic. We also want some functions for operating with tokens. So we want next token, Lexer, and this is really interesting because this is the function we're going to be calling all the way in the parser, like at least 100 times. I don't know, but you can see it's actually taking the Lexer as a parameter, and that's really important because this is going to have the cursor, so you're going to basically lex or tokenize on the fly. You don't need to lex the file first and then parse it afterwards. And that's convenient, I think. Token, we're gonna have a peek function. So peek token. That's gonna take an Lexer. We're gonna have peek next. This is gonna take in a count. So next token, peek next, eat token. I'm gonna tell you what these functions are doing in a bit. Expect token. Skip token, probably. There are probably a few more, I don't know. So let's just consider this this line here. So let's see, the current location is this Lexer. So the current active token is a Lexer name. The next token will then return the asterisk and move the pointer there. The peek next token will return this asterisk, but it will not move the pointer. So the Lexer will still be pointing here. That's a peek token, and that can be like multiple. It can peek further ahead than just one token. Eat token, it will return eat token. That will return. So let's see, I'm currently at this location here. Eat token will return this token that it's currently at, and it's going to advance the Lexer pointer. So it's going to get this token here. It's going to move. It's going to run next token, but it's going to return the current token. Expect token is going to move the token pointer, and it's going to expect that that token is a specific type. So here, we need to have a token kind. So we're expecting a token kind. And yes, we also need these kind of functions for keywords. So a keyword is just going to be a normal identifier, and then you can check for the keyword to be a specific string. And we probably want to restrict the use of keywords some places, but that's really too early to say, because I think you should be able to use struct as an identifier as long as it's not messing around with the code, as long as it has a unique and ambiguous interpretation. So if struct can only be used behind something like this, then you should be able to use structure elsewhere, because it's not gonna, the compiler doesn't care. I don't know, we'll have to see that. And skip token is just gonna assert that the current token is some specific type, and it's gonna skip it. It's gonna return the next one, assuming that the current one is the right type. Will be a VOD of this stream available later. I probably will download a video on this. I don't know, it has been like, yeah, probably. The cursor, an object later, because this way you can store the column and line of each token and use it during arrow printing and create stack trace. Yes, but I'm storing it here. So I guess we could make a structure for it, but yeah. I don't know. Because if we have a token, we have the line number, we have the column number, we have the lexer pointer so we can know the file name, and we have the string. So this is basically giving us the file name and the start pointer. So we can actually backtrack this string here a few lines if you want to print more, because we know the lexer pointer. I'm not sure. Yeah, probably. Anyway, and we have a token kind. We probably want to implement some keywords as well. So I'm gonna, no, that's not necessary now. We're just gonna implement this simple thing. Token kind, token kind. Let's implement these functions here. All right. So these are the functions. Let's see if I can, dang it. Doesn't seem to work. The autocomplete doesn't work. I'm in Linux here. Am I not? I think I'm in Linux. Let's check the status bar. There is okay, I think, let's try again. How do I install extensions? Maybe it doesn't have the C extension error. Extensions. enable install. That works. So it complains about the string. This defines string. If I have it here as well. Oh, dang it. Okay, I'm gonna be a little bit smart here. I'm gonna call it string with 2 G's, like a double G, and I'm gonna rename that later. Actually, we're gonna just hide it a little bit. I'm gonna call it str. That's not so bad. String, and types need to have type def string. All right. Okay, let's try that. No. Make a size. Dereferencing a pointer to incomplete type. That's probably in here. There we go. Let's hope it's working. Yeah, it's working. Okay, perfect. Now I have the things I need. And we're gonna include the thing is that an error doesn't only have a start point, something is delimited by an endpoint. Yeah, that's right. Just 2 seconds. You can traverse the file and count the new lines. Yeah, I was thinking just if I want to print, like, I can go back to the start of the line. That's very simple. I can go back to the start of the line, and if I actually need to, because I'm probably only going to be printing this once, or if I don't have any errors, it's going to be a little bit faster. And if I want multiple lines, I can just backtrace because I know the new lines and R's and stuff like that. So, but we'll have to see about that. Maybe I'm going to do it differently. Yes, okay, perfect. So I'm going to include standard library. std, what is it? Is it lib? I think it's standard library. So you're going to dynamically allocate this Lexer object, calloc. The size is 1, so I'm going to specify the size as 1 byte in a number of bytes. And we can say size of Lexer. So that's giving us a new object, and we're going to say Lexer file name. Okay, just to make it simple, I'm gonna assume those are in memory all the time. And they probably will be. I'm not gonna care about it now, so I'm just gonna save the pointer. So this is a string. I can say size is equal to file size and Lexer file name size is equal to file name size. Okay, so here we're just saving these, the file name and the file, and we have to know that the file has to end with the right termination. So that's saving those things. Lexer colon. I'm just going to explicitly tell what they are supposed to be. The line number is supposed to not start at 0 but at 1, right? The first line number is 1, not 0. The cursor, we're going to set the cursor equal to the Lexer file text, and this is the pointer to the first location in the file. Let's grab a new theme here. That's better. Yeah, so that's a new file. New Lexer. Let's just print the entire content of the file. Print. So I'm gonna say file is, and we're gonna do this. So this is, by writing it like this, we can specify the size of the string to print. So I want to print this many characters from this file. So that's the last thing we're gonna do. We're gonna just print the entire file. And then we have to see how we're gonna like load the file. So I'm sure there is some, not there, read from file Linux. I'll probably give it a C as well. I'm not gonna do that one. Get the in Linux C. I want to know, yeah, this is the one I want. fseek. And you can set it back by seeking to the start. So I'm going to use this for just getting the file size. This is going to return a string pointer, and this is just read file, read source file. And it's going to take in the file name, and it's going to try to read it. Yes. Probably have to copy this. Didn't I copy this? All right. Also, I want to do a different thing here. Types. I want to type that's the file because that's so ugly. I think it's called stdio. Typedef file. I think I can do this. So then I can say file. I want the file. I'm going to say fopen, and it's requesting the file name, and I'm going to open it in read mode. So I want to read the content of this file. And then we're going to search to the file. We're going to search to the end, and we're going to save the size here. We can actually make the, no, I can't do that. String. Yeah, I can do that. String. File content is equal to calloc. Yeah, I'm gonna say calloc1. size of string. So we're allocating a file, and we're going to say that the file content size is equal to the tell. We're going to tell where the file ends. File, and we're plussing on 1. So we have the space for the terminating 0. Why is calloc if you're set of fields anyway? Like, we don't need to use calloc here. We can say malloc. That's a good point. Thank you for following. Welcome to the stream, Bluefish. Blue Flash. I don't like that. So we're basically knowing how big the file is. So we're printing the file content size, and we're just reading arguments of 1. I think the first argument is supposed to be the input. I think so. Malloc, isn't that standard library? Is that maybe it? Oh, too many arguments. So malloc does only care about the number of bytes. So file size is 6, and that's because our file size is 6. So this is like 1, 2, 3, 4, 5, and space for the terminating 0, which is 6. And so fread, this is horrible. Oh my god. So we're giving it the pointer, and is this in like element size here? And then you specify the number of elements. And then the file. Is that right? And this is reading, this is returning the number of bytes written. Actual. Let's make this smaller. Okay. Insert. Actual is equal to file content minus we need to allocate the size here as well. Okay, and we're gonna do file is equal to malloc. Let's do file content size. So we're allocating that, and we're reading -1, and we're asserting that file content -1 is equal to the actual number of bytes written. And then we just set the pointer equal to 0. So this will be -1 as well. Isn't that supposed to work? Maybe I can just do this. That's beautiful. It's really hard to read though. Anyway. File content. Array subscript is not an integer. This is supposed to be size. Done compiling. All right. So this is getting a then we're gonna do lexer init. lexer new lexer you know what? I'm gonna do this instead. I'm gonna hide source file. Source file name. And if this is failing, we're just gonna exit, or we're just asserting that. Okay, so I'm ignoring that part. This is, we're gonna return a void for now. And we're taking in the string objects. So I'm just gonna say string here, it doesn't matter. And I'm gonna say file size is equal to this. And then you're mallocing let's say string size is equal to file size plus 1. This is so boring. You're setting the size equal to 1 more, and you're mallocing this thing here with this. That makes sense. And you're basically reading into this buffer, and I'm gonna read the file size instead and assert that that's equal to file size. That's better. And file size is equal to 0. And it's not gonna return anything. This is string. So I'm gonna call this with the address of source file. And source file name, I'm gonna ignore the source file for now. I don't care. So we're gonna give it a string file, which is the address of source file and the address of source file name. And this is returning a new lexer object, and there we go. So file is hello. Okay, that was way too long time for... I'm sorry, I didn't see the chat. Yeah. I want to add a null byte because that's going to make the checking simpler. Because if you want to advance a lexer pointer, you can either just check if that value is non-zero, or you would have to load the end address into memory and into register and just do a comparison. That's a little bit more expensive. Probably not going to matter, but... Are you seeing... No. It's a U32 file size. I probably should increase it, but... yeah, I'm not going to have a bigger file. Never. But it's very easy to change if we should have that need later. Okay, allocating that. That seems good. Let's make an example program, which we're going to parse. Minus that. And a semicolon. Let's add support for semicolon as well. So I'm going to just go in here, and we're going to add a punctuation character. And that's going to be token token semicolon. So if I'm encountering a semicolon, I'm gonna go here. And we probably should have a commenting also. But that's fine. We can add the commenting later. Okay, let's start. Next token. I want to make an internal function for this. So I'm gonna list all the internal functions at the very top here. Static void. I probably should exit if this is not right. I'm gonna say what is the word I'm looking for? Process next token. This is going to process the next token, and it's going to save that token to a specific location. And it's going to save it here. This is going to make it a little bit simpler with the cache operations. Because now we can just implement this function here that's supposed to have a token in the argument, and we can implement the cache in a different manner. We can just give it the right token here. So what I'm going to be doing, I was telling you about the token cache. I don't know if I want to call it token cache, but the Lexer should have a collection of tokens. I don't know how many. Should probably specify that here. Define. You can say like token peak count and token undo count. So let's say I want to peak 10 tokens and undo 10 tokens. Let's just say that. Then my cache needs to be okay, so if I want to have, so this is the number of undos. I want to have this one plus the current one. And also I will be forced to have a second one because I need to know where this peak ends. Yes, I think so. So the cache size will be 12 here. Can I do this? Token cache size is equal to token undo counts. I don't know if I can do this. I probably should be able to do this though. And let's plus 2 here. So we're gonna have a token cache and that's gonna have this size. And we probably want an index into that. I don't think we need a token into that. I think we're gonna just have an index. Let's just call it tokens, an index. I'm gonna call it token buffer size. There we go. So basically, I'm allocating, let's say 20 tokens here. And when I want to like process a new token, I'm gonna get the one I want from this buffer, and I'm gonna give the address of that one to this main parser. That's how I'm gonna do it. So let's just ignore this next token and stuff like that, and let's make this non-static. So I can test if this is working. We're gonna implement the caching later. Let's just expose this one. delete this. All right. Let's go into main here. We're gonna call it directly from here. So you're gonna say process new token. We're gonna give it the lecture we just made, and we're gonna give it a new token. To this function. And we're gonna do this while token type is not end of file. Yeah, so this is probably in some kind of while loop. If token break. Token name, size. Okay, so basically I'm just getting a new token each time, and as long as that's not end of file, I'm gonna print the token I was getting. Yes. We were discussing vulnerabilities. I don't know how to pronounce that. Not the language. Should protect against a malicious code. Hello, Psycho. Welcome to the stream. Nice to see you here. Check mostly errors and compile time. Yeah, I totally agree. Okay, so now we're actually gonna start. We're supposed to implement this function here. And the lecture has a pointer to somewhere now. So we're gonna this is the main function here. We're gonna divide it a little bit up. So we're gonna say that the token kind equals token none. So we're saying that the token is doesn't have a token, and if you're doing stuff here and the token kind is still 1 at the very end, oh my god, then it's an error. So we can just say exit 1 or something. So this is just for making sure that everything is handled. So maybe there is some absurd character that you don't have encountered, or there is something that you don't process in the file. If something like that happens, you're not gonna change the token kind, and then you're gonna exit the code there. And it's not gonna return anything, it's just gonna modify this token. So we're gonna start with just skip the white spaces. Skip white spaces. And that's gonna be a function. Okay, I'm gonna type a little bit slower because then I'm doing fewer mistakes. This is gonna skip all the white spaces, and we need one more function which will advance the lecture pointer. So as you know, we have a cursor which is pointing to the right place in the file, and this function here is going to move that pointer. And if we encounter a new line or something, we're going to increment the column and line. So this is going to handle all that. So that the line and column will be changed because this function here is going to handle it. Why static? Static is a keyword which means that you can only use this inside this file. So if I would try to call this skip whitespace from a different translation unit, that would fail. I think if you don't write static, I don't think it works either. I think you have to define it somewhere else. I don't know. It's it limits the scope of the function where you can call it. It is not outside the file, isn't it? Okay, so advanced Lexer. If you don't write static, it extern by default. Oh, it is. Oh, that's weird. Like, I've just, if I only need a function inside a file, I'm gonna write it as static. But there are so many functions you only need inside a file. So in my language, I would probably avoid having the static keyword. And instead, if you want to expose something to the outside world, to a different file, you have to declare it as public or extern or whatever. We're gonna find a cool keyword for it. Yeah, let's get the current char. So that will be Lexer cursor of 0. And if the this character is 0, we're just gonna return, because you're not gonna advance the pointer if it's already 0, because this is not the only place which is gonna advance the pointer. So we might delete this, but it's nice to have just to be sure. And also, if you have some text here, and you have a new line, you might also have a an R before it. So if we only have an R, we're gonna count that as a new line. So basically, if it is an R, we're going to count it as a new line, we're going to get the next character. Okay, so the current character is not, it's not a 0, so it might still be the R character. So you're going to check if C is equal to, we're going to advance the Lexer first. So Lexer cursor ++. And then we're going to check if C is equal to \R. So if it was here, and the next one is equal to new line, yes. So if the next one is equal to new line, then you're going to skip past that as well. And this is implicitly checking that there's not 0, because it can't be both 0 and new line at the same time. So we're just increasing the pointer. And then we're setting this to be new line anyway. Okay, so basically what's happening is that if we're having an R, we're expecting an N. And if we're getting an N, we're going to skip past that as well. If we're not getting an N, we're going to count that character as an N. Yes. Yes. So here, we're going to check if C is equal to a \n, this is a new line. So note that if C is equal to n, the cursor is already at the next position. So we can just say Lexer, this is going to be line ++, Lexer column equal to 0. Otherwise, you will be doing Lexer column plus plus. Does that make sense? I think so. It is not used outside. I think that's a good approach. Okay, nice. It's a much better system. Yes, I totally agree. Grid scoping using private and public, not static. Yeah, but I like static doesn't tell you anything, so I agree that the public keyword is better. So an overloader where you can see yet, it's ridiculous. It is. Okay. So I think this should work. This is gonna increase this pointer. And yes, we can just do this. We're gonna have a helper function for getting, for checking if something is a white space. So we can say like if is white space, and it takes in a char. And we're gonna return if char is equal to new line, or c is equal to return, and c is equal to tab, or c is equal to space. So like all these characters we're not interested in, we're just gonna skip it. So the skip white spaces is gonna do while the current token, so while cursor of 0. Wait a second, let's call this function is white space. So is white space cursor of 0, then you're just gonna advance the elixir one step. Holy crap, it's snowing. Dang it. Alright. Yeah, it's snowing as fuck. Oh, my poor bicycle. Oh, I should probably bring it in because it's gonna rust. Alright, so this is gonna skip the white spaces. We're skipping the white spaces first. And then we're gonna check if, because this is never gonna skip if we have 0. So if we can save the current character. Yeah, let's save the current character. So if c is equal to 0, then we set that the token kind is equal to token end of file. So basically, if you're at the end of file, you're just gonna say it here. That's good, and you probably should return here because you don't wanna parse anything else. Skip white spaces. And if I run it now, we can just check if it's working. Skip white spaces, too few arguments. And that requires elixir. Bring it in quickly. I probably should. Has incomplete token. Wait a second, is that, you can't do that, can you? Yes, because the C compiler doesn't know that. And this is partly why I wanted to make my own language, because I'm freaking tired of doing this. It is so unnecessary. And wow, it compiles. And we have a segmentation fault because of something. Let's see if it does it do this? Check. So process next token is not working. Token kind. If c is equal to 0, return. and you say that the token kind is end of file. So if this is happening, I should probably make it like do a debug around this. So this is not happening, that's fine. So to skip white spaces, we have to know that this is working. This is working. So while is white space, this is just going to continue to advance. So we probably should have and Lexer cursor of 0. All right. And we can, all right, so what is happening here? If c is equal to 0, return. So the thing is that we can't increment this further. I hate segfaults. It is starting. So the first time it does this, it's failing. So what I might be thinking is that let's try to print the text here. Lexer file size, Lexer Lexer file text. So it's starting and it has a segfault there. So the file I'm giving it is not right. The Lexer file isn't right. File and file name. Let's go in here to the new Lexer. Because I'm not returning that object, fuck. Return the Lexer. Why the hell wasn't GCC giving me a warning on that? It doesn't give me a warning. It's done. So we have an error 1. That's fine. That's exactly what we want. But I don't know why GCC didn't warn me on that. Because that's kind of stupid. And the file. Okay, so basically what's happening now is that it's it is skipping the white spaces. We can also print the character we're currently at. So char, that's a char printed C. So you can see that the char is 2. And if that's the first character. So if I have like many tabs and spaces and whatever, it is gonna skip all those successfully because the first character is still 2. So what we have to do now, we have to parse this number. Rewriting the rest. I'm gonna actually rewrite in this language here. I think that's gonna be cool. That's why I'm making an x86 backend. Have you set GCC to give you all the warnings? Oh no, I haven't. Thank you very much. I actually knew I had to set the warning all flag. But I think I just forgot it. There we go. So many warnings. Reaches end of non-void function. I'm actually going to disable this specific warning here. So you can say, please don't warn me on no return type. That didn't work. Oh, probably like this. And there we go, perfect. So I don't want to be warned against non-return type. You can actually specify what GCC should warn you about, which is kind of cool. So we can just have it like this. We're gonna parse the numbers. That should be simple. It was a typo, yeah. Okay. So basically here, so at this point, we're gonna be getting characters from the file. That is not gonna be a white space, it's gonna be real characters, removing the white spaces from them. And we have to, at this point, determine if this is a number, if this is a string, like what is this? So what we're gonna do, we're gonna check if this character is a number. We're gonna parse a number. We're gonna parse the entire number. If that character is an identifier, we're gonna parse the entire name until that name has some other character than a valid letter. And the same way with comments and all these like things that you know. And if none of these applies, we're gonna parse the punctuation. So we're gonna do that to in the last, because we can't really, we don't want to check. If I want to check if this is a number, I can just check if this first number is between two values, and that's gonna tell me if that's a number. If I want to check if this is a punctuation, I need to check like 30 different things, so it's very inefficient. That's why I'm placing that the last. This is gonna be I'm gonna do an if, because we might want to check multiple things. So for example, comments, we need to check both that the first character is this and the second character is this. So that's not really done with switch. So that's why I'm using if here. So we need to check if C is a number. It's actually gonna go like, I'm actually not that bad at writing. It's gonna go, it's working. So if this is a number, we're gonna check if, let's do 0 first. 0 is less or equal to C, and C is less than equal to 9. That's a number. And if this is a hexadecimal, we're gonna parse all like everything. So hexadecimal is gonna work, binary is gonna work. So it doesn't matter what you write. And I also want to support like the limiter. Why the hell doesn't C allow something like this? It should, or possibly this. This is probably better. In Norway, we write like, this is a floating point number, and this is used for just delimiting. But I know that in different languages and different countries, this is not the same in all the countries. So we might just support this. This is telling if it's a number. So if this is a number, we're gonna do that. And else, so here we parse the punctuation. Lexer. So we need two functions. We're gonna need parse punctuation, and that takes in a lexer and a token. Thank you for following. Welcome to the stream. I hope I'm not missing anything because my sound is not working. So the sound keeps going out. Wool extra, everything, yep. I think we don't need all the warnings. We're gonna parse a punctuation. We're gonna be parsing a number. Oh, I'm actually so fast. Yeah, parse number. I'm gonna give it a token here so we know where to write the stuff. Number. All right. The punctuation, it doesn't matter if we're not implementing these. They're still going to just be token none if we're not doing anything. So it's still working. Error 1. So I want to parse a number from this. So the lecture is pointing to the first number. So I probably will have a function for getting the next character. So char, get next char. Like this. And the reason we have it like this is because the x... No. We will, like, we're gonna need something like this, but we only want to check the x and b manually. So I want to support like something like this and something like this, and chars. Probably chars is gonna be 0c. I don't know. That's probably stupid. But we want to recognize these numbers here, and the only thing which is different from, let's have the decimal as well, is the base. So this has base 16, this has base 2, and base 10. So the only thing we want to store from that is the base number. So you're going to assume 10, which is the decimal number system. And if lexer yeah, I want to skip a number. Firstly, we want to get a number. So I'm gonna say get we can say get next number, because I want to convert the Elixir cursor of 0 to a number. And if this is equal to 0, we can actually just check that. If that is equal to 0, can you write in C, like, can a number in C start with 0? I'm gonna check that. Return okay, that worked. Yeah, I don't see why it shouldn't work. So we're gonna check the next one as well. So if cursor of 1, which is the next character, and note that we don't check for 0 because we know if this is actually valid. We know that the current location is valid if this is the character 0, and yeah, so we don't need to check for the 0 character. If that is x, we have a hexadecimal number. Else if lexer cursor 1 is equal to b, then we have a binary number. And in both of these cases, we're going to advance Elixir 2 times. The autocomplete is wrong now. Because we need to skip. We don't need to do that, because if this is happening, we know the base is going to change. So if base is not equal to 10, we just advance 2 times. So here, base is going to be 16, and base is going to be 2 there. Starting with C, means octal. Does it? Exit status. Yeah, you're right. You're absolutely right. I didn't know that. That's cool. Okay. So I would suspect to have 2, 3, 4, but I'm getting 1, 5, 6, which is lower. So it makes sense to have an octet. If this should be okay, that was like O or something. O for octets. We can add support for that. It's really simple. Lexer cursor. It's still the same. It probably doesn't matter. Base is equal to 8. If okay, we can do a check here. So if okay, what do you think? Should we allow zeros before it? Because in C it's octal. So if it might make some, it might introduce some troubles there. So I think I'm just gonna disallow it. So I'm gonna give error status 1. Yeah. So if base is 10, because I'm expecting that the base is different here. It's gonna be like this. So basically, if I'm writing a number like this, is gonna be an error. A number can start with 0. Yeah, I think it should have an O prefix for octal. I think that's a nice feature. Octal digits. And we need to check the range of these numbers as well. Anyway, so I want to have a number. This is going to be storing the number. And we're going to start at 0. Okay, so I'm gonna take the example with binary because this is really simple. It took a while before I understood it on stream. But anyway, we're gonna parse this number this direction, so that from left to right. So the first we're gonna say is we're gonna have 2. That's the first number. So number is gonna be equal to 2. And then we're gonna say number, I'm gonna say like x is equal to 2. And then you say that x is equal to x, which is 2, times 10, plus the next number, which is 3. So this is 23. And you can probably see where this goes here. So x is equal to x, which was 23, times 10, plus 4, which is 234. So this way we can parse it from left to right, which is really cool. So we're gonna just have a while loop, and we say number is equal to number times 10 plus, and we want to convert the number. We want to have a function for getting the number from the char. So I'm gonna say char to number, and that can have like a u. I can have a u8, I don't care. And we're also gonna take in the base here, that's important. We can probably just check that later. Char to number. I'm gonna make this a signed 8-bit number. So if this fails, if this isn't a number, I'm gonna return char to number. I'm gonna return false. So the thing here is that I want to support hexadecimal numbers, where like the characters A through F should be valid numbers. So we can't really, I'm gonna make a table for that. Luxury language can break backward compatibility with C ciphers. That's right. I don't really care about backwards compatibility. You're not gonna be able to write any C code with this language. Not probably LinkedIn as well, because I don't see the point in doing that. Maybe, I don't know. Poggers, what does poggers mean? I don't know what poggers mean. I've heard it multiple times before. I probably was explained it once. Numbers times base. Yes, you're absolutely right. Thank you very much. Yes, you're right. So I'm gonna make a tiny lookup table. I'm gonna say number table. And this is gonna have, I'm just gonna do it like this. Let me see. I'm gonna copy. No, that's for printing numbers. That is for printing numbers. We want to get a numbers. Okay, I understand. Let's just do it like this. So if we first track the numbers between 0 and 9. So if is less than 9. If this is between 0 and 9, you return C minus 0. And that's going to take care of the numbers. Yes. Additionally, we want to, so like, it shouldn't matter for a user if it has, like, where is the ASCII table? There is like a cool way of doing this. ASCII table. Like, where's the big numbers and where's the small numbers? Because if you're setting bit number 5, you're basically converting between a big number, a big letter, and a small letter. So if we, for example, take, let's say 65, 97. So that's 32 between. So 32, that's 2 in the power of 5. So by setting bit number 5, we're going to convert from uppercase to lowercase. Or in case of lowercase, it's going to just convert to lowercase again. So what we want to do here, we want to say C or equal bit number 5. So this probably requires an explanation. Convert the number, convert from uppercase to lowercase. And then we're going to check if, we're going to assert that C is between lowercase a and, this is hard to write, and F. And note I'm checking the lowercase because I've converted this to lowercase. That's important. So if that's the case, I'm going to return C minus A. Yeah. Otherwise, return -1. Chronoluminary, subscribe. Thank you very much. Thank you so much. That's very nice of you. Welcome to the stream. You've been following for quite a while. I remember seeing your name all the time. Thank you very much. It's incredibly important if you want a useful language. Probably, I never had a use for it because I'm always writing things from scratch. So I don't use libraries for anything, literally. But maybe, I don't know. Maybe we're gonna add it. Yeah, we can subtract 0 from char. This looks cool. What kind of compiler is it? This is just for a new language I want to make. I like C, but I want to have a few different features, like just fix some things. I don't want to have declarations. I want to ignore header files, bit operations in C, which I'm very interested in because I'm working with embedded systems. So, like I probably have it somewhere. Let me see. There was some crazy. I did a Nick driver. I don't know if that's the crazy one, but like you're doing a lot of these things here, like bit operations, and this was a bad example, but often like I want this to be much better. I don't want to do bitwise operations at all. I want to be able to do like I have a register and I want bit number 5 down to 2, for example. This should be valid. This should return. This should do the things I want without me having to do it manually, because that's annoying. So like just a few changes like that. Bit set in C++ for bitwise operator. Maybe. I know also someone is doing like a separate function for it instead of these operators. But I think like these are nice operators. I don't know. So I have a number equals 0 and plus, and then we're gonna get a number here. So let's say like temp is equal to chart the number. Advanced Lexer. I'm gonna use this should probably return the character. So I'm just returning C there. And I don't do this anymore. I have a little different coding style now. Yes, so I need a number here. Advancing Lexer. I can probably just say this. Lexer cursor of 0. And that will be changed here in this case. Chart the number. And if temp is equal to -1, exit. We're gonna have real error codes very soon. Plus temp. This is supposed to be a signed 8-bit integer. So at the very end here, we should have a number. I'm also gonna do one more thing. I'm not only gonna save the number, I'm gonna save the reference inside this file. So, so the token name text should be equal to Lexer cursor. So I'm basically saving where this starts, and then I have to save the number and I have to say the size of this reference. So the name size is equal to, what's biggest? I think it's Lexer cursor minus token name text. So this is gonna get the difference. So if I want to print this number, I can, yeah, that should be doable. This is not gonna return any error code. Like, this is gonna parse a number. If that's not the number, it's gonna generate an error from within this function here. Yeah, so now we should get the first number. Got a token. Let's see if that works. I'm using the wrong thing here. Like, I was thinking, why should you use I here? It's much easier to understand when using unsigned and signed. The only drawback by using S here is that when you're gonna print, you can't use %s because that's a string. So that's the only drawback I can think of. Char2, it is hanging, and I know why it's hanging. It's because I'm not advancing the Lexer pointer within here. This is really ugly. I'm gonna fix this later. Error 1. One more thing. This is a number, so we should change the type to a token number. What the hell? This is 2. Parse a number. Okay, let's have different error codes here. This is never supposed to happen, so that's why I'm not giving it that much thought. Char to number, that's returning a -1. Am I having some weird characters? I'm having this. It's error 2. If temp is -1, it means the number has ended. That's right. Can make an interface that works like in C. What kind of interface are you talking about? Yes. It means that the number has ended. So this is not right. This is gonna break. Yes, that's right. So we got the token and it gives us the number, which is fine. We can also go in the main and just see if okay, so we're printing the number as well. And you can see that works. So basically the printing number is representing this exactly. So we can see how it goes with and if it's the end of the file, I'm gonna just print it. So we're getting 2 tokens there. And token, that's in a long decimal. So I'm having L here as well. All right, so we're getting char 2. Let's make some more things in here. Let's have let's have a random number. Let's have some binary numbers. And let's have some octal numbers. Like octal, that's up to 8. We need to check if that's valid as well. So basically we're getting this one, which is this number here. The octal is converted to 156. Wait a second here. Wait a second. Didn't I have the... Okay, so let's try 2, 3, 4. Okay, let's try 234. Oh, I was using 234. So GCC says that that's going to be 156, which we're getting here. That's working. That's nice. It doesn't seem like you check allocation or return value. No, I don't. I'm gonna do it on the other return things, on the other allocation things, but not on this. We could check it though. Yeah, we probably should check it here. If not, file exit 1. All right, I want to do one more thing because it's a little issue here. Okay, this can be in, that's a number. We can do this a little bit more clean. So I want to say, we can still use the temp thing. And then we just do I'm gonna have it like this. What is the? We have to check if the number is bigger than the base as well. So if that's -1, well, if this is -1, it should break, and if the temp is bigger than the base, yeah, bigger than the base, we should exit. So exit code 5, for example. So basically, if I'm writing something octal and I'm giving it a 9 here, it should give us error 5, because if you're writing this, it should be an error, because otherwise the compiler would just interpret it as this, like 2 numbers, and you don't want that. That's probably going to be catched by the parser, but I think that's great. So now we have numbers. Are we getting all 2 1s there, 2 1s there? Perfect. Let's quickly implement these punctuation characters. So that's the next function. We can delete the file. We delete that one. Yeah, perfect. So else parse punctuation. So we're gonna assume that there is some kind of punctuation character here. And yeah. So let's do a switch on the lexer cursor of 0. So you're gonna check what this is. I don't know what we had here. We had plus, minus, and all these equal things, and a semicolon as well. Yes, so if it's a plus, you probably want to check if the next one is not a plus. But I'm not gonna check it here. So how this works is that we're gonna check the first character here, and then I would check, for example, the next character. If the next character is also a plus, that will be an increment, like plus plus. And you can probably have plus equal here as well. That's gonna be like plus a sign. Yeah, plus a sign. But for now, we're gonna just ignore it. But anyway, we want to have a function which can handle that. I'm gonna say skip punctuation. And this is gonna take an elixir, and it's gonna take in how many characters to skip. And it's gonna take in the token kind. Skip punctuation. So we can advance elixir, but this will always work. Yeah, this will always work. So I'm just gonna increase the elixir pointer with a skip count, because we have checked that this is actually non-zero. Skip count. We're gonna take in the token as well. Skip punctuation. I'm gonna take in the token as well. And we're gonna set the token kind to the kind here. There we go, big skip punctuation. So basically what we can do here, if I have just a normal plus, and if the... Now let's say the next character. Yeah. So let's say C is equal to, I'm gonna say like next. If next is equal to plus as well, then we can just call skip punctuation with the elixir. Skip count is now going to be 2, so it's going to skip with 1, 2. And the token is here, and the kind is going to be a token like some plus here. It's going to be plus plus. So it's one simple function for setting everything. And we just do a break here. But for now, we're just gonna assume we have 1 plus. So that's token plus, and the size is 1. Oh, wrong window. They are so chill. Thank you very much. Thank you for hanging out here. Yes, okay. So that's a plus. Let's handle the minus case as well. Minus times and division. And we had one more, and that was the semicolon. We actually have the assign as well. So if it's equal and less and greater. This is the last one. Okay. So if it's minus, we're gonna just change this to minus. Multiplication. Division. And here we have to track, because this is an assign token. Yeah. So we're gonna just check the next one as well. So if next equals equal, so if it's equal, then you're gonna do skip token, and this is equal. And you're gonna skip 2 of them because you have 2 equal signs. And you just break here. So this is basically updating the token. If I would now have equal, then this will not happen, and the token kind will still be token none. So that will fail. So that's fine. This can mean many things. So you're gonna check the equal sign first. This can also be like less than, which is bit shift. So that's equal. Then we're gonna skip two of them, and this is less than equal. So less equal. Else it is less. And for this, I'm just going to copy this entire thing. And greater equal greater. All right, so that's what we need for now. I think that's going to work. Yeah, it seems to work. We're gonna write the program which is using a little bit more minus dada plus something equals. I'm always writing the same number. Like something like this. And we should add a semicolon at the very end. So I'm going to add a semicolon token as well, which I have here. So I'm only going to go down here and say case semicolon. Yeah, we're not going to do anything else here. So I'm going to skip the punctuation, one character, and we're going to have semicolon. So if I now test this, got the number, I'm gonna rename this a little bit. So got the number, else if token kind equal to token yeah, I'm gonna do else there. In fact, I'm gonna do else because I should probably have a tag or something which is saying that this is a punctuation character. So I'm gonna just say token there. And yes, that is working. Okay, so I'm getting all the numbers, but I'm not getting anything else. Or I'm getting it here as well. So I don't understand why. Wait a second here. 234, 234. This number, where is this number coming from? Oh, that's probably the number representation of this. Yes, it's doing both. That's weird. That's weird. If token kind is equal to number, you do this. Is actually this happening? It seems that it's printing both of these. That's very weird. Have I done something wrong? C is destroying my stream. That's so sad. First punctuation. It should say this is gonna update the token there. So as long as this is getting the right token, it should work. And I'm getting the token in there. No. Can you get in there? Else. I'm gonna check if this is actually happening. It is getting punctuation. Oh, somehow, like I'm not updating. Okay, I know what's wrong. I'm not updating the... All right, okay, that's cool. So what we need to do here, we're gonna say that the token name text is equal to the current, oops, it's equal to the cursor location. So basically the punctuation starts at the right place, and the token name size, that is equal to the skip count. So let's just have this up here, and then we skip a number of letters. So that was the mistake. I was using the old, that was why it was the same character. So even though the file looks like this, we're getting, is this a little bit too big? We're getting number plus number minus number equal, and this is gonna give us the token here. Like we're gonna get the, like this is gonna represent a number. So we can just ask for, is this their number? Then we know we have an equal. And we have the end token. So this is working. We don't need anything more for this testing phase. Yes, that's good. That's very good. Let's implement the token cache like real quick. So next token and peak token. They're gonna do pretty much the same thing. This is very simple. This is just return peak token lexer1. So just peak one ahead. And we probably need to know the this as well. So current and peak token is just using this peak token function. And that's going to peak a number of tokens ahead. We're going to define this as well. So this is already the API. Where is my draw diagram? All right, so I want to, whoa, that scared me. Decompilator. It seems like your name is something to do with compilers. Thank you for the follow, by the way. Yeah, we're just gonna like, this is a token. Doesn't seem like a token, but it is. I'm making it big. So this is the current, thank you for following, welcome to the stream. This is the current one, and yeah, so now we can peak like 3 tokens ahead and go back 3 tokens back. And we're gonna have a buffer, which is, yeah, which is just whatever's between current and buffer, like the buffer. I'm not sure what I'm gonna call this, but whatever's between this one and this one is the peak tokens, and whatever's between this one and this one again. So these 3 are things we have parsed, and we can go back to see what those are. And you kind of have to store if these are valid, because you need to know if something is valid. Because the thing is that if you're here, like this is a token, right? Like maybe main or like a punctuation or something. If you do peak 3 tokens or peak 2 tokens, so you want to peak this one, right? It is very unwise to, or I guess you can do it, but what I'm gonna do, I'm gonna basically lex both of these tokens here, and I'm gonna mark them as green. I'm gonna take a different color here. I'm gonna mark both as green, so they're valid. And I'm gonna return this token here. So when I'm later doing next token, I can just check the cache here. And if that's green, so if it's valid, I'm just gonna return it. And also I have to then move this pointer up here. So this will be the index. This will always point here. And do we need to track anything more? Do we need to track the buffer? The buffer is always gonna be, yeah, the buffer is always gonna be a few steps behind it. So let's make the buffer here instead. It's a little bit easier. So if I move this pointer away here, I have to invalidate this one. I have to make sure that this is not valid. That's basically the buffer. The buffer is just one token which is not valid. So that if I have, I probably don't need it. As long as yes, I have to use this because I have to invalidate these previous tokens. If this wasn't there and I move the pointer over here and I want to peak, let's say 3 tokens, I'm gonna go back here and this is still valid. So I don't know if this is a new valid one or a previous valid one. So I have to make a buffer between them, which is a non-valid one. So I know where to stop. My name means C compiler. That's cool. You probably know all this stuff. Decompilador. Decompilador. I don't know how to speak Spanish. I had German at school. Exactly, C compiler. Called CD Sienda. That's cool. This is gonna be a legit compiler for this is gonna be a legit compiler. Yeah, for sure. I'm gonna also make an interpreter for compile time execution. Alright, so with keeping this in mind, we're gonna try to implement something like this. It shouldn't be that difficult. So we have a list of tokens, and this buffer size is the peak count and the undo count added together, and you plus 2 because of the buffer and the current one. A new lecture. So this is tokens, because we need to save it. This is valid. So we can make a bit in here, but that's gonna just increase the size of all the tokens. I'm not gonna do that. Let's make a. Can I make an anonymous structure? I've never done that before. Yeah, let's do tokens. I was using my old syntax here. How do you do this in C? Structure tokens, and then you say the token buffer size, and then you can write in here what you want. So each of these entries is going to contain the token and a valid bit, so is valid. So not this one. So I can say like tokens of 4 token, and I can say tokens of 4 is valid. Das ist gut. Sehr gut. Yeah. We need to fix the initialization function. So that's, I guess false is just 0. So we can just make sure it's right. What did I call it? Token. What did I call it? Oh, buffer size. So for each buffer, you do tokens of I, and this has an is valid, and we're gonna say false. And token, we didn't do anything about the token. We just say that is valid but is false. This is implicit since we're using calloc. And I think this is valid to 0. So I don't really need to do this. But it's nice to have. Maybe I'm switching out this. It's nice to have. So the next token, this is basically gonna move the pointer. So we have to get the next index. We're gonna get the next index or increment. I don't think I need a function for that. Increment index, because I want to check if that's bigger than this. Yeah, why not? I'm gonna say increment index. This is gonna take in a U32 pointer index. And it's gonna increment it once. Or we can increment with a count. Or I'm just gonna do it manually here. So if I'm gonna save it. Let's just save the index. So this is Lexer index. If ++ index is equal to the buffer size, we need to set the index to 0 because it's gonna wrap around. And now we need to check if this is valid. So if yeah, I'm going to check if this is valid. So if tokens is valid, so if this bit is valid, we're going to return this one, right? And in any case, when we're moving this pointer, like this is going to move anyway. So we have to make sure that if I'm going to move this one over here, I have to move this buffer over here. Basically, I have to invalidate this token. So my jump distance, or this distance here is 10 in my case. So that will be, this is the current location, and I want to subtract with 1, 2, which means the number of peak tokens plus 1. I want to subtract the original index. No. That's let's have one in buffer. So I want to move this over here. Then I have to invalidate this one, right? So I have to decrement this with a number of buffer tokens. That makes sense. Invalidate the buffer token. This is the buffer between the tokens ahead of time and previous. So I need to decrement the Lexer index, which is the original Lexer index, with, let's just save that index here. So I'm gonna do this. So this is the index we want to save. So I want to do index minus equal this token buffer size. But this might be negative. So you might check that as well. So if index no, not buffer size, but undo count, which means that if that's less than undo count, I need to do index we can just do index plus equal token buffer size. Okay, I'm a little bit lost here. You're incrementing it with a buffer size. So this is basically setting index really high, and then this is going to be the same in any case. So this will get the buffer token. I don't know if this is the best way of writing it. I think it's a little bit too much. That's fine. So we say the token cache of this new index is valid is equal to false. Thank you very much for following. Welcome to the stream. Yeah. So this is invalidating this past token. So all we need to care about here is lexing a new token if it's not valid. So if it's valid, we're just gonna return it. So what we can say here, we can say if is valid is false, we need to lex a new one. And then at the very end, this will always work. We just return tokens of, this is not the index. This is the previous index. I'm gonna do Lexer indexer. That should be more right. So this index is just saved, that's the previous one. Yep. So if that's false, you need to call this main function process next token. The Lexer is still the same, and the token is the address of. Alright, let's just get the token we want to return. Token is equal to the address of Lexer tokens index. And then we can say if, this is much better, if token, dang it, we need to check this one still. Is valid is equal to false, you're gonna process this token here. And you return this as well. Something like this. So this is invalidate the buffer token. This is processing a new one. Yeah, and this makes sure that wait a second here. If I undo, like if this is the case and I'm undoing the thing I was doing here, then I'm basically moving the current pointer back here. So I don't know, like, I think I have to store the index of this buffer. I think I have to do that. Because I need to know when that is happening. Yeah, we're gonna do that. Two seconds. Thank you for following. Welcome to the stream. Atrionyx. Yes. So I'm gonna, let's call it current index and buffer index. Why not use flex? Because flex is so bad. I've tried to, we use it at school. It's so hard to understand. It's like double X's all everywhere, and like the previous lecture I was doing was 500 lines of code, and it lexes. How fast was it again? 100,000 lines in 5 milliseconds. So 1 million lines would be 50 milliseconds. Like it's 50 milliseconds for 1 million lines of code. It is so fast that you don't need more speed. Yeah, I did start now on this stream. That's the only thing. Anyway, so this is going to contain all the things we need. So I need to change this a little bit. So we need to compute the difference between, we might change this later. We need to compute the difference between current and the buffer. If this difference here is bigger, yes. So if this difference here, and this doesn't need to do anything. This is just an index. If this difference is bigger than the number of undo tokens, which is, this case is 2, I need to move this one. And this is only going to move one step at a time for now. So I need to compute the difference between current and buffer. So if this is bigger than this, I can do I need to compute the difference in the number of tokens. Because this minus this is 3. And I want minus 1. So if this is bigger than this, all right, if this is smaller, something like this, then the difference would be 1, 2, 3. So I'm going to move this all the way up here, and that's 1, 2, 3. So that should be simple. We're going to get the difference between get undo distance. This is going to take in, this can just take in a lexer, I don't care. And if Lexer current index is bigger than Lexer buffer index, let's say if that's bigger or equal. This is not supposed to be equal. That's never gonna happen. So I'm gonna say if that's bigger, then I'm gonna return Lexer current index minus Lexer minus 1. That's the difference. Else return buffer size plus Lexer current index, and then you minus let's do this just to make sure nothing bad is happening. So increment the entire thing first. Lexer Alright, so this is going to get the distance in number of white tokens. So this number there. So I'm only really interested in the difference here. So I don't need to store the index. I'm just going to increment the actual index, and then we're going to compute. So if get undo distance of this Lexer, if that is equal to undo count, I'm going to say bigger. We can actually do that before. Oops. So if this is equal to the undo count, I'm gonna increase this index, so I also need to increase the previous index. And I'm gonna make a function for incrementing an index with a number of tokens. I'm gonna just do one here. Index is equal to index plus 1. I can probably just say plus equal 1. And if index is equal to token buffer size, we set index back to 0 again. And I'm using a star because I'm actually modifying the memory here. So what I can say, I can just say if the undo distance is equal to the undo count, which is a maximum undo distance, I'm gonna increment index, and I want to increment the Lexer buffer index. And first I have to invalidate it. I'm gonna say tokens buffer index equal false. And that's just because I'm gonna ignore this. If I have a case like this, and I'm moving the buffer index one step, I need to invalidate this one. Because if this is true, and I do a peak of 3 here, it believes that this is valid. So this is going to continue to shift around, so we need to invalidate this one explicitly. That's very important, otherwise this is not going to work. increment index, and then we're incrementing the current index one time. So now we have a new token. So this is right. I believe this is going to work. Oops. How long were the lines of code? Like how many lines I have? I can probably... That's a good question. Let me see. There is a command for that. Let's see what it is. Clock. No 3. By file. And I want to have these source files. So do something like this. Oh, dang it. There we go. It's not so much. 200 lines is nothing. Yeah. That's the next token, and peak token will be very similar. Yeah, peak token will be very similar. Oh, yeah. No, I tested with the previous implementation was a little bit bigger, and I tested it on a file, FAT32 file of system implementation in C, and it was tokenizing 100,000 lines of code in 5 milliseconds. So I'm just assuming that, like, you know, 5 times 10 equals 50, and 100,000 times 10 equals 1 million. I'm just assuming that. But I tested with, what did I say? Like 100,000 lines in 5 milliseconds, so probably 6 or something. 5-6 milliseconds, 5 point something. Are you kind of implementing an iterator? Not exactly. Can we do this with linked lists? No, then we need to have that. Then we need to make the token bigger. No, this is like a ring buffer where I want to like buffer in both directions. So I need to keep track of like a buffer distance between. Like this is the case I specifically want to implement. So this is the case. So I want to be able to, if I'm currently here, I want to be able to do undo, and that's gonna bring me back here. And if I do undo again, it's gonna bring me back here. If I do undo again, it's not gonna work because I can't store all the tokens. I have to use some kind of limit. And then a ring buffer is a very nice implementation of that, I think. Yes. So a peak token is very simple because you know that as long as the current location won't change. So as long as like you can always peak a number of tokens in the future, always. Sometimes you can even peak more. But the logic for handling that is going to be a little bit more, so I'm going to ignore that. But sometimes if you have done an undo, you can peak a little bit more because the buffer is big enough. But for now, I'm just going to say if count, I'm going to say bigger or equal to token peak count. It's going to be strictly bigger. Then we exit, in fact, because we can't really we're not gonna, this is an issue in the compiler. So I can't go, like, I'm calling this like hundreds of times. I can't check it all the time. Yeah, so we're checking that this is in range. And the only thing don't have to do anything about the previous one. This is really simple. We just have to iterate. Yeah. So let's go from I is equal to 0, or yeah, to this count. And then we're gonna have an index here. We're gonna save the index as well. So this is the Elixir current index. And for each time, yeah, this is the count we're gonna peak. So for each time here, we're gonna increment it first. Because if I is equal to 0, this is gonna happen 0 times. So I need to increment this first. We can call just increment index. And we're gonna check if that is not valid. Yes, so we're gonna basically do this. In fact, this is gonna be indexed though. All right, so if this new index, we're basically checking like this one and this one all the way to the p count. So if I'm getting, thank you for following, welcome to the stream. If the count is like, say, 1, I'm gonna increment this 1 time and I'm gonna check if this is valid. If this is not valid, I'm gonna cache it. So I'm gonna process the next token and place it in here. So I know that wherever index is pointing, that is valid. And if index is 0, it should point to the current one, which is also always valid. Yeah, and we just return. And this will, of course, fail if we don't get the first one. But we're gonna make sure to do that. Index. Yes, we don't need to do anything more. Current index, you increment this number, you check if that's not valid, and you process it if it's not valid, and then you have to, oops. You have to check that this valid is true now. The same thing here. If it is not valid, we're going to set it to valid because we're caching it. Let's do this as well. And the index is pointing to the right place, so if the count is 0, then this is not going to happen. Index is equal to the current index, and you're just returning the current one. And yeah, so this is just peak. This is caching all the intermediate tokens between where you are and where you're going to peak. And this is also handling that, so you can see if the next one is false, you're going to cache it. So if you have called peak like 10 tokens or something, this is not going to happen for these 10 tokens. Yes, all right. And then we have peak next, eat token, expect, and skip. They're using the same. They're using the same. Is that everything? Really? Let's try. Next token. And we should probably initialize these indexes because they are equal now, which is a little bit stupid. So they cannot be equal. Well, okay. Oh, we have to implement undo token. Undo. I'm gonna say undo next token. So we have to implement this as well. I'm gonna specify the indexes here. So the current index is 1, and the Lexer buffer index is 0. So there is space between them. So this is, yeah, the undo token won't work here. So this is the final function we're going to implement, and then we can start parsing. That's going to be fun. Is he using Windows? Yeah, I'm using Windows because Linux. Oh, I had a nightmare a few weeks ago. It was a total nightmare. I was out of RAM. No, not the RAM. Storage, flash. I was out of flash on my Linux partition, and it is completely impossible to add more or allocate more memory. I'm sure there is a way of doing it, but I just had to erase this entire thing. Erase Linux and install it again. So luckily I'm not doing any network stuff because then I would need Linux. So I'm gonna be using Windows until I absolutely need Linux. Besides, the microphone thing is crap on Linux. So people is complaining about low microphone sound on stream, and that's sad. Yeah, okay, let's implement this last function. Undo next token. So that's supposed to be simple. Yes, that's supposed to be really simple. You're just gonna check if you're checking if the get distance is bigger than 1. Yeah, you're checking if the get distance is bigger than 1. Get undo distance. If get undo distance for this Lexer is bigger than 0, so 1 or more, then this is gonna work. Otherwise, error 21. So get undo distance. This is really simple because you're only gonna decrement the current index. So minus minus. Which means if current index is something, minus equal 1, else current index is equal to, so what is the biggest one? That's a buffer size. So if the buffer was 1, the index would be 0. So I'm gonna say this minus 1. So this is just decrementing the index, and this are valid. So we're gonna assert that this is valid because we have been processing it before. So let me just include no mistakes here. There we go. Assert Lexer tokens index is equal to true. We're gonna just assert that and return the same thing. Gonna return the address of token. So hopefully this will work. I'm saying it's very nice looking code, so I probably will clean it up. It doesn't matter. Yeah, let's hope it works. Yeah, perfect. Lexer index. We don't have an element called index. We have current index. Because you're incrementing current index, this is supposed to be current. Yeah. It seems to 227. There we go. $233. Yeah, I guess it's here. Token. Okay. It is in fact compiling, and we don't have anything here. So let's just write it like this. And now we're gonna try to do something which doesn't work. We're gonna say undo next token. And this is returning a new token. We're gonna get error 21. That's perfect. And we don't want unused variables. Jesus, why the hell does it add all these warnings? I'm using unused, I'm using warning all. That's why. I think that's the best way. You just say warning all and just mark the warnings you don't want to have. So error 21, that's perfect because you can't undo a token if you have already gotten it. We're gonna make a print function as well, so just print a token. Oh my god, that's so fast! I'm like Superman on the keyboard. Oh my god. So let's do token. So print the token, and we're gonna print a new token here. Probably we should just return 0. Error 21. Okay, undo token. Let's try to get the first one. So get next token. That's gonna give us 234. Wait a second here. Only 4 errors, yeah. That was probably up here. Which, in other words, mean that I've been looking at chat for like at least like 4 minutes. And I didn't see. Broadcast gonna be stored. I'm probably gonna store it somewhere. Maybe on, yeah, I don't know. Let's Windows. Yeah, it's a VSL. It's a Windows terminal, which is looking really good. It's really slow though, but it's looking good. What was I gonna do? Yeah, that's the problem. So when I do next token, what is really happening? Because when I call this, the buffer will be at 0, and this will be the current index. So get undo distance. This isn't right, is it? I don't think that's right. I think it's still -1 here. Because that's the under distance. Where am I calling this function? Maybe I can just is equal, like I'm gonna be using, let's delete this. So if this is bigger than undo count, and if this is bigger than 1, get undo distance, or we can just assert that because the thing is that when I'm starting this, both should be the same thing, because I'm incrementing the current index. Or should it? No, it shouldn't. It shouldn't. I'm sorry, it shouldn't. And it should be -1 here. So this is the case. Now my brain is so slow. This is the case, so the difference will be 0. Then you increment it. Yeah, this is gonna work. Okay. This is gonna give us 2, 3, 4. I can also get the next one. That's gonna be minus. And if I now do undo next token here, I'm gonna get the previous one again. If I do undo next token Lexer, it's gonna give me error 21. Dang it. Undo next token. Oh. Yeah, undo next token. Oh, I have an assertion. Valid is equal to true. That's interesting. So the distance here, let us just write the distance here. I can just call it 2 times, it doesn't matter. Distance is equal to 2. Isn't it +1? Yeah, this is not right. We're gonna have buffer index -1. Yeah, that's right. I just don't understand why the first distance is 2. Yeah, the first distance should be 2, right? Because you have 2 tokens there. And yes, this is right. And then after the first undo, the distance is 1, which is also right because you have the 2, 3, 4. And it fails on the assertion that it has to be valid. Assert that this current index is valid. Buffer says -1. So something is not setting it to valid. The next token. Okay, let me quickly just check what index it's writing. Writing and that will be the Lexer current index. So it's writing index number 2. Yeah, these are supposed to be the same. Wait a second. These are supposed to be the same. Yeah, they are. So I don't know if this still works, but writing at index number 2. We have like node, 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 node. This is where it starts. And this is where the start location is, after this first call. So after the first call, this will be set. So the question is, next token, get undo distance. This will be too big. So I'm gonna just get the distance between these buffers. And if that's bigger, because that's gonna underflow. It has to be bigger. This has to be bigger than 1. I think that's better. Writing at index number 2, writing at index number 3. And undo. I'm gonna look up here what I'm looking for. So undo. This will be Lexer current index. Okay, so undo is looking at number 1. And that doesn't work. Wait a second here. Maybe this is not supposed to work either. I'm getting, like, I'm saying next token and next token. So the token will point here. Okay, this is not supposed to work. However, the distance is 2. Like, this is not supposed to work. I'm not saying, I saw you're 23. I'm not graduated. I'm at, I should be writing my master, like, which is my last year, after this summer. But I'm thinking to take a year off because I have something to do at work, and I missed the deadline for sending in these suggestions on what the master thesis is going to be about. So, and I don't want to write, like, I saw the suggestions, I think it was last week, and the tasks there are so boring. I can't do them. So I'm forced to take another year just to get a interesting task, because I want to write a master about this compiler, like a compiler, basically, because that's something I enjoy writing. But I'm studying electronic engineering. Okay, let's. All right, we have to figure this out. We're writing to index number 2. So 2, 3, 4 is at index number 2. This is index number 3. And the first one is at index number 0. So this is writing. I thought I did change this. No, I didn't change this. That's the problem. There we go. So we're writing at index number 1. This is correct. And distance is 22. That's not right. So we have to fix this. The distance is wrong. And where am I? So the first undo okay, let's just print it. So getting the distance between, okay, I'm using the wrong thing here. Okay, so based on what I'm getting here, it's supposed to, I understand why it's not working. Because both are being incremented. So in the next token, so basically this is happening. Each single time this is happening. Yes. And that's not supposed to happen. Yes, yes, okay. So what is the undo distance here? Like the first time the distance is 0, 0. Oh, wait a second, this is equal. All right, I think I have it now. That's bigger or equal. Then this is working. Okay, nice. That's cool. Let's delete this printing. So slow today. Yes. So we can undo the first part. We cannot undo the last part. So let's make a different check here. How many tokens do I have? I'm gonna just do this. We're literally so close now. And then we're gonna start with the parser. All right, so if I do this, it should undo here. So what I can replace, I can token equals next token. All right. That's a token here. So I'm gonna do this. And we're gonna say that the token equals current token. Yes, 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 yes. I know, I know. Using a pointer. And this is also something I want to get rid of, because why the hell should I do this? Like, the compiler knows very well what I want to do here. So, and it just doesn't give it to me. So my compiler will figure out if this is a pointer or a reference, and it will just fix it for me. Oops. Current token. This is only getting the current one. And current will do a peak of 0. Peak token. So this is an edge case if this is equal. So peak token of 0. Like somewhere we have to get the, like we can take it in here. So assert lexer like this, and this is going to fail the assertion. And if I would have get a next token here first, then that should work. It's going to just give me many ones. Yes. So now I'm going to do next token here instead. Let's do peak token. Let's do next token. And before that, I'm gonna do peak. And I'm gonna say like this I want this token there. Error 3. So I can't peak this many tokens. Also, this is also going to be the case if, like, what if I want to peak 9 tokens? Then I'm getting this. All right. So I want to have like printy. Peak token. Okay, so this is going to ask for more than actually in the file. And this will just process the new token, the next token. So the question is Elixir supporting that? And I would say yes, because it's not going to skip this. So this will just continue to give the end of file. All right, that's nice. I think this is working now. Eat token. Let's try to think what we actually need. I'm going to implement skip token. So this is going to require that the current token is of a certain kind. And if that's not right, I'm going to give an error on that token. And we're going to implement this error handling just now. So if token kind is not equal to kind, error at the token, I'm going to give it the error token. We're going to give it the token and we're going to give an error message. Failed. And we're going to implement this one. So let's make a new file called I can't use error. Error is a built-in file. I'm pretty sure I'm gonna run into the same problem as with string. So I'm gonna call it error instead. That seems very like a Linux word, so it might be taking that as well. Anyway, so we're gonna implement that function. Error token, and let's give it a const. Yeah, let's give it a message. Just give it a message. And we're going in error if not defined error.h. I have to really concentrate when writing these words. I'm going to include Elixir because I need a token structure. I need this one, so I'm going to include Elixir for that. Error token, and we're just saying like error exits. Just for now, I'm just gonna say that for now. What the hell do I have an A out there? Delete. Okay, adding the files. Yeah, so you can see that it works. Got a number and a lot of minuses. So I want to assert or skip the first token, which is supposed to be a token less equal, for example. So I'm assuming that the first token is less equal. This will of course fail now. Exit is a standard library. Standard library or standard IO? Error token. We need to include error. Lexer needs to have error. I'm sorry, I didn't see chat. I'm so concentrated when working with this. What is the idea of the language? It's very C-like, and it's just fixing some of the issues with C. So it's gonna be more fun to code. Like you don't need to. It's gonna be a very different syntax, but it's gonna have the basic idea the same. What's gonna be our target? Like this is just a regular C language, and I'm gonna make a backend for x86 and for ARM, and it's gonna be really crappy assembly code. Yes, I have. I'm gonna write an OS in this language, definitely. Oh, like operating system, I'm planning a file system, network stack, and a game, because I've always wanted to make a game. And this is probably not the language I'm making a game in, unless I make some kind of LLVM backend or something, which I probably will end up doing, because optimizing is very hard. I think the commands are expired. I'm going to have to update those. It's complaining. Yeah, so now we have an assertion failed, which is fine, because we assert that the current token is less equal, but we haven't the current token. So we need to do next token first. This is going to parse the current token. And then we have an error. So that's perfect. Let's make the line number a little bit more interesting here. Yeah. Let's wait a second. Let's say if we have the number, if this is a number and the token equals 5, and then we're going to skip something that doesn't exist. So you're trying to skip this one. And then this is going to work. And we have an error at this location there. So now I want to print where this error was happening. So I was probably looking at the number 5. So basically I'm saying that this is supposed to be a less equal. So let's make a bigger number, like this. So I want to underline this word, and I want to, let's say the 2 lines, 3 lines, 4 lines. Some of the lines here I want to print, and we want to print the line number before it, and underline, like highlight what's wrong. Either we could highlight it, or we can just give something like either this, or what is the other thing? I don't think I have that operator. I'm gonna stick with that one. I think that's cool. Thank you for following me, by the way. I'm gonna turn on my speaker. Okay, so this is an error. So we need to backtrack a few lines. So first of all, I want to say where the file starts, which is equal to token. Actually, this is a const char. When parsing these tokens, we need to make sure that the lexer is right, that all is pointing to the lexer. So what might work is just saying the token Lexer in here. That might work. So something like this, because we're not changing the Lexer anywhere. So by doing this, I think that will work. We just to make sure that's actually working. We can assert here. We're gonna assert that the token has a Lexer. We can remove this later, but this is just to make sure we're not doing anything stupid. Still works, printf error. All right. So the start is equal to token. Do I not have? Of course. Of course. Compiler error. I knew there was some thing wrong with that file. Compiler error. Oh. There we go. So the Lexer, the token has a Lexer, and that's a pointer. And this also have the file text, which is the start of the file. So I need to check that if I'm backtracking here. So let's take the current equal token cursor. It's supposed to be, or name text. So when I backtrack from this token here, and I need to know that I'm not backtracking past this one. That's why I have to store it. So should we probably define a number of lines to backtrack? So we can like say the number of lines we want to backtrack. That can probably be an argument later as well. That's not a char pointer, that's a integer. Let's do 3 lines. 3 lines. And it might not be possible with 3 lines, but we're gonna try it. 3 lines. So we have a loop which goes from 1 to 0 to 3, or to this one. So I'm gonna just mark it so it's easier to follow. And we might be having this pointer here. This is the one we're having, the first location there. So this will be the first line. And then we have the second line up here. And in this case, we don't have anything more because we only have 2 lines. This is line number 1 and 2, so we can't backtrack anymore. So if I declare this here, I can use it later. Sorry. So I'm gonna backtrack. So inside this, for each line, I'm gonna backtrack as long as current is not equal to start, and just getting rid of the headers would be a gigantic win for me. Yeah, that's right. Like, there's many other languages out there which doesn't have headers. But I still like to code in C. Like, for example, Rust. It is so much different. Like, I love C, I just feel there's some issues with it. And yeah, I'm not gonna say any other languages, but there are other languages which I don't think has a very nice syntax. So yeah. So let's say it might be something like this. I have to return here on each line. So we're only caring about the return. Okay, so if we have either this one. Okay, I'm gonna stop when I hit, I'm gonna stop if I hit either an R or an N. So while that's not equal to N, and current is not equal to R, because one of these will hit, and then I'm gonna exit the loop. So it doesn't matter. And I'm gonna just say current minus minus, the pointer. So in that case, it will either point here, or if this is the case, it will point here. Or it will point here, which is the last line. The line number, we can probably track the line number as well. So line number is equal to token line. And we need to save the token line. We haven't saved the token line yet. So we probably need to save that first. Token kind is equal to something. And this token should be on the same line. And we're going to track the line after we have skipped the white spaces, because this might also be a new line. So you're going to track the line here. Token line is equal to Lexer line and token column. So now we have the line and column information, and that's it. It's good. And we do that while line count is equal to 3. We can just track here if the current is equal to start. We need to check the line number here. We have the I. Break. Yes. Let's make a while loop here instead. And then we can manually increase this index here. So if this breaks here, this will still increment. So now I will hold a number of lines. I is less than line count. No. We'll still be like this, and yeah, we're still gonna break here because we have to print the line anyway. So now we have to track if so if this current pointer is either pointing to this one or this one. So if current is not equal to start, and can just make 2 while loops, not 2 for loops, because it's a little bit easier to see. And current is either one of these, And the speed here doesn't really matter because it's error handling. Then you do current plus plus. So basically if you're, because this will terminate when it's either at the new line or an R. So for example here. And then you check if this is true, you're gonna move it down here again. So it's at the start of the line. So after this, current is pointing to the start of the line. And we have, let's do I number of lines to print. So we're just going to print I number of lines here. That's less than line count. Like that's I plus 1. Doesn't matter. Do I have to use parentheses there? So for j is equal to 0 to I plus 1, we're going to be printing like some error message up here. So print error. Make a new line here as well. And then we're going to print the indentation, which is 1, 2, 3, 4. Let's use 4. And then we have a decimal number, which is supposed to be the line number. And then we add in the line here. And we know we can print the line. So this will basically be current. Can I just print this in that entire thing? Because this is still containing the information. I don't think I need to go in iterate here because it's pointing the right place. I can just track the size I want to print. So the size I want to print is the current minus the token name text. This is the size I want to print. No, wait a second. I need to do this because I want to have the line number. I forgot about the line numbers. So while current and this is just for checking, like if we have an error here, we might have end of line later. We might not have this case here. So this might just stop. The file might stop there. So we still have to check if that's gonna go out of bounds at the same line. Out of bounds at the same line. While that's, and this is not equal to new line, and current is not equal to R. Then we do plus plus. We can just print it first. So we print that char. Current plus plus. And we can actually do because I have to track if, now we have to think a little bit. We have to do it after this. if current is pointing to a new line, do current plus plus. If current is pointing to like this. So that'll work. So if the user for some odd reason only has an return character, carriage return or something, I don't know what it's called, then it will still work. It will do current plus plus. So basically we're skipping this new line. So at the very end, I'm gonna force a new line. And the reason is that if the user doesn't have this, like, I don't know, like, how that should be even possible. Let's see if that works. Okay. Decimal number. I'm required to have a line number here. And the line number should work. So J is increasing. I'm just going to track the line number. Line is equal to token line minus I. Yeah, minus I. That's the line number. And then we print the line number plus plus. Error 117. Oh, there we go. So we were printing what's wrong. I don't know if that was what I was hoping for. And we're printing error after. All right. So you can see something is working here. Let's see if the line numbers are right. So this is line number 5, which is right. This is number 5. The question is, we have an error here. So why didn't it backtrack enough? That's the question. So this J number here was too big. It's a mismatch between this one and the other one. Line count is equal to 3. So I want to backtrack 3 lines. So I'm backtracking 1, 2, 3. I want to see where it's at. Holy crap, I'm getting so scared of that noise. Thank you very much for following though. Current char is nothing. Isn't that great? It's probably that one. Let's see how many times this is happening. It's supposed to happen 3 times, and it's happening 3 times, and no, this is supposed to be equal. If that is equal, that's probably the one. So if it's equal to this one or this one, we're gonna skip either of them. Oh, is that if it's it's equal to this one or this one. It can't be equal to both. Yeah. So we are printing the wrong thing. We're not getting the first. And the current char is 5, which is here. Let's print a token. Let's token name size text. Token is number 5. All right. So while current is not equal to start, might that maybe be the case? Let's print the 2 pointers. I just want to check if those are not equal. No, those are not equal. Because if this was equal to this one, that would happen. If current equals start. Oh, wait a second. The first time this is gonna happen, of course we have to skip these. We have to skip both. This will be something like this, like in the same way. So that's equal to this. You do minus minus, minus minus. That's better. So you can see we're doing the right thing here. We're printing one line too much. So I think that's the case. I don't know why. But I'm gonna assume that works. And now we can see that this is working. If I increase this number to 4, I'm gonna get one more line. No. I'm getting one more line, I'm getting the wrong line. Let's say 2 then. And this is working. 3 is working. 4 is not working. Let's choose 5. I'm getting this weird line at the very end. Oh, wait a second, we're backtracking one too much. I know what the problem is. Because we're basically skipping past this one. So since we're skipping past it, we have to current plus plus first. And then we have to check if either of these are true. No, that might also not be right. Minus minus. And these should probably be in a different order. So it's a new line. This is giving really weird outputs. And we probably should do like this first. There we go. Oh. Okay, I'm gonna ignore this because this is not fun to watch. We're gonna track the new line. If it's a new line, we're gonna jump behind it. And if this is not equal to start, we're gonna increase the pointer. If that's then a new line, we're gonna skip past that as well. There we go. So we're asking for 5 lines. 1, 2, 3, 4, 5. That's working perfectly. We have an error as well. Implicit declaration. Implicit declaration. That's an elixir. Okay, so we have an error, and we know where it is. So the only thing we're missing now is just underlining where that error is. So I'm indenting this much. I just have to skip this. Actually, let's make a counter. How many lines should we support? Does this return the number of characters written? If that is the case, that's very nice. Because then we can just say like count this is a really small problem. I don't care. I'm gonna print at least 3 characters. This is gonna work for files up to 999. And gonna do one more, 1, 2, 3. Okay, 1 too much. Let's do 1, 2, 1, 2. There we go. So here we're printing the error. So I'm still gonna exit though. I'm gonna exit with a status code 0. And here, I want to know how big this token is. Yeah, I'm just gonna make a new for loop. Holy fuck, I'm being so scared. Thank you for following. It is actually worse than writing, like watching a horror movie. That is, I don't like that. I'm getting so scared. What token should we choose? This one. All right, so now we can see we have an error and we are telling where this error is. I'm actually going to do like next token here, so we can check if we're using the correct number. So now we should get an error on the next token there. All right, so we need to skip. This is starting at the same location, so we need to skip the number of where this starts. And like, it is actually nice to have the column number there, because then it's going to be much simpler. Token column doesn't really matter. I'm gonna fix this later. So now we have the error at the right place. That's perfect. Error reporting. And are we actually reporting the error? We're not having a message. So I'm gonna say error, and then if or I'm gonna assert message. It's gonna have a message. So now we can see that we have error skip token failed, and we probably should have a new line as well. error skip token fail, and then you're printing like where that is. I think that's very nice. I don't want to have this though. That's annoying. Can I do this? Yes, that's beginning to look like something. Hey, cool project you have on GitHub. Another language rather than C. Yes, I've considered this one. I'm probably gonna switch completely to this new language here, because I like C. I like being able to do it the way I want. So if I want to make something in a language, and I like to make it the way I want. I don't want to have a language which adds all these restrictions on how I should code. So yeah, it's gonna be more unsafe, but at least I can code it the way I want. It could probably be a bit safer than C, but no, I haven't considered it. All right, let's stop this. New lecture. Let's start with a parser. This is gonna be very cool. So we could probably, you know what? That's too simple. It is actually too simple. We're gonna add support for parenthesized expressions as well. So if this is a parenthesis, skip punctuation, lecture 1, token, and we're gonna have open parentheses and close parentheses because they're really simple to add. I'm adding that. Okay, so this is open and this is close. I think that's the biggest word. I might do this multiple times. So tedious, yeah, but it's cool when it works. So we're gonna give it open parentheses. And that's a misspelling of punctuation. Close parentheses. Okay, so now we have support for that as well. So let's just write something that the parser should be able to compile. So I will do like 32 plus, let's do times here. And we say like 1 4 is equal to 2 plus 2 times, we have parentheses here as well, times 2 minus 34, or minus, let's do 32 times 1 minus 32 times 2. This is supposed to yield 64, isn't it? I think this is supposed to yield 64. And this is of course true, so this is going to be 1. No, that's 0. Yeah, because it's doing this first. So this is supposed to be 0. Let's let's do this. That's supposed to be 2 then. Yeah, so if I do 33, that's supposed to be 2. Made a toy language that let you use base64 encoded strings. What is base64 encoded strings? I never heard of that before. Is that like UTF? Does that make sense? Does that even make sense? It is not understandable by a human. Binary data as text. Oh, I understand. Okay. So you're gonna start simple. Take any binary file. Oh, I see. That's actually cool. But like, what's the use for that? Oh, that's really cool. I understand now. Yeah. So, just to check here, I'm gonna just verify that this is actually working. That I'm getting all the tokens. Okay, so the last one is 234. And we have plus, you can see we're recognizing all these numbers and parentheses correctly. So basically when, let's assume we're the parser, we're gonna ask for these tokens and we're gonna get these tokens one after one. And we're gonna generate a syntax tree representing that. Yes. So let's start with the parser. That's the job of the parser. And I'm gonna, after the stream, I'm gonna fix up these, the syntax here, because I like to have it like a little bit clean. So for example, this I don't like at all, but I'm gonna fix it later. Print token. Oh, there we go. Parser, if not defined, types.h, that's including typedef. I think I want to use a different file for, call it like asts, or I'm gonna just call it tree. Yeah, I'm gonna call it tree. So this file will contain all these tree structures, like statements, types, like everything is gonna be a few types here, and I also want to allocate these types. So I'm gonna make a C file where I'm gonna allocate these types. And I probably need to include std lib here for the malloc. So that's a tree. If not defined. That's so hard to write. Define. There we go. Okay, so let's add all the types in there. So what do we need? This is going to be used directly by the parser. So we're going to make a function for parsing. Like the top level function is going to be here. So we have to just see what we can compile now. So from the file, we should be able to compile compound statements, which are basically statements separated by a semicolon. So let's start to write some structures. So we have a program with the gifs and stuff stored inside. Yeah, I know what you mean. It's it can be nice, but like you're not gonna see it in the editor. It is just gonna be raw data. Or probably if you have an editor for it. Does this have an extension for it? Or am I totally off the track now? Base64. No. Oh yeah. Okay, so you have to use this editor here then. And then you can actually see the data. That's interesting. Do you know about Rust or Sig? Yeah, I know about them. Rust, I think it is way too complicated. I don't think a language should be more complicated than C. And yeah, it's dangerous to use, but there are some things you can do to make it more safe. And Sig is supposed to be like C, but better. I'm sure it's really good, and I've seen a lot of it, but I don't recognize the syntax at all. And I don't really feel that's for me. So that's why I'm making something myself. This is ugly and complicated. It's really complicated. And yeah, I don't like the look. The progress is good. We can print all the tokens that we need for parsing this early stage. And if we have an error, then we can print it in a nice way. That's about it. Yeah, it is. All right. So let's start with expressions. Let's just write something down. So an expression is something that evaluates to a value. Like I've done some of this before, and it was a nightmare to understand what the difference between expressions and other things are. But basically, expressions are constructs in the code which can evaluate to a value. So, for example, this is an expression. Also, this is an expression because this is also a value, and this is an expression. Right? So all these different constructs are expressions. In C, even this here is expression. This is allowed in C, and you can, for example, say like data is equal to this. This is allowed in C. I don't like it. I don't think an equal, like I understand the use for it, but at the same time, I have never used it, and that's probably because I don't like it. And besides, then this should also probably work. I don't know. This is a comparison. you say like does this work in C? I think this works in C. The problem is that I want to overload this operator here. Probably this is going to be the autocast, because in C I have a really big issue with, like, I know I'm casting this type the correct way, but if I have something like statement, I don't need to write like statement here as well. Like, I know this is I know this is right, so why can't I just do this? And even better, yeah, like let's say I have like this. This is gonna autocast void to statement. So I'm just saying that because this will not be an expression in my language, because this is a statement. This is not gonna evaluate a value. So that's expressions, and you also have statement expressions. So a statement is probably easier by just looking at examples, but this is a statement. This is a statement, even though this is a value, it's also a statement. This is a little bit like weird. It doesn't have a concrete explanation, but this is an expression statement. So everything which is one line in the code separated by a semicolon is an expression statement, which is basically an expression. And we have an assign statement over here, and this is also an assign statement. Everything which has an assign is going to be an assign statement. Yeah, and for loops, while loops, that's also statements. And for expressions, if you have, I want to do like 33 plus taste. This is valid because this is dereferencing taste. So this is not a binary operator. So this is a unary expression in which we have an operator which is working on one single construct. So I can also say like this. This is valid. This is valid if this here evaluates to an address. So then this will be a unary expression, and it will point to this expression node here. So that's some of the info, like when I'm calling things. It's very usual. So yeah, and all these like numbers and identifiers, taste, data, that's primary expressions. So we're gonna have binary, unary, and primary. And every one of these things are pointing to new expressions. And this is gonna be a statement. And this is gonna be a compound statement, which is just a collection of statements. And then we're gonna use a list. Preferred languages for low level. It's handy for loops. What's handy for loops? Like, we're gonna have some cool loops in this language, I think. Rust is very nice to use. I think it's very nice once you get used to it, but I think the learning curve is a steep one. Iterators, copy by default. Yeah, like embedded system you see because it's fast, and you kind of need that on embedded systems. But Rust is also fast because they're using LLVM backend. So yeah, Rust is beginning to come for embedded systems. They're beginning to come with like ARM compilers and I don't know, AVR compilers. Yeah, probably AVR as well. That was what I was like for a few months, like probably a year ago. They came out with a AVR compiler. So it's for embedded system as well. Implicit casting, I've seen this for quite a while. Yeah, I think that's a nice feature. The casting, we have to figure out how to cast exactly, like how that syntax is going to be. Do you have a document describing the language? Not yet. I'm going to probably make it. But the syntax isn't really done yet. Stroke when writing code using unsafe API. Yeah, I'm writing my own API, so I know what's going on. And I'm not saying that's not safe, not unsafe. It's probably like really unsafe. That assignment is an expression. It is handy for loops. Yes, that is right. I understand now. That is right. But maybe I want to have this operator yeah, I can probably make a sign, like I can probably make a sign an expression as well. That's not gonna mess around with my syntax here. No, that's not gonna be a problem. I actually agree. And I was told by some other guy that even though I can restrict this language very much so that you can only code like I want personally to, like in my coding style. But I was told that that's not good, and I totally agree. So a language should be like, even though I'm not going to use that feature with equal, it doesn't, like, I can add it. It's not going to be a problem for the language itself. So anyway, Motorola LLVM target alive because Rust people are wanting to use code for it. Oh, code for it. Oh, that's good, huh? So it's still working on that. Still working on it. Okay, let's start with making these things. An expression is one of multiple things. We're going to use a union here. And then we're going to have an expression type. Again, I'm using kind instead of type because I'm going to be using type for something else, which is types in this language. So I need an expression and an expression type. So let me just add it in here. All right. So that's an expression, and this is going to contain all these primary expressions and stuff like that. I'm going to add it beneath instead. Primary, unary, binary. Expressions, primary, unary, and binary. We're gonna have like multiple of these. We're gonna probably have like call expression, for example, call expressions, dot expressions in like strict reference, like some like bitwise operator. That's gonna be an expression, but we're just gonna start with these guys here. Expression primary, binary. So one of these, so that field here is going to determine which of these I'm going to use. And by the way, I probably have to make it down here because I need the actual size of these fields. So binary. So expression, unary, binary, and primary. That's the three kinds we're gonna deal with. The primary is also gonna have a type. So I'm gonna call this like primary kind. So this might either be a, this is gonna be much, I'm just gonna say, I'm just gonna store the number and the string identifier. Let's use a enum for this, like a union. So either this can be a number, or it can be a collection, it can be a string identifier, and I'm gonna say where this identifier is placed. I'm gonna just remove that for now. And the last is just a string. I'm gonna ignore that as well. So here's the different types of primary expressions. So we have, whoops, number. So that's primary, unary, binary. Expressions, let's hope I'm adding all of these. That was that, and then we have an enum for this primary kind. All right. Ternary operator. Is that like 3 of those? Like what the? Oh. Crane lift will become a decent replacement for LLVM. Much faster compile times. Isn't LLVM just a backend like an optimizer? It's probably as a compiler as well. But yeah, in GCC compile times are way too slow. Way too slow. I don't know what it's doing. That naming convention looks like from Rust's compiler. Expression, expression kind, type, type kind. Yeah, probably. I haven't seen it. I haven't looked at the Rust compiler because I don't know how to write Rust. But ideally, like I like much more to have like type here, primary type. I always use that. But I'm gonna have a structure called type eventually, and that's going to be like type, and that doesn't make sense. So that's better with type kind, and that's why I'm using it on all the other structures. That's the reason. Are you going to use LLVM as a backend? I'm going to do my own in the beginning, and if I want to have a faster code, I probably will make an LLVM backend. So yeah. Forbid unsafe code Linton. Is that actually a thing? Forbid unsafe code? That's going to be very annoying on embedded platforms. That's not actually possible. Horrible to use unless you need support for many platforms. Yeah. I'm going to probably be generating extremely bad assembly code. Like, until I have some kind of register allocator, it is going to be slow code. and you can do some optimizations, but yeah, that's gonna be the last thing I'm gonna do. Probably I'm not gonna do it. I'm gonna rewrite this in their own language first, and then I'm gonna make it. All right. A unary expression has a unary kind. So we have to know what kind of unary expression this is. And as I said, a unary expression is just one expression. So the expression is the operand. Is that the right word? Unary kind. We're also going to save the token here. So you're going to save the operator and the operand. And a binary expression has a binary kind. And it has an expression left and right. And I'm also going to save the token for the operator. So this is going to point back to the structure. So the thing, like how it's going to work, I'm going to make something for parsing an expression, and that's going to look like, for example, the printer or the generator is going to look at an expression, is going to look what sub-expression this is, and it's going to recursively call itself with either this one, or this one. So that's why this needs to be CAS compatible, because it's much simpler to deal with those. And a primary, we need a unary kind and binary kind. Binary. So let's just add in what we have. So for binary operator, we have all of those. So I'm gonna just copy them. Binary minus binary multiplication, binary division. Oh, plus, I'm missing plus here. Binary equal, binary less, binary less equal. I'm writing the same thing, I know that. It's because I want to have a separate thing for those, because in some cases the binary operator isn't the same, like it has a different meaning. That's the entire reason. Greater and equal. That's it. Those are the ones. Unary kind. What kind of unary expressions do we have? Not anyone here. Like, we're not gonna consider those yet. But I believe we cannot allow an empty expression. I'm gonna just say counts. Binary type, binary kind counts. Okay, that's a bad naming. Unary kind counts. All right. So primary, unary, binary expression. So since equal is still gonna be okay. It's horrible. Yeah, I believe you. Operator is a reserved word. I don't think so. Is it? No, it's not a reserved. It's just that I haven't defined the unary kind. Or is it a reserved word? What? Why should that be reserved? I probably need to include Lexer. Oh, come on. Lexer and token. It's so slow. Okay, now it works. Unary kind and binary kind. It is really slow. It doesn't pop up anything here. Anyway, that's fine. Oh, it's probably because I don't have a typed yet. So I'm gonna go in. I'm just gonna do split screen. Let's try this. Hello, Farshield Musabi. Welcome to the stream. Okay, so unary kind and binary kind. Primary, unary. Probably list this up a little bit. It's hard. I just hope that I've added all the things we have so far. So let's add a statement. That's really fun to write in Dvorak because it's super simple. Statements. And of course we're gonna have a statement kind. Which is the same thing as this. We're very close now. This is the last thing we're gonna add. Statement kind. So since a sign statement is going to be an expression which can evaluate to a thing, we're gonna say statement expression. So this is an expression which is separated by a semicolon, and that's sort of a line in the code. So that's a statement expression. Anything more we want to add in here? Yeah, a compound statement. That's compound. Kind count. Yeah, compound. So we're gonna have some structures here. We're gonna two more. We're gonna have an expression statement. And a compound. Do I say compound? Like compound is implicit. Like I'm gonna just say compound. So for this I'm gonna include list as well. Because then I can do list. I'm gonna call it statements. So this is gonna be a list of statements. Yes, this is a list interface. This is a circular doubly linked list. I'm using it for everything. What am I gonna call it? Like, I don't like to have it that long. That's a little bit too long for my taste. Fuck it. Expression statements. Because expression statement was going to point to an expression. We can probably make this a pointer instead to an expression. Is that probably fine? This is just going to hold it in. Yeah, okay, let's do that. This is just going to be a pointer to the expression. So when I parse this, yeah, let's leave it like this for now. It might we might need to change it later. Compound. So we don't need this one. That's a statement. All right. So I think we're done now. We can start actually compiling this or parse this. Have you written a compiler before? I have written a compiler before, yeah. I have written something similar, but like that was a mess because that was the first time. So I decided to do it on stream because now I have a little bit more background, so I don't so I'm not stuck on stream for like 6 hours without doing a thing, because that's very boring. And I decided to write it from scratch because the code was a mess. And because you don't know what you need. So I know what I should do here because I know very well what didn't work. So yeah. So the overview is that we have statements that's lines in the code, separated by semicolons, for now. And a statement can either be a new compound statement. So for example, I might have an if statement here. So if, for example, true, this is a statement, and this is containing a new compound statement. So this body here is a new compound. And an expression statement is most like what we're gonna be mostly concerned with, and that's just a line in the code. And an expression, we have 3 types. We have unary, primary, and binary. That's the wrong order. That's the wrong order. That's better. So this is pointing to 2 expressions, and it's going to perform an operation between them. This is going to point to one expression, and it's going to perform an operation on that expression. And this is just a number or a string or whatever. And this is telling what of those are actually in this structure here. It's telling whatever, like, it's telling which of these we should choose. Yeah, I'm using Dvorak, so I'm still learning it. That's why it's going so, and like, if I have to talk as well, it is so hard. Like, I'm struggling with Dvorak without talking Norwegian, and if I have to talk English, that's even harder. Linked list, yeah, it's gonna be much linked list, but this is a really clean interface. So it's really simple. It is not like, you don't need to think about the pointers. Too long a name, just drop the vowel. Cack. Too long a name. It's better now. Do you have the B and F somewhere? No. We're gonna be writing like, no, I don't have the B and F somewhere. When we're writing stuff, we might write what is representing, but I'm not sure. We use a linear buffer and we didn't use pointers, just indices. That's probably faster. That's probably faster. So, but this is simpler, I think. So what I'm gonna do, I'm gonna parse this tree in the first run, and then I'm gonna do a second pass of the parse tree, and then we're gonna rebuild like linear tables, which is faster to work on. All right. Okay, let's implement this. Do we need anything more? Yeah, let's just parse a statement here. That's fine. So I'm gonna do this and this, and it's still working. So now I'm gonna delete this. Oops. I'm gonna delete this. And we're gonna call in with the parser, we're gonna make a function which is gonna parse a statement. So if I'm parsing a statement, that's gonna in fact parse this entire thing, because this is a compound statement. And actually, we need to store more information here, because we need to store the lexer, we need to store the current and previous scope. We're gonna have to I don't know exactly how I'm gonna do this. I think I'm gonna like have some scope tree structure as well. I'm at least gonna have a parser object here, and that's gonna go not in the tree, because not the tree, it's gonna go in the parser. So I'm gonna do a type def of the parser. So parser. This is going to contain all the information we need to parse the actual thing. Yeah. And what is that? Well, we need to store the lexer, which is currently active. So we're going to use one parser object to parse one single file. And also, I like having this in a structure, because if this eventually is going to be multi-threaded, it's going to be much simpler to split this up into multiple threads once you have it like this, I think. And we have a lexer. All right. So let's start with the first function. It's going to take in a parser, and it's going to parse that. So we're going to include here the parser. Error type parser. We need a lexer. I probably need the... Okay. Anyway. Let's make a new parser as well. So I'm going to say parser something like this. So I'm going to give it the lexer, and I'm going to get a parser and back again. calloc, I'm gonna say I'm gonna allocate 1, and the size is gonna be size of parser. I'm gonna allocate this dynamically, and I'm gonna say lexer equals lexer and return parser. So this just allocates a new object, nothing special there. I'm gonna expose this function here. We are gonna expose you. So now we can call a new parser. That's gonna link the lexer to the parser, and then I can call parse statement with that parser. Does that make sense? And this is gonna return a statement. Yeah, and we're gonna make a printer as well. We're gonna see how to do that. Let's skip the printer for now. We're gonna have a printer because we want to be able to visualize this structure in memory. So parse statements. Let's see if this is working first. Ooh, some errors. That's interesting. Okay. All right, everything is just a list implementation. There we go. So undefined reference to, we have to add a parser we have to compile it. There we go. Done compiling. All right, so it's gonna generate this output here. How much is the clock? 21, not that much. Maybe we can do the generator today as well. I was once in Norway. Femundsmarka Lake. That's beautiful. I haven't been there. Like, I know there is really, it has like really beautiful nature there. But there are bear there. There are bear in that area. And I hate that. Like, I'm so scared of bears. So I don't know if I want to go there. But yeah, it's I've seen many pictures from there. It's really a nice place. Is there any reason you're using Dvorak? As far as I know, it gives no advantage over QWERTY. It is much more comfortable typing on. Like, so it isn't faster. That's the point. It isn't faster. Once you know how to touch type, everything is gonna be like have the same speed. But I feel Dvorak is much more comfortable typing on. Yeah, and I didn't know how to touch type before, so I either had to learn to touch type with Dvorak or with QWERTY, and I choose Dvorak. And I'm really happy with the choice. Okay, let's clean this up a little bit. Parser. Okay, so it's parsing a statement. That's good. So now we basically have to start. parse a statement. Actually, we're gonna make a function for parsing a compound statement. And this is going to return a statement. Because the parse statement will only track a compound statement if it has like curly brackets. So that will not work since I'm not having... Or like, I'm going to ignore this and let's just add some curly brackets here. And then it should be fine. So that's a statement. And we're going to parse this statement here. Yeah. All right. The first thing we have to do, we have to make sure this lexer is having the first token. So that's, we're going to always track the current token. So that should point to the first element. So therefore I'm going to say next token. Like this. If I now print the token, we can make a function for printing that up here. Print a token. Let's just print the actual token here and a new line. And please just ask questions if something is unclear. Like, what is this name, for example? This is a token name. So I will, for example, be like 4 or like equal. So I'm just printing this token name here. Let's remove this and a print token, and we're gonna do like current token. So we're gonna print the current token there. And that's an error, and that's right. And the reason this is an error is because we don't track the curly braces, I think. So I think we're getting this error here. So if I was saying like 2, 3, 4, I was getting 2, 3, 4. And this is because it doesn't find a token. So we're gonna go in and we're gonna add curly braces. Open curly. Like this. I learned how to touch type by accident. By accident, actually. Without Lamplight. That I heard that was the case. Like, people know how to touch type from doing PC games. That's actually a thing. I think I read it in while reading about should you learn Dwark or some other thing. I think that was where I saw it. So an open curly bracket here and a close curly bracket. So this is a close curly. I'm gonna do this.
I was positioning the fingers wrong. Close curly. Curly, that's a typo here. That's clone curly. Close curly. So if I now do this, it should work. So the first step, the first token is this one, open curly bracket. So we can check if this has the right type. So we're gonna do if, let's start with the lexer here. So the lexer is equal to parser lexer. This is just that the parser is storing the lexer object, and we have to use the lexer object to get information from the lexer. So now we can say that if, let's say token is equal to the current token of this lexer. And if token kind equal token open curly. So basically, if this is happening, it is gonna parse a new compound statement. It's actually gonna go down here. We're gonna have to implement this compound statement. I'm so fast. Wow. It's annoying. Yeah, I'm gonna call it static because it's gonna be called by the parse statement. And I'm gonna place all the static functions up here. Clone curly. Yeah, it should be close curly. Thank you. The clone curly wars. Yeah. Theme, I'm using the standard theme, the dark. I also have this one. I like coding without any syntax highlighting. That was actually kind of cool. I'm gonna go back to the original. I don't like this theme though. It's so horrible. If that is the case, we're gonna call this function here. And that should return a compound statement. So I'm just gonna say statement here. And parse compound statements. So the question is, parse compound statement. That's gonna look for, yeah, that's gonna look for the opening curly and closing curly. So I don't have to check that here because a compound statement must have something after. So actually I can just return here because this is supposed to return a statement and I'm returning this. So here, I'm actually gonna skip, I need a lexer object. Okay, I'm gonna skip the open curly. And this is just making sure, like this and this one is redundant because I know this is, but if I call this if like in an if statement or something, I know that there is supposed to be an opening curly, so I'm just checking it here as well. Token close curly, no. Curly. And in here, I need to parse statements until I'm hitting this close curly bracket. So let's just, maybe that's easier. Current token is current token Lexer. Okay, so basically we're checking if the current token is open curly. And that's going to make us parse this statement here. We're skipping the open curly, so now the Lexer is pointing to the token after that. In other words, 2033. So this should print 33. Okay, so we have an error. Skip token failed, what the fuck? Current token is... print token? Return parser. It's a calloc. Am I doing new parser? That's weird. Okay, current token is something. Oh, yeah, perfect. Okay, so yes, I know what the problem is. So basically it says that the current token is this one. Let's do this as well. Print token. So it seems that we're not getting a new token. We're only getting the start one. Okay, the skip token isn't working. Oh, we're not doing anything there. Yeah. Yes. So basically, if the current token is not right, we're gonna error on that token. Skip token failed. I don't know why the print is messed up there. But anyway, we have to call in next token here. That's gonna fix it. So skip token failed. Yeah, so it gives us 2 lines here. That's these 2 here, because we're expecting a close curly, but we're getting a 3-3. So this is right, but we're missing the last line. So I think that was the case where I think this was supposed to be I+1. Yeah, it's supposed to be I+1. Yeah. Anyway, skip token failed. So basically what's happening, we're skipping this one, and that leaves us with 33, and then we're skipping close curly. And this is failing because we don't have a close curly, we have a 33. So what I have to do in here, I have to do a while loop. So should we allow an empty compound statement? Probably. Yeah, I think probably we should allow that. So token is equal to current token Lexer. This is going to be the 33. And I'm going to say while token kind is not equal to token close curly, then we're just going to continue. and then we're skipping that at last. Token, and we have to update the token as well. So token equals current token Lexer. New token. I'm gonna explain what this is in 2 seconds. Does that make sense? Yes. That doesn't make sense. That does not make sense at all. If I now do this, is it the typo? Okay. Yes, because I'm not getting the next one. If I say here next token, it is working. So let us print done. So this is printing when it's done parsing a compound statement. We have to check while that's not close curly and is not token end of file and close curly. So basically this is working. So we can say this is correct. It prints done. If I would have deleted this one, it would give an error because it's expecting a close parenthesis, but it was getting a end of file. So here we could probably check for, so if token kind is equal to token end of file, we can say token and give a message. So unexpected end of file. So we have an unexpected end of file. So it basically tells us we have that we're missing something. Actually, this should be. I'm gonna ignore this. Eventually, I'm gonna replace this with more useful error messages. So it would, for example, say like expecting a closing compound, like a closing brace or something. Yeah, so what are we doing here? We're starting with the current token, which is 33. And as long as that token is not close curly or end of file, we're just getting the next token here all the time. And we're updating the token which is currently at. And that's gonna force it to print all these things. So instead of doing this, we're gonna call parse statement again, which is gonna move the token the same way. So statement, let's make a new statement there. Parse statement, parser, and here we should have a new statement. And this is going to be added to the list. So this is a compound statement. So you're going to allocate a new compound statement. I don't know if this makes sense at all. Statement compound. Let me think here. Let me think. So a compound statement is just a list of statements. Yeah. We have to make some function for allocating this stuff here. I programmed just for the beauty of syntax highlighting. Yeah, some syntax highlighting can be very cool. You skip close curly. Yeah, that's right. Yeah, I'm missing recursion. So the thing is that I just wanted to see if this was working correctly. So ideally this is gonna parse a statement, which is gonna parse an expression, which is gonna quit before it reaches the close curly or the semicolon. I'm gonna just write the allocators, and then it's gonna be much more understandable, like what I'm doing here. I'm gonna use a different thing. This is impossible to... That's nifty. Ooh. No. No. Just gonna sharp dark. That's better. Okay. I'm gonna just make some functions for allocating this stuff. Nothing too crazy. So we're going to allocate a new statement, and we're going to give it a kind. And this is actually going to return a void pointer. Because as you know, a statement can be multiple things. It can be a compound statement, an expression statement. It can be multiple things. So probably, yeah, I'm just going to leave it with that. Calloc 1. And I'm gonna make a new compound statement. That's also gonna be a void pointer. So this will actually allocate a compound statement here. So I'm gonna say new statement, and we're gonna give it the statement compound, and we're gonna do list init compound statements, which is a pointer, so we have to do the address of that, and compound. So allocate this, and you can either do compound statement or statement, because all start at the same address. It doesn't matter. The size is not the same, but the address is the same. So here I'm just using the compound to actually get the statement list very cleanly. I could have done like statement something like this, and list init. Then it would have been like statement compound and a dot statement. Something like this. So I think it's cleaner to have it like that. That's why I'm using void pointers. Expect token. Expect is you're expecting the next one to be some special thing. I'm on my last number of, why is YM? Set of identifiers and operators then can be evaluated to compute a value of a given. This is basically language. So we just, everything you write, like everything I'm writing here, we're basically gonna try to represent what I'm writing here. Like we're gonna try to represent the language. Yeah. So compound, I'm actually gonna return, I'm actually gonna allocate a compound statement. We have to expose these functions here. Oops. So now I can say new compound statements, and the list will be initialized already here. So that will be a list of statements So what I can say here, I can say list add last parser. We need to have the list interface. So what we can say list add last. Like, why? Oh my god, am I having the wrong interface here? List pop, what the fuck does pop mean? List remove back. List pop front list. List remove last. List remove first. Last list push front. What did I say here? List push before. So here I'm gonna say add before. List add first. List pop? What the fuck does pop mean? I don't know what I was doing here. List remove. This is a really stupid thing which has to be rewritten. List iterate, that's fine. Iterate reverse, get last, get first. It's empty. Delete, add. Let's see if that's working. List at last. Okay, there we go. So we're gonna add. Let's see what I'm gonna add. Like, we have the tree here, like the structures here, and a compound statement is a list of statements. So from this statement, I'm gonna list these structures here. So in order for me to list them, I have to add a list node here. So this node is gonna allow me to list. I'm gonna link this node to this list here. So now I can say list node, we're gonna add a list node to statements. So we're basically adding this to the statement list. And then we're updating the next token here. I'm gonna write it like this. Yes, this is good. So compound statement, we're expecting the first one to be open curly. We're allocating a new compound statement, initializing all the lists and stuff like that. We're getting the current token, which is the one after the curly. In this case, it's going to be 33. And we're just, as long as this is not a curly bracket or end of file, we're just going to continue to parse these statements, which is going to end with, like, which is either a for loop or some statement with a semicolon after it. And you add it to the list, and you update the token, so this is going to point to the current one. And then if this is curly or end of file, you're going to quit. And then you just skip the close curly. And if this is the end of file, it's going to fail here. So that's the compound statement. And parse statement is going to check for open curly. then it's going to parse a compound statement. Otherwise, it is going to parse an expression. Parse expression. And thank you for the follow. Welcome to the stream. Welcome, welcome. Again, I have to turn on the speaker. This is not really an expression. The difference is that expression doesn't end with semicolons. So I'm gonna make a separate function for that. So parse expression statements. And this is really simple. This is just gonna save an expression. And it's gonna skip the close the semicolon. Token semicolon, where is that? And we're just going to return the expression. So basically we're just parsing an expression, which is this part, and then the token is going to point to this last one, and we just expect this to be a semicolon. If this is not a semicolon, it will give an error. So for example, if I write something like, let's say hashtag here. So this is not a valid operator in an expression. So then the parser will eventually, it depends on the precedence, but it will eventually recurse up again, and I'm still pointing to this one, and it's gonna quit the expression parser with it pointing here, because this is not a valid operator. And then it's going to check if this is semicolon, which is going to fail. So if you write something in expression which doesn't belong there, for example, if I write like plus test and test again, this is not going to work because it's not going to expecting this one. So this is going to be caught by this skip token. Yeah. So now the main thing here. Yeah, this is the main parser. So this uses a recursive, really cool algorithm. I hope I remember it. We're gonna need to wait a second here. Where is that? Nope. Yeah, it's a binary operator. I need to track the precedence for these operators. I need to track the precedence there. Thank you for following. Welcome, welcome, welcome. Kebab. I don't know why I took that and dragged that around. Yes. So the first thing we have to do, we have to make a function which is going to convert. This might be stupid, but we're just going to do it like that the first time. We'll have to convert this token kind to this binary kind. So that's going to be a function, so we can get the right operator here, and then we're going to have a function which is going to return the operator precedence based on this table here, like based on these options here. So for example, binary plus will have a lower precedence than binary multiplication, because if you write something like this, you want this to have higher precedence. So this is going to be taken first, and then it's going to be this. So those things we need to keep track of. So let's do 1 plus 2 times 3. That is going to be how is this like plus, how am I doing this? It's gonna, as long as the precedence is like, as long as the operator precedence is rising, it is gonna continue to recurse. That makes sense. That makes a lot of sense. So the tree is gonna be made like this, and it's gonna track the new precedence here. This is not gonna be a thing. This is gonna be parsed again, and this has a higher priority, so it's going to continue to recurse down. I'm getting 2 and 3 here. So this is the one. This is the thing we want to implement. And if the precedent falls, we're going to take that case as well. So it was like this. It will start by getting times here. It's going to be times there and plus there. No. Let me think. Let me think here. This is a recursive piece of shit. So I have to. My brain is not tolerating that. We're parsing the number 1 first. This is what we're starting with. And then we're looking at this operator here. So that's fine. So far so good, and we're getting 2 here. This is like this is a recursive call. So when it goes down here, so I'm doing this first, then the multiplication. This has a priority, and then I'm calling recursively down with this priority here, and this is going to yield a number. It's going to parse number 2, and if that number okay, I think I got it now. So it's gonna start there. It is gonna track this priority here, and it's gonna call itself the parse expression with this new priority, and then it's gonna parse 2 here. It's gonna parse 2 separately, and the next operator is gonna get is plus. So this is getting plus here, and it checks the operator. So this plus is lower than what it was called with. So then it's not going to continue to recurse, it's going to return the number 2. So this is returning 2. And then it's back into the original call, it's going to recurse up again. And then I have a pointer here, which is the original expression. And then I'm going to replace this one with this one. So basically this is the pointer I'm getting at the second call. It's going to be a loop which is tracking this. And that's how we construct this tree this way. 3. Okay, so this is it is not much to write. It is just understanding what it does. But I think that should be, yeah, nice. So again, we need to make these functions for converting a token type to a binary type. And if it's not a binary type, actually, wait a second here. I think it will be wise to start this with, for example, 1. Or binary error. I don't know if I should use error here. Let's use 1 here. And the same thing with probably this as well, if I'm doing it the same way. So I'm going to convert the token to a binary kind, and if that's returning 0, it's none of these. And then it's also going to recurse up again. Yeah. Okay, before we start, I'm just going to go to the toilet. So I'm going to just leave it like here. 2 seconds. I'll be back in like 1 minute. All right, I'm back. Just 2 seconds. Yeah, anyway. All right. Yeah, so let's convert from this token structure to the binary kind first. So static. This is going to return an enum. So binary kind. No, that's not right. So static binary kind. This is going to be a function. So token to Should we use token type there? Probably. I'm gonna use token kind there. Yeah. So if it's token, okay, we have some things there. Okay. So case token equal return equal. Token greater equal return binary greater equal less return binary less token less equal return binary less equal. Do we have any more? Equal, greater equal, less equal, minus, plus. Yeah, I'm missing case. Thank you. I didn't see it. Binary plus division. Multiplication, return binary multiplication. So there's a cool feature which is this. I didn't mean to ignore it though. And then we do like this. Okay. And then we just return 0 as a default case. We can either like have a default case there, but I like to just have return at the very end. So that's the the conversion between a token and a binary kind. And then we're gonna track the priority here. So we're gonna have one signed 32-bit integer, signed 8 bits probably. So get binary priority. This is gonna take in a binary kind. We're also gonna use a switch here. So if it's, I need to check this. See order of operations. So we're basically going to implement this table. So it seems very complicated and it's very simple for us because we're going to just track this number. So the precedence here is falling, it seems like. It is falling. And you can see that associativity is wrong. Some is left to right, some is right to left. The ones that are right to left, we're gonna have a separate parser for that. So that's all the unary expressions. Yeah, so we're tracking this. Relational, that's number 6. So we have an priority here, plus minus, multiplication and division. So this has lower priority, this has higher priority. I didn't know that. Anyway, okay, so if it's either, is that the same? Everything here is the same? Yes. So if it's either equal, let's do this. Binary less equal greater or equal. So if it's wait a second, equal is that one. So that has a higher, what the hell, that has a lower priority. So this will be taken first. So in other words, this will have a lower priority. Let's we can probably write it in the right order. So I'm gonna write it like this. Return, say like 20. And this is right beneath. So probably 19 though. 19 then. And then we have plus minus, plus case, binary minus. Then we return. That has a higher priority, so we're gonna bring it up there. So higher than 20, it's 21. Let's do 24. Maybe we're gonna add stuff between these cases here. Binary multiplication and case return 20. Let's do 30. Okay. So once I have all the operators, I'm gonna fix these numbers, because this only needs to be like 1, 2, 3, 4, and so on. But maybe I'm gonna have multiple stuff placed in here. That's why I'm having it like that. Everything is handled. Equal, yeah. A default case is gonna be 0, like a priority of 0, because that's the lowest priority you can have. Yeah, so that's no priority. Yeah, perfect. And actually, we're gonna call it with yes. All right. That's gonna get it here. So now we have this function here and this function. So the case is that when if you're only having like multiple, like 1 plus 2 plus 3 plus 4 and so on, you're gonna get the same priority all the time. And since this is left to right, you're gonna stop recursing all the time. So that's the thing. So you have to track if this has higher. Cool feature. Wim had it for decades. Please make should that be right? A and B. What do you mean by that? So you have to add the parentheses? They are unary expression. That's going to be handled differently. It's going to be handled a different place. Yeah. I don't know what you meant by the parentheses thing. Well, the first thing we're going to do is we're going to parse a unary expression. So each of these factors, binary, like each of these factors here are unary expressions. They can be like the address symbol, it can be this one, it can also be a sub-expression. So that's going to be handled by this function here. So parse, let's call it unary. Parse unary expression. VS Code is running slow now. And parse primary expression. We can also have parser in there. I'm gonna try to eject my keyboard. Maybe that's the problem. Probably is gonna be better. Okay, so this is a main expression parser. This is gonna be called with a priority. So we're gonna track the priority here. It's gonna be assigned. It's gonna be assigned 8-bit integer. Priority. This is the previous priority. I'm just gonna call it priority. It doesn't matter. Then we're gonna start with parsing. You see, the first thing we're gonna parse is the 1 here. So you're gonna parse a unary expression. This is like one single thing. And then you can have a binary between. So we're gonna start by parsing this unary. We can call that an expression. I'm gonna call it unary. Parse the unary expression. Okay, so don't worry about the rest. Like, this is gonna start by parsing this number. And a unary expression, it is just gonna return parse primary expression. We don't have any unary expression yet. So this is just gonna call in here, and that's gonna parse a primary expression. So it's gonna give the token, the parser to this function here. And then we're gonna have the main while loop. And what we're basically looking for, actually we can call this left, because we're gonna make a new binary operator in here. So we're parsing the left expression here. And then we're gonna get the next token. So we can probably have it just in here. It's supposed to be get current. So this will parse the 1, and it's gonna move the pointer so it's pointing to plus. So the token will be get current token. Current token. And then we're gonna transform this to the right binary type. So first we want to get this one, the binary kind. Binary kind is token to binary kind of token kind. So this is now getting the operator here. And also we have to be careful, so we call this with a priority, which this one never is going to get. So I would probably say -1 here. So I'm going to say -1. So because the kind here will never be -1. And if this is 0, it's gonna go out. So we have to check if the priority is still or rising, or if it's still or If it is rising, we're going to continue to recurse. Does that make sense? Yes. If it is okay, so the new priority will be, let's just write it out here. Cyanide new is equal to what's it called? Get binary priority. Get binary priority of the kind. So if this new priority is smaller or equal to the given parent priority, it is gonna return. It is gonna return something. So if the priority is falling, or still it's gonna stop the recursion. And we also need to track if we're calling it with the priority, like let's make a define for that. Let's make a number instead. Do we need that? If the new priority is less than the caller, like this priority will always be something, and if it has 0, that's fine. We can just do it like this. So if the new priority is less or equal to the old priority, is going to stop recursing. So if the new priority here will be 0, so none of these are present, it's going to stop recursing. If it's getting like a different thing, like an integer or something not an operator, it's going to give 0 here. And because we're going to get 0 here. Wait a second. Is that? Yeah, token kind. Binary starting at 1. So 0. Yeah, so if it's not none of these, it's going to be none of these either. So then it's going to have 0, which is a lower priority, so it's going to stop recursing. In this case, we're going to just return the left one. So if we have, like we're parsing the 1, that's up here, then we're getting the priority here, which is a multiplication. And then we're calling ourselves. So here's going to be like expression right is equal to parse expression parser and the new priority. So basically, if we're getting this first, the second call left is going to be 2, and we're checking this plus sign. And the priority is falling here, so it's going to stop recursing. It's just going to return the 2. So that's when this is happening. So it's returning the 2. And we have to make a new binary, what do you call it, node here. So we're going to make an allocator for that. New binary, that's an expression, so I'm gonna make 2 new functions there. A new binary, that's just a void function. Expression kind. I need to type for something else. Expression. There we go. Oh, thank you. I got it. New expression. Let's set the type first. So expression. Return expression, and new binary we'll call. We might need to do something in here. I'm not sure. Like, should this function take in all the things needed to make a binary expression? That's what I don't know. So I'm gonna, if I'm ending up doing that, I'm gonna write it like this. Okay. So just returning a binary, which is the same as an expression. It's the same address in memory. So new binary, we're gonna allocate a new binary. That's it. And we have a left and we have a right. So here the left will be left. Right. So we're making an operator on this, and we also need, do we have the operator? So this is the first time we actually need to store the token. And since we're using this cache architecture for, now I'm sounding way too fancy. That is not right. Okay, since we're using like a buffer on the cache, we don't allocate the tokens there. So we have to make a copy function. We're gonna have to copy a function, a token. Static token. I'm gonna say new. I'm gonna say copy token. New is very close to next, so it might be thought of having something to do with the lecture. Copy token is going to take in the token and we're going to say new column. Wait a second here. I'm actually going to do a mem copy, because the size of the token can change. Yes, I'm gonna do a mem copy here. Let's just use a U8, like a byte access. Source is equal to token. So you're just getting the address of this token here. Yeah, and the destination is the new one. So we're going to iterate until the size of the token, which is in number of bytes, and we just say like destination plus plus equals source plus plus. And return new. So this is copying all the data from this old token to this new one. So what we would do here, we're basically looking for this one, which is the current token. And before we parse this expression, we want to take the new one. So next token of this lexer. Skip the operator. So this token here is actually what we want. So since this is just a, and we don't want to copy the token here, because this might stop recursing, and then the previous call will actually do this for it. So I need to allocate it down here. I need to actually do it before the parse expression. So I need to move this down. Fuck, that's gonna be annoying. We're gonna have it here. So I need to fill in the binary operator, which is equal to the current token, which is this one. So I'm gonna say copy token. And I don't need this. I can just write it directly. All right. So this is filling in all we need. It is allocating a new one, and we're assigning this left one to the one leaf, like arm, and setting the operator. Then we get the next one, and we recurse down. So what happens if the priority doesn't rise? Or like, that's why we're calling this with, for example, -1. Because then the new priority will never be yeah, we can't just do this. We have to do, because we have to track when this is 0. Because the priority here will eventually be -1 on the first call, and this will always be bigger than -1, so it will recurse forever. I'm gonna actually make it a define for that. Define init priority. So no priority, that's 0. Init priority is -1. So if it goes down here, it's going to give no priority. If new priority is equal to this, or the priority is falling, then it's going to stop recursing. And at the very end, if it doesn't stop recursing, it's just going to go in this loop here. So then we have to replace this left node with the binary. So we're actually going to say left is equal to binary. I think this is it. Do we need this for something else? Token to binary kind. Yeah, all right, that's fine. We could also place this. We have to place it under. All right. I'm gonna start at the parser just to make sure I'm not doing anything stupid. So now I'm just gonna go. I'm actually gonna go implementing this one really quick. This is simple, I think. So this is going to parse a primary expression. So when it's pointing here, this is going to call parse unary. Unary is going to call parse primary. And I'm going to end up here. Lexer. And we're gonna switch on token kind. So case, do I have a number? So if this is a number, I have to have a primary expression anyway. Yeah, so if it first is going here, it's gonna have a primary expression. Yeah, so this is gonna force a primary expression. So therefore I'm gonna allocate the primary expression up here. We could use new expression here, and we just say, I want the expression primary. And that's a primary expression. So if this is a number, then we're going to set the number equal to token number. I probably also should say the token. If this is if I can't use this primary token somewhere, I need to know where this token is. So I'm just gonna save the token there. Primary. There might be some primary expressions where, yeah, tokens. That's gonna point to the token, the primary token, which is supposed to be one single token. And we say primary token to copy token. So we're saving the token here, and we should break. And after all, we return the primary expression. And we have to use a cast here because we're expecting an expression, but we're given a primary. But this is the same type, like you can see it here. It is literally the same type. This is a union, so it will be the start. It will start with the same address. What keyboard do I have? I have a, what keyboard do I have? Digma Race. It is a really nice keyboard. It's a split keyboard. Customizable. Really cool color animations. Holy crap. It is like rainbow and you can actually program it. You can set every single color on this keyboard, and it's lighting underneath, and it's really well built. It was a little bit expensive though, but I'm really happy with it. For VS Code, I'm using Source Code Pro or something. Yeah, Source Code Pro. It sounds really nice. Thank you. I think it's cherry red. Cherry red switches. Okay, so that's it. So basically, everything we're gonna be doing, and it's gonna get much more complicated than this, than what we have written here. It can get crazy complicated, but it doesn't matter. These two functions gonna fix most of it. Yeah, it is so nice. I really enjoy writing code which looks this clean. I don't know. Kind of have to save it there. I'm gonna do one more change here. I'm gonna say that the token equals eat token. Do I have support for that? I don't. So this eat token will consume. Like somebody calls it consume. I think Rust calls it consume, but I'm gonna call it eat. I'm gonna call it consume. I like that word. I'm gonna call it eat. Okay. in fact, it's going to return the current token. It's going to advance the pointer. It's going to process the next one, but it's going to return the current, if that makes sense. So we're going to save the current token, and then we're going to get the next one, and then we're going to return the current token. Doesn't this seem very similar to something we did a different place? I thought I did this before. Anyway, so this is basically gonna get the operator, or we can just call skip here, you know? We can just call skip. That is probably more clean. And then you assign all this stuff. So you copy the token there. Oh, this requires the token. Yeah, because that's saved. So this works because of our like token buffer. So we can actually process the next one and still get this. So this is probably a little bit bad, because if you tune that undo count, this might not work. It might work with 1, but if you set the undo count to 0, this might not work. Or it still might work. I don't know. Probably not. So just like remove the element. Should like remove that returns elements. What do you mean? From collection. Yeah. So the thing is that I'm going to try to explain. Here we go. Okay, so like if I have tokens like this, it's going to point somewhere. So the Lexer, so this is pointing to a token, but the Lexer has this pointer into the file. This is going to point to an actual location in the file. If you do next token, you're gonna move this one up here. You're gonna process the next token, and you're gonna return this one. So let's take the other cases. Peak token, it is gonna process this one, or this one, and so on. So if you're gonna peak like, if you're gonna peak like 1, 2, 3, 4 tokens, you're gonna process all these tokens here. It's gonna be placed in a cache, and you're gonna return this one. But you're still not gonna increase this pointer here. You're not gonna do that. Like technically you're gonna move this pointer in the Lexer way. This is the pointer to the current token. And undo next token will actually move this back again. Peak next will not change this one, but will return this one. Current token will just return the current one. Eat token will return this one, but it will move the pointer so that the next time this will point here. Expect token will return this next one, and it will make sure that that token is a specific type. So if this token is like, for example, a B, it will give an error. So it will return the next token anyway. The skip token is what we're going to be using most, because we're tracking we're actually moving the token pointer to the last or first in each statement. So if I'm parsing like a statement plus something like this, I'm gonna end up pointing to the last element here. If I'm parsing this expression statement, it's gonna be pointing after this last part. So that's why we're gonna be using this the most. And this is just asserting that the current token is of a specific type, and it's gonna return the next one. So it's functions for all the use cases we might encounter. Delete this. Oh yeah, I should delete this. And we're gonna make this static. All right, so we're gonna try to see if this works now. Just go through one last time how this actually works with an example. Let's do this case. Okay, so this is going to be called, I want to parse this expression here. So I'm going to give it an initial priority of -1. This is the init priority, so -1. And you can see it's going to first try to parse this unary expression, which is 1. So this is going to be the first it's going to try to parse. So it's going to be getting a 1 here. That's fine. Then it's going to look at the next token after the 1. And as I just said, we're going to leave the pointer, like the token pointer, at the end of each single statement. So if I'm parsing a primary statement here, the token is going to point here afterwards. If I'm parsing the expression, I'm going to leave the pointer after this last token. So the token is already pointing to the plus, and we're just getting that one, the current token. We're converting it to a binary type, which is just the same thing, just different naming. And we're tracking the priority. So let's say we're getting plus, which has a priority of, let's say like 5. So plus has a priority of 5. Then you check if this is a valid priority, 5 is a valid one. And the new priority is bigger, right? 5 is bigger than 1. So it's gonna not do this. It is not gonna return. And it's gonna go here, it's gonna skip the plus, so it's gonna point to number 2 instead. And then it's gonna make this binary operator. So this is gonna be made. So I'm basically making something like this. And the left-hand side is the left node up here. And the right-hand side is, we're gonna recursively call parse expression here. So what we're placing here, do I have a wrong setting here? US keyboard. There we go. So this hand side is going to be a new expression. So then I'm going to call this recursively again with a pointer pointing to the 2. And it will parse the number 2. It will see that the priority is the same as the previous one. I'm calling this with priority 5, and it gets a new priority of 5 because both are plus. So this is going to just return the left. So return the 2. So that's going to yield a 2 here. Going back to the first function again, I'm filling this in. And then we're switching out left equals binary. So what I had here, what is up here, is basically the binary. So this binary expression here will now be the left leaf of a new expression. That's how it works. It's very stupid. I'm gonna write a little explanation here later. So it's cool. This should be able to parse. I probably have a lot of errors. Enumeration value not handled in switch. Oh. That I don't want that. I do not want that. If I said something like default, it will probably say that's fine. Where do I add it? That's better. return parse expression. How am I calling that? Yeah, down here. I guess we have to fix this. This is supposed to parse a statement. And if that is not a something like that, it's an expression statement. So I'm going to parse this one. And just verify that the return type is the same, expression, and so that's wrong. This is expecting a statement, but I'm having an expression here. So I have to transfer this to an expression statement. Statement expression. So I'm saying that this statement here is just an expression. And then I'm going to say that the expression pointer is basically this here. And we're expecting a semicolon and returning a statement. That should be better. Is there so many errors? All right. We haven't been testing for a long time. Include asserts. We also need to declare these functions here. So I'm just gonna split the screen. Yeah, copy token can stand there. This is a static function. Because I'm going to call this all over the place, I'm going to call these functions here. So I might just declare them in the top anyway. Parse unary, parse primary, parse expression statements, and this is supposed to return a statement instead. Yeah, this is a static one. Parse expression statements. That's a static one. This is not a static one. This is the one we're calling. This is eventually going to be a static one because we're going to call higher level functions. We're going to parse a translation unit, for example. Yeah, I think that's going to get rid of the most of the errors. Almost. Yeah, 118. So we're having trouble here. This is expecting an initial priority. So I said that we're going to use -1 here, and that's defined as the initial priority. So this is basically making sure that if we're having a constant priority, which is never rising, it is just going to continue to loop. Unless it, of course, returns like a non-valid operator in case this will happen. And it's going to return anyway. But it prevents this from happening, which is really unintentional. But not used. I'm not gonna have this error. Okay, I'm sorry, I'm gonna check the chat in 2 seconds. I'm seeing something there. Oh. Oh, no unused function. There we go. What do you think about the REST language? What do you think about the REST language? It's cool. I like the safety thing. I don't like I've tried to get into it. I like to be able to do things the way I want. So if I want to make function pointers and save stuff, I want to be able to do that. So that I don't think that's a language for me, and I don't like the syntax very well. Something is very nice, but some things I do not like. The right-hand side operator like not. The right-hand side operator, what do you mean? If you're gonna parse from right to left instead, because the operator precedence is handled right to left, it is gonna be handled in either this one or this one. It is gonna, either this one or this one is gonna recurse a different way. Probably I'm gonna have a separate postfix parser here. A prefix parser, this one, and a postfix parser or something. And that's gonna be recursing in a different manner. Not using ID because it looks cooler. I don't want to. I really don't want to have... The only thing I need is some text editor which I can type in, and which has an autocomplete now, but when I'm getting faster at typing, that's not going to be necessary. So as long as I can type text, and yeah, I'm happy. It has some plugins. I don't know exactly what plugins. In function, undefined expression to new. So we're missing the new stuff here. Parser. This is having tree. New expression, new binary. Is there something we're not compiling? Probably. Source 1, 2, 3, 4, 5. Okay, so we're missing that one. All right. So we have something unexpected. Let's add this one. So basically this is failing. I'm parsing a compound statement. That's parsing a statement. The statement is checking for open curly. I'm calling this first. So the second time it will be calling parse expression statements. So I think we're in here. Okay, so we're getting in here. We probably need to skip this token here. That's a problem. So it still gives a fault there. It's expecting a... Yeah, it is. This is failing. So this is really going to eat the current token. It's going to consume it. I actually like the word consume a little bit more. All right. So the problem here, I don't know why it gives this one, but basically I think the problem is this parenthesis. So that should be handled in the unary expression. So this is going to be called 2 times. Test. Okay, so the second time this is being called, it's failing. So basically we have some kind of sub-expression here. And that's really cool because we're just continue the recursion down here. So this function is going to call up here again with this sub-expression. So we have to check if... And we have to check if we have an open parenthesis. If that's the case, we have to skip it and call this parser again. If token kind equals token open parenthesis, this is the final recurse step, and then we're actually done. If that is equal to open, we're gonna skip the open. There is probably some compiler which has a function for it, like skip if it is, but I'm just gonna skip it manually. We might make a function for it because we're doing this kind of often. If it's equal to skip parentheses, I'm getting the next one. And parse expression again. And this is a new sub-expression, so that makes sense with the init priority. So we're parsing this again, and we skip the closing parenthesis. We're expecting the next one to be a closed parenthesis. And then we return that one. So that should handle everything. So it doesn't matter what operator you're using. It doesn't matter like parentheses. It does really not matter. It's gonna parse it successfully, which is really cool. It's not that much code. It is like it is really only this function here, this one, and this one, which I think is really cool. I like this algorithm. I'm printing okay. So we have 2 lines. And we're having 2 expression statements, so that makes sense. It can actually parse everything. It doesn't give us anything, so we have to make some kind of printer for visualizing this. So I'm gonna make a new function called tree printer. Yeah. Tree printer. Let's see how fast this is gonna go. If not defined, to really concentrate when I'm writing this. Okay, so we have support for compound statements. So this is gonna take in a compound statement and print it. It's gonna be a void function. Print compound statement. This is really not a thing. We're going to print a statement. And if that happens to be a compound statement, it's going to recursively call itself. That's going to make it so much simpler. Statements. We can't write the code in here. Yeah, the printer here also needs to know what kind of stuff this is. So I'm gonna include tree. This is where all the types are. We shouldn't get any errors here. we should, this should be a valid tree. So I'm just going to include tree, and that should be fine. Okay, last time I did this, it was really not very nice. So I'm planning to do some changes, I think. Yes, I think so. We're going to make it look like a tree. Tree printer. Smart code completion. VS Code is very nice on that. It is actually really cool. What strategy are you going to use for memory management? That's a good question. We will handle it at some time. We will handle it. But currently I'm just allocating memory, and that's going to go on the TCB on the OS and get freed when you switch when you kill the task. So that will work on Linux, and it also will work on my OS because I track that specifically. So if I didn't do any memory management, it will still work. But I think that's probably not the best way of doing it. So we have to make some memory management, but I don't know yet. We're gonna fix the language first. It's on CD, I think. If any, yeah, we're gonna figure it out later. Let's go into main. So I'm parsing a statement, and we're gonna print that statement. All right. So I'm printing the tree here, which is fine. I'm just doing this. So the statement has a type, so we're gonna switch the statement kind. We're just gonna handle everything here. Do we have anything more? Kind count, no. Okay, so if none of these are being handled, we can make a default state. Here we're gonna actually print something. Handled. So this just lets me know if I don't have handled a statement there. Yeah, if this is a compound statement, we're gonna actually get the compound statement here. The compound has a list of statements, so we're gonna iterate that list. So we need to include lists. So I have a function which is iterating for us. So I have to make a list node. That's just the iterator basically. And then I say list iterate with this node, and I have to specify the list. So this is the statements list. So each of these statements are supposed to have a statement. So I'm gonna say like new statement is equal to list to structure. Okay, so basically when I'm iterating here, I'm iterating these nodes here. So every single address I'm getting is this one, is placed here. And that's like that last line is converting this address into this one. So I'm getting the address, the statement based on this list node here. Statement and list node. So I'm basically looking for this element in this structure, and I'm doing some pointer subtraction on that. So now we have a new statement. I'm just gonna print that statement. Okay, I want to have, like, how am I gonna do this? I think I need actually a mask on this. Maybe I'm not gonna do it. Maybe I'm just gonna do it like last time. No, you know what? We're gonna try to make something work. So I want to print it like how I'm getting this. I'm printing a statement, and this is a statement here which is gonna go through this again. And if this is an expression statement, I'm gonna print the expression from expression. So I'm gonna print this. So I need a new function for printing that. So I want to have like, let's see. This is gonna be structured like a tree downwards. So the way I did it before, I think I did it like this. Node. And so on. So basically, it printed all these indentation lines. That will in fact be like one more. So this indicates that, I think it was like this. So this node has, or consists of this node here, and okay, let me just fix that. It will be like times here, and then you have an expression, an expression. So this is the operator, and it operates on these things here. So what I would like instead, I would like to get rid of this. So it is like this instead. And like this, of course. Assuming that there is something before it. Like the reason that it has to be that long out. So I want to get rid of these. And why I didn't do it the last time was, it is tricky because you need to know, basically you have to track each single line here. And I just didn't want to do it. But we're gonna try to do it now. So based on indentation, I want to have a like a paint mask or indentation mask. What will the compiler compile? It will be compiling everything the C compiler can compile. And in a little bit different syntax. But yeah, it's gonna be my new language that I'm gonna use for everything. Bool. So it's some kind of paint mask. I'm just gonna call it mask. Let's have a maximum number. max indentation. Let's do 32 or something. So I'm going to allocate 32 booleans for this. And we also have to track the current indentation. So now I have to think. The first time we're gonna do something, we're gonna, for example, say, I want a statement. And that statement is gonna contain okay, this is no indentation, so when indentation is 0, it's gonna be like this. And for each indentation, I'm gonna use this. So this will, for example, be an expression. And if this consists of a new expression, I'm gonna have 1, 2, 3. So where's the new line's gonna go there? If I make this a little bit smaller. It's gonna go there. It is gonna go where this actually starts. Something like this. So I want to print this. So this is indentation 0. This is one indentation because you're basically looking at the indentation of the word. This is indentation 1. This is indentation 2. So 0, 1, 2. So this is indented 2 times. I want to print something with indentation. Indented print. This is gonna take in a char pointer. So here we're gonna first print this kind of thing. And it's gonna look at the current indentation. So if indentation is something, if it's like 1, at least 1, it is gonna loop from 0 to the indentation minus 1. And we know this is going to work because we know the indentation is non-zero. So in this case, that's going to be 0. And here we want to print. We want to print like this. Three characters. And at the very end, we want to print this. And then we want to print the actual data here. So I'm going to print a string, data, no new line. So the thing is that I can't just paint these. I have to make sure that the indentation can be painted. And so this has to be painted anyway. But this will not be painted if I'm not going to paint it. So this is indentation. This is indentation 0. Yeah. So I'm going to look at the mask here. If mask if mask of I, right? That's the first, that's beginning with 0. Else, that was too much, like this. All right, so that's, I feel like that's gonna print this based on the indentation. And the print statement will, okay, so we're gonna print, how are we gonna do this? We're gonna print compound. This is a compound and we're gonna print it here. Indented prints. Compound. And a new line. We have to do the new line. And we're assuming the indentation is 0 by default. So that will print it like this. And if the indentation is 1, this is not going to happen. Yeah, I think that's going to work. So a compound statement is going to be consisting of multiple of these. And I'm just gonna increase indentation here. Indentation plus plus, indentation minus minus. And if it's an expression, we just print the expression, I think. Yeah, we're just printing the expression. And that will be indented prints expressions something. Let's just see how that goes. Exit. I'm not sure if it would be useful, but you can just print the ast in dot format and use the dot. You can just print the ast in dot format and use the dot. PDF PNG. Is it like a generator, like which is pre-made? I don't know, I will try to just keep the code in this project. Graph generator, okay. Yeah, that's... we could do that. It's actually nice to have like some visual thing. I'm gonna start by doing this and we'll see if it works. I feel like it's gonna be better than the last time because you're gonna see these indentation lines better. Where's the list? That's a good suggestion. That's a good suggestion. Okay, so I have like list to structure. Okay, segmentation fault. Very nice. It's having a compound. It's having just one compound. So this is failing. If this is not initialized, it's supposed to fail. Compound statements. So I need to verify that this one is actually properly initialized. And I'm doing list init there, which is strange. But I'm not returning anything. That's a problem. I hate having an error if I'm not returning anything, if I'm not returning something. This is so stupid. There we go. Compound. Let's see how many compound statements this is gonna parse. That's parsing 2. So it places 2 statements inside this list. And it is returning compound here. So parse compound statements. And if this is open curly, it's gonna return that one. So to me, it seems like that's gonna work. Like we're giving it the statements. That's compound. Oh, I'm only printing it once. So there we go. So now it's gonna print it 2 times. It's beautiful. So let us enable this one. All right. So far, so good. Where am I getting that? Oh, this is not supposed to be there. Oh, it's supposed to be up here. Right. There we go. So the compound statement is consisting of 2 expressions. There we go. And this has the indented print. Also, I would like to, if this is the, I need to check if this is the last one. Otherwise, I'm just gonna get rubbish on the last line. So this expression here is, like if this is nesting downwards, I'm still gonna get this. Something like this. I have to, on the last here, I have to unpaint this one. So I'm gonna paint number 0 between these. I'm gonna paint it first. So I'm gonna set it a mask of, let's save this indentation here. Indentation. So we're gonna paint this one. And we have to check if this is the last one. So if this is the last in the list, if this iterator is the last one, then iterator next one is equal to the compound list itself. That's just how the implementation is made. So if iterator is equal to the last one, we can just print it first so we can see if that it works. So you can see it prints at the last one. So exactly here we want to disable this mask. This mask. And if this doesn't print anything, we're also going to disable it. So at the very end, this is disabled. Yeah. So now we can continue. So I'm basically painting, the expression is now printed at this indentation 0, 1. So I want to paint number 1. So I'm gonna first store the expression identifier, no, indentation. This is equal to indentation. Are we going to store it? Are we in fact going to print expression? I mean, we can. Like, if we're going to print this, then this is not going to be tracked. Yeah, we can do it like this. What's up, said who? We're making a compiler. So I'm a little bit like, my head is really into this compiler now. So I'm sorry not keeping too much attention on the chat. I'm gonna improve myself. I'm gonna try to keep more attention on the chat. Yes. So this is a compiler. So very soon we're gonna see if this is actually working. Or maybe it's not. I don't know. We have to see. Hello, Argus. Welcome to the stream. Nice to have you here. So here we're going to switch on the expression kind. And if it's a unary expression, we do something. I think I'm just going to write the code inside here. About a compiler book, but I'm just not in the situation to go into that. Oh, that's like, you probably should. I never read a compiler book. I feel the best way of doing it is just trying. And it takes some time in the beginning, but I don't know. It is better to do it wrong, like 4 times or 5 times. Like at least at the very end, you're gonna learn more about the problem. So it's gonna be easier to do the right solutions, to do the right things. I don't know. Okay, so unary expression we're gonna print with indentation, indented prints, unary. We're just gonna print, this doesn't, I want to be able to do this. I want to be able to do this. Something like unary. Why is not that working? It's probably because of the function. Yeah, so we have a token here, which is the operator. And we might want to print, or do we have a kind? I'm gonna print this based on a kind. But in any case, I want to have some parameters in here. So I want to be able to do something after. So this is eventually gonna be a table. It's going to be a char pointer. Each element in this array is going to be a char pointer, which is a string. And this is going to be unary kind. Unary kind. So this has to map directly with the unary kind. So let's see if I can find that. Unary kind, we don't have a unary kind, but I probably should do this. The binary kind we want to print. The primary kind, no, we kind of don't want to print that. It is really just a unary and a binary. The unary doesn't have anything, so none. So if I'm given 0, I'm gonna just print 1, no, none. And for the binary, currently working at the SDF font renderer. writing the open type shaper myself as well. That's really cool. How do you, like, how is that? Is it hard? Because I've taken a look at TrueType before, and like all those Bezier curves, and when you get down to that kind of thing, it's starting to get hard, and the format is not very well documented. It's hell. Oh my god. But that's really cool. What are you going to use it for? Like, where are you doing it? So binary kind, we're going to start with none. Let's just write the symbol. Yeah. Division equal less. This is really mindfuck. Less equal. Bigger or equal? No, just bigger. Bigger or equal. And that's the last one. All right. So here we have these sort of like the string representation of these kinds, but I still want to do this. So I want this to take in a variable argument list. So I'm going to include standard arg. And then I'm going to make a VA list arguments. So this is basically going to encapsulate these arguments there. And we need to say to the compiler where this starts. So this is starting after the data. You say that the argument starts after the data. Actually, I'm gonna move this down because I'm not using it up there. I'm actually using it just here. I think this is the one I want to use. Restrict char vsprint. Okay, this is printing to a buffer. I'm doing it for an Islamic program, more complex Arabic font rendering, since I needed dynamics, text scaling, and so I decided to use SDF. But it ended up being more complex to handle that. But I learned quite a bit. Yeah, that's I can imagine that's a really complicated project. Yeah. What are you writing it in? Is it in what kind of language are you writing it in? Do you need modulus in your binary kind? Yeah, I need. I'm gonna add a whole lot more, like bit shifting and many things, but I'm starting with this just to make it simple. It's C89. Okay, that's cool. But using C++ for the program. That's cool. Like, that's really complicated. I would never have done that. Okay, so this is the I think is VSN prints. There's so many different options there because this is tracking the max length as well. I'm not really gonna care about that. I'm gonna have a I'm just gonna have a static buffer. Let's place it up here. So static in this kind is that it's basically global. It is not placed on a stack. So I'm having like 1024. That should be enough. I'm gonna give it buffer. This is 1024 lines long. The format is a data, and the VA list argument is just the arguments. And this is also returning the size. And then I'm going to say VA end of the arguments. So now we're going to have a buffer with this size. So we're going to just print it like this. Isn't that right? Probably a typer. Sure. So now we should be able to write it like that. In other words, I should be able to do unary kind of unary kind. And then I have to assert that this is not going too big. Assert unary kind is let's say less than unary kind count. So it has to be less than this one, less or equal. Yeah, it has to be less or equal. This is 0. No, it kind of have to be less than. Assert unary kind, but we're not going to have a unary expression there. No, we're going to just return a binary, so I don't think this is going to happen. But we're going to assert less than. I don't think that's going to happen now. In case of binary, that's the expression binary. Assert binary kind is strictly less than binary kind count. Okay, and then I can do an indented print, and we're gonna say binary, and we're gonna print the operator. I actually don't need this. So this is gonna be binary kind, binary kind. So it's just printing if it's a binary or not. Yeah, so unary won't do anything. Unary will not paint any mask. This will only do print expression of unary operator, no, operand. So this is the sub expression. So we're gonna have something like unary deref, and then we're gonna have below that, we're gonna have the address, for example, or the expression is going to be derefed. For indented binary, I actually want to indent this a little bit. So you're going to do indentation plus plus and indentation minus minus. The same thing here, but I want to store the binary indentation first, which is this, and then we do plus plus indentation minus minus. So between these two, I'm gonna print the binary leaves, like arms, the two binary expressions. So I'm gonna print the first one, the left one first, which is binary left, and we're gonna actually paint that one because we have a right one. So we know that if this is the left one, we know that they will follow a right one. So I'm gonna paint this line all the way down. All right, and then we're gonna print the other right side here. How's this looking? Assert? I need assert. I'm still going. How long have I been streaming for? Like only 8 hours. That's nothing. Like really. I don't feel tired at all. Are really powerful. You can use them in a lot of different things. I'm kind of using them for a restricted purpose. Cheap effects with them. That's cool. Like you probably know how fonts are rendered. I've always wondered how fonts actually are rendered. So like, is everything here is a bitmask which is generated based on the true type? Or is it rendered on the fly? Like it has to be a bitmask. Like some kind of bitmap or with a font. Because the scaling is so smooth, I don't know. It just seems so smooth, but it's probably just happening really fast. Someone doesn't write C. Why won't you use C89? Oh, portability. In good state. Yeah, I abandoned my project with TrueType. I was getting some parsing working, but that's about it. I didn't get it to work. Okay. There we go, we're getting something there. It seems right though. We're missing the new line here, and we have to handle the primary expression as well. Primary equals expression primary. Please work. I'm actually a little bit keen on doing the generator now. Indented prints. This is a primary. So this is either an identifier or a number or a string. So I'm actually going to say, I'm not going to say primary. I'm going to do the switch first. It's supposed to be a switch. So primary, if that is equal to primary number, which we're having, I'm going to print number. I'm going to print a number as well. So this is very nice because now we have that feature. I don't think we have any other primary thing here. Yeah, we only have number. So I'm going to also say else. And we're going to print like handled. This is just so when we're adding more stuff in the primary structure, if we're forgetting to handle it here, it will tell us. Let's do a new line here as well. And voila. Did it work? It gives us binary none. Binary. So it's a little bit wrong with indentation here. So expression needs to indent binary. The expression needs to indent. Not having that. Okay, so we're probably going to indent it here. Indent it and then annotation plus plus. That's gonna make it a little bit more clean. Ah, this is not working. Are forgetting to do minus minus somewhere. Depends how you render, but you can use FreeType to dynamically rasterize the glyphs. Alright, I think I used FreeType, either TrueType or FreeType. Yeah, hello Sebes, welcome back. Making progress? Yeah, we're making progress. This is, we're just gonna make this work and then we're done. Or then we're gonna do the generator. Like, make some assembly code out of this. But like, if we're doing anything other than English, you'll have a problem. Marks are joining script fonts. Yeah, I know it's a lot harder if you're not using like regular letters, and if you're starting to combine letters and what was it, like Islamic letters. That's probably really hard. Yeah. Maps to Unicode. Yeah, those tables are really complicated. EPPP. What is a looks file? Another language? This is, yeah, this is the language we're trying to make now. It's called, it's, what the fuck's it called? Oh my god, I keep forgetting that. It's something with luxurious. Oh, dang it. Luxury is it called? Luxury. I don't know why it's so hard for me to remember exactly that. I'm thinking like luxurious or luxor. It's luxury. Anyway, yeah, so I thought, actually I wanted lux because I liked the extension, and that was actually taken. What the hell? So I thought, like, if I name it luxury, it's something different and I can still have the same extension, which is cool. Yeah. Yeah, luxury. Yeah, I understand you. Like, you probably have it all figured out already. It is in the folder to the right. Yeah, this one. This is where we're going to write the code. Okay, we're very close. The number 2 messes up everything. Like, I don't know why this is happening. Isn't that just... Am I not printing that somewhere else? Okay, let's go through this. We're printing compound, we're indenting here. We don't need to indent before every single thing here. We can pass this up here. Actually, we can delete it all. We can just say plus plus. And this is indented. That's fine. In case of a unary, this is not happening though. In case of a binary, doing plus plus, you're painting the mask. In case of a primary, you're just printing indented. What the hell is this? Like, we're having an expression and the binary is right after. So it doesn't seem like the extension is indenting anything. How am I printing expression, by the way? Oh, I'm printing it here. Print expression. No, I'm not gonna do it like there, like that. That's why it was so ugly. I'm gonna do that down here. there we have something. So this means that we should do binary none on the number 4 and this together. Okay, this actually looks right. Expression is just a number. Yeah, that's right. Expression, and it doesn't indent further here. So the only thing I don't understand is why we're getting binary none here. So that's probably because we're not saving that. So we're saving the operator, but we're not saving the type. So we're gonna say kind equals kind. So remember, we're saving the kind up here. This is just extracting that information. Here we go. That's it. So let's see if this is right. So now we have converted, and this can convert anything, it doesn't matter. So this will do, this is a multiplication, it will of course do the parentheses first. So it will end up doing this thing first, which is in comparison between 4 and 2 plus 2. So you can see it does 2 plus 2 first, and then it compares equal the result of this with 4. So that's the inner parenthesis here. And then it multiplies the result of this one with the number 2. That's here. That's this entire thing up there. And then it does the binary with times 33. That's up here. And then it subtracts that with 32 times 2. So it does this first, and then it subtracts both. And then we have just 23, and just as a number. So there we go. That's the parser. Like, that's the hard part. The rest is really simple. It's very simple. Loops and for loops, if statements are really simple to parse compared to this. So let's write some assembly. Generator.c. Generator. I don't know if I'm gonna call it generator, maybe like x86 backend or something. Yeah, no, I don't know. Just have to see. I'm gonna just stick with this for now. If not defined. So this is how we're like, now the parser is giving us this, and we're gonna generate assembly based on this. And then you have two options there. So either, like when we're starting to do pointer arithmetic and types, and like maybe you want to do struct references and much more complicated expressions, you can either modify this tree here in a later pass, which is probably simpler to do in the beginning, or you can do it directly in the generator. So I'm not sure what we're gonna do. I have to see about that. Is that an AST? Yeah, it's a binary tree. This is magic. Yeah, I think it's really cool. And it's really, like, what I think is the coolest thing is that the entire thing is parsed from this code here. So only this part is parsing this entire thing. It is not that much. Like, hello? This is like 50 lines. Top. It is such a beautiful algorithm. Types of H. We're gonna generate we can generate a statement. So this is gonna take in a statement and it's gonna generate that assembly code. So basically each single, now we don't have any variables, so it really doesn't make sense to have this, because this is eventually gonna end up in the RAX register, and this is just gonna be placed on top of that again. So this will return from the assembly program 23. So I want to just do this. But you have to lex it first. I'm lexing on the go. So when the parser has completed something, it's gonna ask the lexer for a new token. And the lexer is then gonna go through the file and get the next token. This needs some more as well. We need to know we need to know what file it should produce. We're gonna set up the generator. We're gonna call a generator init. And this is gonna take in a const, or probably a string. No, it's gonna take in a const char output file. So I'm not sure exactly how I'm gonna do this. I feel the best way right now is just opening this file, placing it in a file object, and just using that. We need 3 because we need a statement here. Generator. All right, so now we're gonna extend this main file. We're printing the statement, and now we're gonna generate the statements, the program. And we're gonna call it here. So generator init, that's gonna take in the output file, which is in the argument 2 pointer. And generate statements. So they're not defined, first of all. So generator init will just print init. Something, I don't know. Just gonna see if we're getting that. Init and statements. And then I'm gonna take me some water. Be right back. What kind of language you wanna make? It is something really close to C, I guess. It is a C-like language, but it hasn't used like a fresh syntax in my opinion. But yeah, it's very much like C. I don't want, because I like C. So I don't know. It's amazing still to me. No, it's just magical. Yeah, it is. Okay, be right back. right. Okay, so here we just need to open a new file. It is very simple. stdio.h output file. We probably need to call it something different. I'm gonna just call it file. fopen. That's going to give a file. So we want to write here. So I'm going to open this file. If this file is equal to 0, we're going to exit. So like 56. I'm going to just generate like a random status code. So if I'm getting that, I'm going to just search into the program. 56. That's easy. Lower level and solving problems yourself is that you can actually understand how things work. That's exactly right. I absolutely love learning how things actually work. That's why I'm doing everything myself. Yeah. It is very hard to make a library easy to use. Like all my libraries has just been used by me. So I don't know. Yeah, we have the file. Do we need to do anything else? Probably we need to have an emit function. I'm gonna make a emit. Either emit or emit line. I don't know. I'm gonna do emit, and I'm gonna emit a line automatically. So I'm gonna emit some text, and it's gonna be formatted. So I'm gonna include the same thing as we did. stdarg va okay, va end. We're also gonna have a private buffer. Static char buffer. Let's have the same size. Doesn't matter. And then we're gonna say that the size is, what did I call it? Like VSN print, was that it? Yeah, max length. So I'm gonna print to this buffer. The buffer is this long. I'm gonna print the text and the arguments. And then we're gonna just print this to the file. So f write from buffer. Each element is 1 byte. We're gonna print this many bytes to this file. And we can probably do fput c, so it requires a char. So I'm gonna do a new line to the file. So this will, if I'm right, this will print to file with a new line. All right, and it will open a new file as well. And it's opening something at least. Nothing there. Oh, this isn't stdi, it's stdlib. Okay. We're not getting any error code. So I'm wondering why I'm not getting anything. Can we just print a file name here? Making file. We're making build. Oh, we're actually making it. I didn't see it there. All right, so it seems to work. It is this one. So we're emitting this line and this line. So generator init. I'm actually gonna do some stuff here because we have to make a function which is global, and when we actually can parse functions here, that's going to be handled by that function. But until that time, 1, 2, 3, 4, we're going to print global main. Actually, let's do text section here. This is telling that we're going to write some code here. And then we're writing something, generate statements. I'm actually going to do generate program. That is also taking in the statement though. And this will call generate statement with the statement, and then it's going to emit the final thing, which is just return. So if I was to emit something like, I want to move the value 5 into rocks, I need to do double because this is escaping the next one. So if I'm going to do this, I'm going to call the generate program instead. This isn't defined. Just have to define it. So now we get something like this, and this is not indented. 1, 2, 3, 4. Okay, so we're saying that this is some code. That's why we're writing text there, and we're saying that this is a global function main, and this is only placing 5 inside racks and returning. So this will actually return the value 5. So this is in fact a function, and that function is going to return 5. So if I actually run this, I probably have to go in here. We're going to try to run this function. I probably cannot do anything with that. Let's add some compile flags. Some warning flags. Gonna move this up here. And then we're just calling it with flags. That's much more clean. So this is the compiler. And when I make, or when I just type make here, this is gonna happen. So it's gonna first build this target, which is doing this, just building it, and then it's running the targets. And it gives it a test file and gives us the output file here. So that's what it's generating. So then, what I need to do, I need to build I need to link this or assemble this file. So I'm going to call in with GCC here. And I'm going to do the... How did I do this again? Build. Just going to copy this. We're going to assemble this one. And the output is going to be... I'm going to call it outputs. Does that work? We're probably going to make it static as well. Static. Build outputs. Oh, probably it should be like this. Treating as linker scripts. Malib in the background. Build output. Yeah, that was the file. Making the order tree. What do you mean by that? To know where things starts, which operation go first, etc. Yeah, we're actually going to compile this into machine language. So this is just a simple stack machine. I have an S flag to assemble. It says linker input file. Do I need to supply a linker? Let's see here. Input file. Output file. No, this is not the output file. Or is that... Okay, I'm gonna probably need to do the output first. Is that a thing? No. Build. It's actually trying to link this. ASM, maybe that's not the right... Maybe that is not the right thing. This file. Output.asm. I'm gonna do output.s instead. There it works. Okay, so it was a file extension. This is Linux AT&T syntax. Otherwise, I think you have to do a different linker, like some... Oh, what is it again? I don't know. It is very nice using AT&T syntax because then you can just use GCC here. But I guess the extension is S instead, like in ARM. Hello, Ravioli. Welcome to the stream. Ravioli Bakery. That's a cool name. It's like C flag to assemble. Isn't C flag to not compile? To just compile will not assemble? I don't know, stupid. This will not be a problem with mine. Like, I want to write the compiler. I want to give it one single file, and that's it. Then the rest is just going to be built into the language. Like, there is not supposed to exist any command line arguments. I'm so tired of command line arguments. There's not going to exist. I'm really honest. This is it. And this file is going to tell you how to build it. And it's going to tell what flags to use. It's going to tell where to link it. It's going to have the linker script. If I'm compiling for ARM, I need to fix that. Anyway. Build and outputs. We're just going to run it. And we're getting error 5, which is right because we're the output here is supposed to give us 5. So if I go into the generator and I replace this 5 with 56, I'm getting 56 here instead. Yeah, it seems to work well. What are you using for the backend? It's just normal x86 AT&T assembly. Yes. Okay. So we have a stack pointer. I don't know. I probably shouldn't talk anything about x86 assembly because I don't know it. But I know there is some like registers. You have 4 different kinds of each register. You have 64-bit, which is racks, and EAX, which is 32-bit, and AX, which is 16-bit, and AL, which is 8-bit. I think that was right. Yeah, I think that's right. So we're going to be using RSP, which is a stack pointer. So I'm going to have 2 functions for pushing and popping things from the stack. So I could, for example, do like, this is now in racks, and we can move racks to the value of RSP. Is that valid? I think it should be. And then we're moving RSP. Now we can just use push here. I think that's the right syntax. And pop. No. T push pop. That's not AT&T. Oh, what is this? Compiler Explorer. This is really cool. I'm gonna see what they're doing. We're gonna use just normal syntax here. So let's write something a little bit more complicated. Something like this. So that should use some push operands. Okay, so you're gonna just push the base pointer and you're popping into a register. Okay, so I want to push the racks register because that's where everything is going to be. Push racks. This is just going to push it. And we're going to pop... we're going to push... Let's see how this works. Where's my diagram? All right, so we have the stack here. We're going to be using the stack and 2 registers for this. So we have racks and the destination index pointer, which is RDI. So these are the 2 registers. And you want to parse or generate something like a binary, and that has 2 members, which is the left and the right. The left and the right. Okay, so we're gonna start by parsing. I think the right is the first one because we want to store back in here again. So we're gonna start by parsing the right expression recursively. And that's gonna eventually, for example, have like 2 primary expressions. Like we're gonna figure out what this is gonna be, and that's gonna be placed in racks, and then you're gonna push that onto the stack. Then you're gonna compute the left one, and that's gonna be computed into this register, and then you're popping the right one back out here again, and then you compute the operation on both of these registers. So maybe we should take an example. So if I have like times and 2 times 3. Well, let's take the same example. Everything is going back to the same simple example. So this is understandable. This times this plus this. So then it's going to first recurse all the way down. So these 2. Oh, sorry, I didn't see the chat. You're probably much better on x86 assembly. I know ARM assembly like okay. Yeah. EX, EH, EL. Oh, EH, you actually have EH. I didn't know you had that. Yeah, I didn't know you have AH. But that's cool. This is probably used for it. Okay, just push racks. Typically in x84 environment, you use the R stack pointer. Non-manually activation record tracking and RBP for local memory offsetting. Yeah, we're gonna use RBP for memory offsetting. We're gonna set up the stack frame. How's that again? You're pushing the stack pointer. When entering a function, you're pushing the stack pointer into the base register, and then you compute the offsets from the base register for the local variables, and you offset the stack pointer, so you basically save the space for the local variables. And the same when you exit a function, you just pop the base, you just pop from the stack pointer into the base pointer again, just reversing. Okay, so this is racks, and we have the stack here. So this is a stack pointer. RSP. So this is holding nothing. So the first thing we're gonna do, we're gonna parse the right-hand side first. So this is the number 3, and if we're getting a number 3, we're just gonna load that number into racks. So this will be equals 3, and then we're gonna push this onto the stack. So we're gonna push 3 up here. This will now be right. And then we're gonna compute the 2 value, which is also gonna place it in here. And then we're gonna pop the stack, whatever's on stack, back into RDI. So this will now be popped. This one will now be popped in here, and this goes up here. And then you compute this times this and return the result in here. So that's going to give you 6. And then you're here, and this is the right hand side. And then you compute the left hand side. No, that's the right hand side. And then you push this one. So you push Rax up here. And then you load 1 into RAX. And you pop this one back into RDI. And then you do plus. So this plus this is 7, and you store it in here. And if you want to return 7, this is already here. So that's how I'm gonna write the code. So just push into Rax and pop from RDI. We probably want to track the... I'm also gonna track the stack level, so we know we're not doing anything stupid. So this is, I'm gonna say stack level plus plus. And when I'm popping, I'm gonna say stack level minus minus. And this is gonna emit pop into RDI. Yes, pop into RDI. And this is gonna push from Rax and pop from RDI. So that's just the stack operations. The generate statement is now gonna contain a little bit more code. So we need to switch the statement kind. If this is a compound statement, we're gonna do the same thing. It's very similar to what we have been doing before. Yeah, so compound statements. Do we need... Oh, I think we have it here. So we're just saving that. And we iterate the same way. So I'm going to include lists. All right. We actually use the same variable here. But you actually can do that. Like, even though this has a name, you can still use the same name here. I'm forgetting that all the time, but that's really a nice feature. Anyway, statement is equal to list to structure of iterator statement list node. And you just generate statements recursively from that one. Yeah. And we have to break as well. And in case of an expression, we're going to call a function for parsing an expression. Assert expression just to be sure. Well, yeah, we can just call it, I think. because this has an expression pointer, so we can just call it directly. We need to switch the expression kind as well. Case expression primary. And please ask if something is unclear and try to explain why. All right. Expression primary, unary, and binary. So in the case of a primary expression, we need to figure out what kind of primary expression we have. So all this is just like boring stuff to do. It is just iterating the entire tree. That's what I'm doing now. If this is a primary number, then we're gonna emit the number. So we're gonna end up moving, and we have to use this symbol into rocks. And the value is the primary number. So just doing that. Else generate expression error. So it is not handled because we have only this now. Unary, we're gonna generate an error. Binary, we have to handle that. So binary expressions, we want to first compute, we'll first have to compute the right hand side. So first we're going to assert binary is equal to expression binary. So assert that both of these are valid. They should be. And then we're going to generate expression recursively from this binary right. Then we're going to push rocks. Then we're going to generate expression from binary left. And we're going to pop into RDI. And then we have to compute, we have to check what kind of binary expression to choose from. Can you have switches within a switch? Geeks for geeks. Doesn't tell. I think it's possible. Yeah, I totally agree. The code is going to be ugly. I absolutely agree. So we're going to do a generate binary expression. And we're just giving it the binary here. I totally agree. And we're going to call it with that one. this thing. So now I can have a switch here. We're gonna switch the binary kind. So what kind of binary operator we do have? And remember now, I can actually write it here. So we have some kind of operator. So this is in racks and this is in RDI. So this is a setup. And this is the case. So we only have to apply this operator on these registers and store the result in RAX. Like that. So we're going to perform this conversion here. Binary plus. That is simple. Emit. What is the syntax? ATN. Assembly. Is this project just for the fun of it? Yeah, partly, and also I don't like to code in C anymore. So I would love to replace the C language with this for my use, at least. Still going, Pug, good morning. Yeah, good morning. We have been streaming for 9.5 hours. So that's a nice session. Nesting in my shaping lib. Yeah, it is. It needs a little bit of a refactor once you start doodling around too much. Guide to x86 assembly. Oh, here we go. Examples, add. Okay, so this is the destination. You're gonna move this plus this to this last location. So we're basically gonna add, it doesn't matter. Yeah, it does matter. So you're gonna do RDI into racks. So this will take RDA plus racks and place into this register. Where is sub? There we go. So AL is set to A L minus AH. Let's see if this is right. Come on. Come on. There we go. Sub. So you're gonna at least place the result in RAX. So we need to have this kind of syntax here. And now we have to double check because this is doing AL minus AH. So this minus this, which is this minus this, which is this minus this. So that's right. Fortunately, that's right. What is the next one? Multiplication. Oh, it's emul. Emul, integer multiplication. Okay, so here we're starting to have these crazy x86 instructions. You can multiply the whatever on this address with this one. So I think the syntax is the same. We're just gonna do this. Binary division. Divides the content of the EDX Why the hell is it 2 registers there? Oh, there's the result is stored in EAX, which is what we want. Remainder in EDX. So idiv. Okay, so idiv EBX divides the content of by the content of EBX. Okay, so we want to have something like emit what we're going to divide it by, which is RDI, and that's it. And we have to make sure this is placed in Rex. It is placed in Rex, but we also need the EDX to be 0. In fact, we want the upper 32-bit of RAX to be placed in EDX. ID 64 idiv. Oh my god, is there anyone in the chat who understands this? Who really understands what this means? Oh my god. Flags affected, perfect. Is there some examples there? Yes, I understand it a little at least. Yeah. I just understand like the M8 and there is so much special syntax there. I don't know. Okay, so this is, I think this is what we're gonna do. So exclusive OR. That's a smart way of doing exclusive OR, like clearing a register. In ARM, you can just write the 0 register into the destination register. And you arguments. Because this is working if it is just a... The thing is that, what if this is a big number? What if this is a 64-bit number? Then I need to store the upper half in a different register. So I need to do an operation there. This is why compilers change division to a multiplication and shift where possible. I understand, yeah. It stands for register memory. Oh, register memory. But then it should be a register as well. Oh yeah, okay, register or memory. And I guess the 64 and 32 applies to both. Yeah, I guess so. It's just R for register. I think dynamic optimization for specific hardware should be part of the language. Something like GCC FMV. namespace I'm going to implement. Namespaces are important. And also everything you can think of which can go at global scope, like include, use and like namespace, structures, functions, whatever can be written anywhere. So you can have like a tiny if statement somewhere, and you can write exactly what you would. You can copy in an entire source file in an if statement, and it's not going to crash. And I think that's very cool. Where is this? Keep the language procedural. It is going to be procedural. Or the proper operands. Okay. Yeah, I'm gonna not do the include stuff. It's not gonna be a preprocessor. The only place I really like a preprocessor is for iterators. But I feel it has to be a better way of doing that. So I have to see. I'm using the preprocessor only a few places. Yeah. You just want a 0 RDX, or you will get floating point exception. That makes sense. RDX. If you could probably do factors, functions with templates. Like, I'm not sure. I've looked at templates, and to be honest, I haven't figured out any use for it. Like, it's probably just because what I'm programming. Anonymous like template function, what do you call it? Function overloading, depending on the arguments. That I can see a use for. But in many circumstances, I think that can be messy as well. Like, I know there's a few cases where that's good. But I don't know. C++ a better reflection. I didn't see it. What do you mean by documentation? I read your comment above. Oh, there we go. Maybe it's too high up. Templates are useful in game engines and such. Okay. Yeah, I don't know. We'll have to see. It is going to make the compiler a lot more complicated. Like, a lot more complicated. Yeah, anyway. We have to... There's an entire video, 15 minutes on a division. Okay. Apparently we're at x86 now. The IDIV. When doing 8-bit division, you must sign extend. Okay, so sign extend, that's fine. 16 bits requires a x to be sign extended into dx. 32-bit division requires to be sign extended into edx. Okay, so what I'm doing is basically 32-bit division. That makes sense. So that if that's a negative number, we don't support that yet, but if it is, I need to sign extend. Dividend low. What is that? CDQ. Okay, so sign extend of AIX into EDX. So this is probably what we want, isn't it? J does something similar. Templates are horrible. Single function to handle many data types. J does something. I'm gonna copy this one. Okay, I'm gonna save this one. I'm gonna read it. What language is this? Oh, I read about this. I didn't like the syntax. I think I remember I didn't like the syntax there. This actually looks good though. It looks better now than what it did. Yeah, this is I agree with how this should be. I don't like this. I do not like that. Anyway, I'm gonna read it later. Yeah, so basically CDQ. Is that just a simple instruction? You just write it? Apparently. So we need to do emit CDQ first. And IDIV RDE. Okay. Let's just see if this works. I'm gonna get rid of these statements here. Gonna need assert. $55. Generator. Oh, isn't this allowed? What the hell? Really? Okay, there we go. Oh, it still complains. Multi-line comments. Is that a multi-line comment? Generator 56. Okay, I'm gonna ignore this one. I don't need to know that. Why am I ignoring stuff? Okay. So did you mean new expression, generate expression? So this is just implicit declaration. It's very simple to fix. Static void. Let's place this at the very bottom. And generate program. And then this one is static. And generate binary expression is static. And generate expression is static. And probably this as well. And generate program. Oh, I have that. All right. I can see it's generating a value. So just remains to check if that's the right value. Oh. Static declaration. Is that in the header file? I think that might be in the header file. No, it's not. It's not there at least. There we go, 208. Is that correct? Does this evaluate to 208? Okay. Okay. Times 32. Okay, so what is not working? Let's just double check the generator, that everything is correct. You're doing binary right. You're pushing into racks. You're pushing from racks and you're popping into RDI after this one, the left one. And then you add RDA, break, break, break. Let's have a default case here as well. I don't understand the use of CDQ. It's just for sign extending. Like the documentation said, you need CDQ for, because you need to know, like the high register needs to be the sign extend, needs to either be 0 or the sign extended version of the lower register. Like 0 makes sense for me, but I don't know. Error. Do I have an error? And I'm moving the primary number into racks. And we're breaking here. Generate binary expression. Let's try something simpler. Let's just use 33. That's generating 33. If I do plus 33, it's generating 66. If I do times 5 plus 5, which is 10, so 660. No. Let's see the output here. I'm moving that into racks. I'm pushing racks, moving that into racks, popping from RDI. I'm adding them together, and I'm pushing racks. So this will, if I run this will yield 5, I think. Let's make just a compile option here. That is 10. All right, so here we have 10. So Rex is 10 and it's pushed. You're pushing it here. And then you're moving. You're not pushing this one though. We're forgetting to push this expression here. Because you're moving this into RAX and you're popping into RDI. Because like this actually makes sense. But it doesn't make sense here. Wait a second, do I do something stupid? 5 plus 5. It's gonna do 5 plus 5 first. Oh yeah, it's gonna, it's gonna do this. So I have to do parentheses first. This should yield 187. Okay. Now I'm just doing one make compile. So now it's specifically doing 5 plus 5 and 33 plus 33. And you times that together. So far so good. That is right, or actually here. This is pushing the first 5 plus 5. And then you're moving this into racks, pushing racks, moving this into racks, and you're adding these together. So if I return here, that should give me 66. Segmentation fault. That's weird. Why can't I return from there? Segmentation fault. Let's just double check that the stack is working correctly. So after this, the generate, we're gonna assert that the stack level is 0. And the stack level is 0. I prefer C-style syntax. Talking about that. Like for declaring variables, function and function pointer syntax. I've heard that is really bad. Especially the function pointer syntax is really bad with C. And comment with, oh, I didn't know that. Yeah, okay, I understand now. I mean, type qualifier on the left versus right. To swap variables. Like, I don't like that syntax at all. So I think you just should write it in 2 lines. But it's like, it's okay. The gene generator, stuff like a J. Do you have implemented precedence? Yeah, we have implemented precedence. So you can see it's working. You can write anything which uses, anything which uses these tokens here, you can write these tokens here, and numbers. Anything. So that's cool. As long as you don't write 2 large expressions, you run out of stack or something. You don't need 3 registers to implement this. I'm only using 2 on the stack pointer. Maybe just understand what's being done. It's for sign extending. Yes. Yes, but it's using 2 registers. So the division is using 2 registers. So that's why I have to sign extend it all the way up, because that's apparently what the divider is expecting. I don't know exactly how a divider works. I don't know. You're adding those together. Returning here works. That's 10. That's right. And you're pushing 10. And this should still work. 10. That didn't work. Oh, the stack is wrong. The stack needs to be aligned. Wait a second here. Okay. Let us save the stack pointer, so we just know that's right. So we're gonna move the RSP into RBP. Now we're gonna push the stack pointer. You're moving the stack pointer into RBP base pointer. You don't need to do anything here. So after or before the return, I'm just gonna do the opposites. Oops. I'm gonna copy them back because I'm not changing that base pointer. So this will be base pointer into stack pointer. (148). So stack pointer to base pointer into stack pointer. So now I can return after this point if I just remember to do this first. And that works. No, that didn't work. I was actually doing it wrong when I was typing make again. Push rex, return. That's error 10. So as long as we get the stack base right, it's fine. And that makes sense, of course. So we can just use that to check the rest of the code. So you're adding RDI and RX. That's supposed to be 66, and it is. And you're popping into RDI. So this will be 10. If I'm doing racks here, it's supposed to be 10. It is 10. All right, so it's popping into RDI. This is 10. I need to do IML. RDA and RX. Okay, I don't know what that doesn't work. Aren't you supposed to be IML to use IML? Okay, no. When you do 33 plus 33, the exit code is modulo. Okay, but is that because of the code? Like if I was to, let's say like, I don't know what the range is here. Can I do this? Oh, that's actually the modulo. Right. Okay, that's nice. Okay, so we have to generate some expressions which is closer to, or which is kept beneath this limit all the time. So that's like 2 times 4, which is 8 minus 3, that's 5. Plus 5, that's 10 times 2. Okay, so this is going to be, that's 5. So this is 15 divided by 3. So this will give us like 3 or something. There we go. Error 5. Does that make sense? Okay, my calculation were wrong. It is actually right with 5. Yeah, so that's cool. So this is the, I don't know what the clock is. Okay, I probably should I'm gonna go for a walk. It is snowing outside, so I have to get a little bit out. Anyway, this is a really nice start. So it is very simple for us to just generate, like for example, return. I can say something like this, and this is just gonna, it's just gonna generate this expression here exactly the same way as this one, and the result is gonna be placed in RAX, and then this is gonna do a branch to whatever is the last label. So this is really simple. Like this is the hard stuff, I would say. Actually, I think I'm gonna stream tomorrow as well. Oh, wait a second. We're not finished just yet. We're not finished. We're gonna do the comparison, which is really cool. So we're not gonna do -3, we're gonna do -2 minus parentheses 3 equals 2 plus 1. So this will be 3, which is equal to 3, so that's the number 1. So -2 minus 1, that's -3. So this will be the same thing. If I do this, it is not going to work. It's going to give us error 1. And that's because of this one. Is it? It should be because of that one. Printing error. Generate the statements. Oh, we're not actually generating that. Wait a second. Is that? Oh, they said return statements. I can't do return. But why didn't we get any message on that? Like we should be getting this. So the parser, this generates an expression statement, and it expects a semicolon. It's going to parse expression. Is something exiting here? It is exiting somewhere. And I don't know why. Oh, wait a second. It's not. We don't support identifiers yet. So this is actually the Lexer which is having a hard time. So we're getting this one. I actually should print that. So now I'm gonna go fix Elixir. Okay, so but I remove that. Yeah, because if I remove this, it should parse it correctly. But we have an error, and that's because we don't generate anything for it. So equal, we're gonna do a comparison, and we're gonna set, so if they're equal, if RAX is equal to RDI, we're gonna set the RAX register equal to 1. Otherwise, we're gonna set it to 0. Hello, Nay Hey. Welcome to the stream. I'm glad to have you here. You're making a custom language? No, this is like a custom language. It's gonna be very similar to something else. Like it's gonna have a few things which is similar, but I feel like all languages are very similar. Yeah, but it is a language compiler. Does we have a comparison? So compare these two. This is the crap which is with flags and bigger equal zero flag and minus flag and stuff like that. It is so confusing. I guess you can do the equal. X64. No, set if equal. Set CC. Set greater than. Okay, so what is set CC? X64 set. No, not that one. Let's try set CC. Set on byte condition. So this is set byte. So you probably need to set the to 0 extend the rest of the register. So you can set if all these flags, like set if greater, set if greater equal, and what is the instruction again? This is really confusing. Let's just compare. Is it which of these are gonna go first? That's the thing which is confusing. The flags are okay to understand. The difficult thing is to compare. This doesn't help. Really doesn't help. Subtraction, but it does not store the results. Okay, so this is equal to sub that. I just want to have an example. Set E if set with if equal. Yeah, it's at the 0 flag. The question is the other flags. So it doesn't, for the 0 flag it doesn't matter the order. But for the other flags it matters which register I'm placing first. I'm actually gonna go to the compiler just to check what they're doing here. If number is bigger than this, return something. Okay, so if greater, jump if greater to L2. So L2 is continue. So number is bigger than that's greater. It seems like compare low. Okay, so jump if greater. Okay, I'm so stupid at this. This is gonna be an absolute joy to go to ARM assembly again. Jump is less if less equal. Oh, yeah, that makes sense. All right. So if it's less or equal, if number is less or equal to this, which means that this is less or equal to this. Does that make sense? So if I want to check if this is less or equal to this, I have to take this first and then Rax. That does not make sense at all. Probably if you look into how the flags work, it's gonna make sense. But for me now, it doesn't. You're comparing those, and you set if equal. Is that a thing? It is just E. Set if equal, and we're gonna choose AL. So this is byte, so it's gonna be AL. ARM is really nice. It has a really cool instruction set. I really enjoy it. And this might be wrong. Like probably some of you know this. When you write something to AL, what is happening with the rest of the register? Is that being written, or is it just zeroed? Or is that gonna still contain the old values? So do I manually have to change this? Does anybody know? You compare and set equal, move 0. This is 0 byte extend. It is 0 byte extending. Okay, so all the other bytes have the old values. So we have to move 0 byte extend. We have to do this one. All right, so we're 0 extending that register. Yeah. And I'm missing this one. Actually, this is gonna be the same on all. This is gonna be the different one. So maybe we can get this instruction here based on the binary type here. So what we can probably do, never mind, we're just gonna catch all the cases here. So we have equal, less than, less equal, bigger, bigger equal. Greater or equal. So this would be like GE I'm not sure, I'm just guessing here. LE set L set equal. Is that right? Let's see. That seems right. We're missing a break here. Okay, so that's perfect. Let's see if that should work. We're getting 5, which is the right thing, because this was still supposed to be 5, even though we have a thing in here, and we can actually check if this is true. Is this bigger or equal to 5? That should be 1. And is this bigger? No. Is this smaller than 5? That should be 0. And that's 0 because it doesn't return anything. That is so fucking cool. That is cool. Alright, so currently we're basically good to go now. All expressions are working. The next thing will be variables and functions and if statements, for loops, while loops, pointers. It shouldn't take that much time. So, generator, like this is the entire code. It is so small. That is not much. Flexor. That's really cool. Thank you for the cheer, 100 biddies. Thank you very much. Thank you so much. Yeah, so this is really cool. Make count 200 lines. That's really cool. I'm gonna fix up the code a little bit. I'm gonna clean up a little. I'm gonna do some commenting, and I'm gonna be back tomorrow actually because this is fun. So tomorrow we're gonna take a look at variables, functions, perhaps pointers, and yeah. That's it. So I think I'm gonna end the stream now. I'm gonna take myself for a walk. And if somebody still are watching, I'm gonna do a little raid. As always. And it's so nice to be back. I don't know what I've been up to. Science and technology. But it's very cool that it worked. Let's see, who should we raid? Is CodeCon something? It's almost like Comic-Con. That seems interesting. Wasn't much here. Let's just playing your games. Yeah. Let's just raid Go Breaking Things. Anyway, I'm gonna be back tomorrow, and we're just gonna continue on what we did. That's cool. Yeah, thank you for dropping by. I really appreciate it. The goal is to write a compiler so it makes sense to directly emit assembly. Yeah. So, and eventually we're gonna write some ARM backend for this, and then perhaps we would be able to, or we'd be forced to write actually the bytecode ourselves to convert to like binary instructions. I don't know. I have to see. Anyway, I see you tomorrow and have a nice day.